Hello everyone, I am Siddharthan. This is the second video in my deep learning project series where I have added another 5 deep learning use cases that you can learn from. So these videos are something that I have already uploaded and I thought that it would be better if it's in one place so that it's easier for you to follow. So in this project series, I have kind of combined different aspects of deep learning use cases. Say for example, in this case, you will have use case on deep learning project where we build an end-to-end system with a proper Streamlit application, image classification system with a proper Docker containerization. So you also have use case on image generation and building up neural network with PyTorch and NLP use case and so on. So I'll just give you an intro of what are all the 5 projects that you will be looking at in this video, and then you can just get started. And it's also easier for you to follow even if you are not that familiar with the deep learning concepts. So I've explained everything from scratch so that it will be like easier for you to follow. So the sixth project video that we'll be discussing here is Fashion MNIST, where we will classify the images into fashion products using a convolutional neural network. And this is an end-to-end system where we have built a Streamlit user interface and deployed it as a Docker container. And this will be like a good practice for you to get started with Docker and how to create these Docker image and Docker container. And the next one is about a planned disease prediction system, which is also a image classification task, again with a Streamlit user interface and Docker. And then you have this breast cancer prediction with the artificial neural network, but the thing here is we build this neural network in PyTorch. So if you are just used to TensorFlow, this video will be useful for you, where I've just introduced a kind of using PyTorch for building this neural network. And the next video is a pretty interesting one where we try to generate image with GAN, specifically DC GAN, also known as deep convoluted generative adversarial network. So we will try to train a generative adversarial network on the handwritten MNIST dataset. And the 10th project video is IMDB movie review sentiment analysis, where we are going to classify the sentiment or the review as positive or negative with a long short-term memory neural network. So these are the 5 use cases that you will be kind of learning in this video, and I hope that you kind of get all these things that are covered here. And yeah, please continue. Hello everyone, I'm Siddharthan. This is the 6th deep learning project video in my YouTube channel, and in this video let's understand how we can build an end-to-end image classification system with the Fashion MNIST dataset. This dataset contains different class of images belonging to fashion items such as t-shirt, tops, ankle boots, sneakers, etc. This is similar to the MNIST dataset where we had recognition of handwritten digits. We will be building an image classification system that classify the images that belongs to these different fashion items. So first we will try to get the data, process it and build a neural network, and then we will be deploying this neural network as a Streamlit app and then Dockerize this Streamlit app so that we have an end-to-end system. So before getting into this video, I would like to quickly tell you about my YouTube channel's membership program. So you can check it out from the link given in the description. So you will get a lot of perks such as early access to videos and access to exclusive videos, and also you can get the PDF of the presentations that I'm using in my videos. So kindly check it out. If you're interested, you can sign up for that. So let's get started. Before getting into the coding aspects of this use case, let's try to understand what's the workflow that we are going to follow so that you can replicate this for any use case that you have. The first part of any machine learning or deep learning use case is to understand the problem statement that we are working on. So once you have that, the next step will be the data curation. So it's about what's the data that you're going to use and what's the data is all about. In this, we will be working with the Fashion MNIST dataset, and as this is a very basic dataset, this is present in the TensorFlow library itself. So it's not going to be tough for us in order to curate this data. So we can directly import this. And the next step will be data pre-processing. So we can't use the data directly to train our model, and everyone knows this, right? So images are a bit of complex data set, and we need to process this in such a way that our neural network model can understand it and learn from it. And that's what we'll be doing in this data pre-processing step. And this data set is present in the TensorFlow library. So most of the data processing are already done and that's saved. So it saves us like some steps and we can just do the rest of things like normalizing the data, reshaping it and so on. So that's what we'll be doing in the data pre-processing step. And then we have to split the data into training and test data set, where we will be using the training data in order to train our convolutional neural network and test data in order to evaluate the performance of the model. So the next step will be training our convolutional neural network, and once this is done, we will be having a trained CNN that can recognize images that belong to different fashion classes that I said. And once we have this, we will evaluate the model to make sure that it has a good performance and good accuracy score. So once we have have all these done, we will build a streamlit web app where the user can upload an image and classify the image that is belonging to one of the classes that the model is trained on. And once we have this Streamlit app, the next step is Dockerizing this. For this, first we will create a Docker file that contains the list of instruction that we need to give in order to build a Docker image from the code that we have, from the Streamlit app and other Python code along with the model that we have. So once we have done this, we will build a Docker image which will act as the base image for our Docker containers, right? So once we build this Docker image, we will create Docker containers which you can run in order to get your Streamlit web app. Okay, so I hope everyone is clear with the steps, and let's get started with the implementation. So I'll give all the codes required along with this Jupyter notebook where we will be building our or where we'll be training our neural network, and also we also have the Streamlit code and other required files. So I'll put all these in a GitHub repository and I'll share you the link, and you will find this link in this video description. Okay. So the first step that I'm doing here is seeding certain libraries. So deep learning code, or whenever you're building a neural network or building some deep learning or machine learning things, right? So there will always be some sort of randomness involved in it. So consider about train test split. So each time you run a train test split, it splits the data in different manner, right? And if we want to kind of have the reproducibility for it, we always need to set a seed for this. So that's what we are doing here. So I'm importing the libraries such as random, numpy, and tensorflow. So we know that random is kind of like a built-in package for Python, and we are going to seed it with a specific number. So it's not that it always needs to be 0, it can be any number. So let's say you are kind of running this code and you set the seed as 0, you will get the same result that I'm getting. And if you're using a different number, and that's going to be the same result for that particular set. So that's what it is all about. So we are first importing the random library, and then we are seeding this random.seed with 0 as the seed, and then we are importing the numpy a numpy library which is used to create and work with numpy arrays, and we are also seeding with 0, right? And there are a lot of places numpy is used. Say for example, we may need to kind of initialize the weights of the neural network at the start of the training. So all the values of the numpy array will be initialized in a random way. So this kind of a place where it needs to be reproducible in order to get like same results in multiple runs. So this is one of the reasons why we are kind of seeding the numpy library. So this is just an example. So similarly, there are different cases that uses this randomness, and if you want to have like a reproducible results in order to, let's say, for comparison or basically for testing something, we always seed the libraries. And we also seed the TensorFlow libraries as tf.random.set seed 0, right? So I'm going to run this, but before that, make sure that you connect to a GPU environment in Google Colab. It's okay if you even run this on your let's say in your local machine on Jupyter. But if you don't have a powerful GPU, in that case you can just upload this notebook in Google Colab, where you will get the GPU runtime. So you can just go to the runtime and go to this change runtime type and choose the hardware accelerator as T4 GPU. So the default will be CPU, and if you do that, it's going to take a lot of time for training. So most of you might already know this. So if you're not aware about this, you can just change this configuration to GPU. So I'll save this and connect to my GPU session. Okay, so now I'll run this cell. So this is kind of starting my session, and this will run. The next step is importing the dependencies that we need, which is from tensorflow.keras import datasets, layers, and models. So Keras is like a high-level API that kind of makes building or training your neural networks much easier. And even Keras supports both TensorFlow and PyTorch, which are like the most widely used neural network or deep learning libraries in Python, right? You can actually use this in two different ways. You can kind of use the Keras library and choose the backend as either TensorFlow or PyTorch, or you can also import Keras from TensorFlow. So TensorFlow kind of added Keras in its own package as well. So that's what we are doing. So from TensorFlow.keras, we are importing datasets which will have our fashion MNIST dataset and different layers that we need. So often a convolutional neural network will have convolutional layers, max pooling layers, and so on. So we'll be importing those layers from here. And models is basically, let's say, to save your models and other things. Okay, and then we have this matplotlib library in order to just like plot the images and see how the images are looking like and so on. Okay, so these are the libraries that I'm importing. So the seeding is done, as you can see, and now we are going to import this. So I'll run this cell. The next step is data curation. As I said, this is like a basic data set, and this is present in data sets of Keras. And oftentimes, like when you're working on, let's say, in a company, in a client project, in almost all cases, you will get your data set from a database. Okay, so and connecting to a database is not a like big task. So you can always like I mean, like different databases as different packages, different libraries in Python, you can use it. For this, we will just like import it from Keras, and maybe you will also be working on some Kaggle projects, so that you can import from Kaggle APIs. That is like also a simple step. So in this case, what we are doing is from datasets.fashion MNIST. So this will basically kind of load the dataset loader of fashion MNIST dataset to this variable called as fashion underscore MNIST. And later from this fashion MNIST data loader, we will call this load data, which will load the training and test data to these tuples. So the output of this fashion MNIST load dataset is just two tuples, and the first tuple will contain this train images and train labels. So train images is basically the image data which is in the form of a NumPy array, and train labels is nothing but the labels of those images, whether it's 0, 1, 2, or so on. So it's already encoded and we don't have to worry about it. The second is the test set. So this is our training set, our training images and our training labels, and the next one is the test images and the test labels. Okay, you can also go through the documentation of this fashion MNIST. You will also kind of can understand how the data is looking like. So I'll call this. So this will load the data set. You can see the data like loading here. Okay, so this is completed. Next is you can, as I said, this is a NumPy array, but you can also check the type of this training images, training labels, and so on. So I'll run this. So you can see it is a NumPy n dimensional array, same for train labels as well. So let's also print the number of images that we have in the training images. So we have 60,000 images, which is like a good number, and train labels will correspond to that. So this 60,000 is the corresponding labels for these 60,000 images. So I'm just going to kind of take the first data point of, or let's say the first element within this training images, and see like what's the shape is going to be. So for that, I'm saying train images of 0 dot shape. So let's run this. So this train images of 0 is also a NumPy array, and this is the image that we are working on. So these are like small images with height of 28 pixel and width of 28 pixel. So that's what this represents. So similarly, we have 60,000 images of this same shape. Okay, and you can try to print and see this train images of 0, and you can see you have values from 0 all the way up to 255. So the fashion MNIST dataset basically contain images in your grayscale, and that's why you don't have a channel, right? So if it is like an RGB image, a colored image, the shape would probably be like 28 28 3, which basically stands for RGB images, because you have like 3 channels. In grayscale you just have like one channel. So that's what this means, right? So here basically 0 represents black color and 255 represents white color, and in between numbers basically represents the intensity of white color. So that's how you can understand this. So the value ranges from 0 to 255. Okay, so you can see the numbers. And now let's this is basically a NumPy array, right? You can maybe also check the shape from here. Oh, sorry, check the type from here. So I'll say print train images of 0 type. So basically what has happened is the data is already processed in such a way that the image has been converted to a numpy array. So this is from Keras library, so we don't have to worry about that. And if we are working with a raw data, let's say JPG images or something, in that case we have to do that conversions. And you can see all the images in this numpy array will be of the shape 28,28, and it's important for a neural network to have the training dataset and even the test dataset to be of same shape. So you can't have some images with, let's say, a particular shape of 28,28, and you can't have some other images of shape like, let's say, 150 width and 150 height, right, which are basically the pixel values. So you need to have like a common shape for all the images in the dataset. So here we don't have to worry about this. I'll also post videos on more complex use cases where we have to handle all these things. Okay, so we have printed this, and you can use matplotlib library. So we have this plt.imshow. From that you can just call cmap is equal to gray. So this will basically display your numpy array as an image in grayscale, and I'm calling this plt show. So plt image show imshow train images of 0. I'm kind of displaying the first image, and color map is gray. So let's run this. You can see this is kind of looking like a shoe, and I mean, you see that this is not very clear because the image is actually like a very small image which doesn't have like a lot of resolution. This is just like 28 into 28 pixel image, so it's not of like high clarity. Okay, so if you have a larger or a better resolution image, in that case you would probably see a better image here. So that's about it. And let's see what is the label for this. So we have this train images of 0 as this image, and let's see what is the corresponding label for that. So for that I'm calling train underscore label. So this is train underscore images, this is train underscore labels. This is 9. Okay, so this dataset basically contains 10 different classes, and this is the classes in order. First you have a t-shirt or top, and then you have a trouser, pullover, dress, coat, sandal, shirt, sneaker, bag, and ankle boot. So this ankle boot is the 9th index. So your index starts from 0 and you have all the way up to 9, which basically counts to 10 classes. And when it says 9, it's basically is referring to the ankle boot. So you can find this class names in online as well. So this is not like a big thing. Now let's do some other data processing work in order to kind of efficiently train our model. So the next step is normalizing the pixel values to be between 0 and 1. So these are the pixel values that we are looking at. So you can see the value is between 0 and 255. Normalizing is just kind of having the values in a specific range, and the value that we are going to have is between 0 and 1. For that, what you will be doing is you will divide each of this value by the maximum number. So here the maximum number is nothing but 255. So what would happen is we know that the minimum number that you would have is 0, right? So when I divide 0 by 255, all you get is 0, right? And when you divide 255 by 255, this is like simple math. We know that we will get 1. And let's say we take some value in between, some, let's say 120, and divided by 255, it's going to be between 0 and 1. So your value cannot be lesser than 0 and it cannot be more than 1. So this is the normalization that we are doing, and this is like a very important step, and it has its own advantages. So you actually can train your model without normalizing, but the thing is, right, when you have the pixel values or basically your data in a shorter range, your performance or the efficiency of the model is going to be better, because we know that our models use an optimization algorithms like, let's say, gradient descent, where it kind of tries to see how your loss is decreasing when you change a specific parameter value, right? So when you have the values between 0 and 1, the transition or the change in gradients, or basically your gradients change, is going to be standard in a uniform range. But when you have values as from, let's say, 0 to 255, it's a larger range, and this gradient change will be like very drastic in several steps, and this will also lead to a problem of the model going into a state of local optimum, where it tries to say that this is like the perfect parameters that I can choose from, but it's actually not. It's like, what's the model think? So that's what we call as the local optimum. So global optimum is the point where it's actually the best the model can perform, but local optimum are like kind of like the curves which are not as good as global optimum, but I mean, the model thinks that it's going to work well. So this normalization kind of reduces the risk of the model being stuck at those local optimum. So this might be a bit kind of hard to understand, but you will understand this once we start or continue our deep learning series. So they're like I'll explain you all these things in detail. So here what we are basically doing is, as we said, we are going to scale our training and test image pixel value by dividing it with 255. So I'm having this train images and test images. I'm having like two basically the train and test set, and dividing each of this by 255. So what will happen is you have 60,000 images in the training set, right? So maybe let's also see how many images that we have in the test set as well. So here I can say print test images. So I think it should contain 10,000 images or something, but let's see. Yeah, it contains 10,000 images. So this is like one data point, one numpy array of image. So we have to divide each element of each of this image by 255 in order to scale this, and that's what we will do. Okay, as we can see. So I'll run this, and probably I'll copy and run this again to see if this worked, right? So now you should see values between 0 and 1. So I mean, you will just see like float values between that range. Right, as you can see now the values has been changed. Okay, so the next step is reshaping this. So the let's say Keras and TensorFlow models requires your data to be 4-dimensional. Okay, so the first dimension here we have is basically the number of images present in your data set, and then you have the height and width information, which is 28 and 28 pixel, and the next information is your channel information, whether it is like a grayscale image or it is like a RGB image. If this is a RGB image, we would have said that 28, 28, 3, and this is a grayscale, which is a single channel. So when I say 3 channels, it's nothing but red, green and blue. When it's black and white or grayscale image, you just have grayscale channel, so which corresponds to this one channel. Okay, so train images, I'm reshaping this to train images dot reshape, train images dot shape of 0, 28, 28, 1, and test image also we are like kind of reshaping. This is basically the number of images you have in your data set, and 28, 28, 1. So here I'll say train images dot shape. Oh, I need to rescale it. Okay, so here you can see we have the 60,000 28 28, but we don't have this one. So I'll run this, and now let's copy this and run this again. Okay, so now you can see we have kind of added that channel information as well, which is like the main purpose of this code. I'll also print the shape of test images. So you have 10,000 28 28 1. Okay, so the next step is the important step that we are looking at, which is building our convolutional neural network. So I'll give you a basic explanation of the model here, but it's okay. Again, it's okay if you are not clear with all the layers that we are using. So we will understand in detail about different neural networks, like just an artificial neural network or a convolutional neural network, RNN, transformers, etc. Right? For now, you can just have a basic understanding, because the purpose of this video is just to get a overall picture of starting from data curation, training the model, processing it, and just deploying it as a Streamlit app and Dockerizing this, right? So we will dive deeper into all this data processing, model building, all of these things in a detailed way in our deep learning course. But here, let's just have like an high-level overview of what we are doing. Okay. So here we are creating a variable called as model. So model is equal to models.sequential. If you remember, we have imported this model from models, class from this TensorFlow.keras, right? So from this, I'm calling a method called as sequential. So this sequential is basically used to stack layers one top of the other. Just think about like stacking one plate on top of other. The only difference is that we are stacking the layers on one top of the other, and each layer kind of feeds the data or process information into the next layer. It's just like how our neurons are connected in our brain. So it's like a series of connection in this case, where we are stacking the layers. Okay, so this is like the base sequential model for this, and to this we are kind of adding the layers. So we are saying that model.add layers.convolutional 2D con 2D, which is basically a 2-dimensional convolutional layer, and we have this 32, right? This is basically what we call as kernels or filters. These filters are used to kind of detect several features in the image, like the shape it can recognize in the image, the edges of, let's say, the object present in the image, and so on. So this filters are basically like a matrix, and the shape that we are representing here is 3,3. So let's say you have a 28,28 pixel image, and it kind of scans through with this 3,3 kernel, and it tries to kind of do some convolutional operation in it, so that you kind of or let's say the model, this particular layer, kind of understand some features present in the image. And we are using an activation function of ReLU. As I said, we will discuss this more in detail in our course. And we have our rectified linear units activation function, which is like one of the widely used activation function. And then we have the input shape. So here we need to mention the input shape that we have. So you don't have to mention 60,000, just image the shape of each image that we are using, which is 28,28,1, where 1 stands for our grayscale. Next is max pooling layer. So max pooling, again, a two-dimensional layer, 2D. So this is used in order to reduce your spatial dimensions. So we have two-dimensional image, which is height and width of the image, right? So we need to kind of reduce the spatial information present in the image, so that it's easier for the model to recognize things from it or understand it better, right? So that's what we have. So first we have a convolutional layer with 32 filters, or you can also call this kernels, and then you have a max pooling layer, and then you have convolutional 2D with 64 kernels, and then again this is a 3,3 matrix, and then activation function is ReLU, right? So as you can see, first I've started with 32 filters, and then I've started with like 64 filters. So this is like one of the standard things to do, where you start with a smaller number of filters, so that it recognize some basic features. And once you move on to the deeper layers, you increase the kernels, so that the model can understand more complex and minute information present in the image, right? And again, it's not like you should always do that. You can also have like the same number of kernels. So here, if you can see, I have a third convolutional layer after this max pooling, and this has like 64 kernels, which is the same as this. You can also kind of, let's say, have 128 kernel and work on this when you have, like, let's say, a different data set that requires it, right? So again, the sizes matrix shape is the same, which is 3,3, and activation is ReLU. So here you can see I've used a convolutional layer and then a max pooling layer again. So this is like the first step of convolutional and max pooling layers. This is the second test. And here, if you can see, I just have like convolutional 2D layer alone. It's not that when you have a convolutional 2D you should always have max pooling layer and so on. So it's not necessary. Again, there's not like standard things to do, but again, right, you can just like add a max pooling layer as well, or you can skip it, so that's okay. Let's also later understand what's the purpose of having this kind of architecture and how this helps and so on. So this is a very basic CNN. So I've just like stick to basic information, just not to complicate things in the start. Okay, so this is like the convolutional base for our neural network, and then we add the top layer, which basically kind of classifies your image. So now we would have let's say a three-dimensional image processed with like all this image. Basically, like after the data has flown through all these layers, you will have a 3,3 shape array or a matrix. And before we pass on to the dense layers, we need to flatten it, so that it's kind of a vector is nothing but just like a single array, right? So that's what happens in your flatten. So it kind of flattens your array into a one-dimensional array. Okay, and then we add a dense layer, let's say a deep deeply connected layer, where all the neurons of the previous layer are connected to the next layer, and we have 64 units of like neurons here, and the activation is ReLU, right? And the final layer that we have over here is our the output layer or the top layer, which classify the image as the class. So here dense is equal to 10. So if you can see here, I haven't mentioned any activation. That means we are just going with the default activation function, which is linear, right? There are like different ways to use this activation function. So when you use a linear activation function, what will happen is you basically have 10 neurons. And the other important thing is, in the output layer, always use the number of classes that you have in your data set. In our case, we have 10 different classes, so I'm using 10. If you have 15, use 15 there. When you're using a linear activation function, right? So basically, let's say you have 10 neurons, and each neuron will output a value. So let's say the first value is 10, and the next value is 0.5, and let's say 15, and so on. So this goes on, where you have like 10 different values, and each of this would give you some values, right? So what your linear I mean your output layer with linear activation function will do is go through all these 10 outputs and choose the output that has the maximum number. So in this case, let's say this is, let's say, our third neuron, and this has 15 as the number, right? So this has the maximum value. So basically your third class will be 0, 1 and 2, which is your pullover, right? So this is how this would work. But when you have a softmax layer, what would happen is you would have 10 probability values that ranges between 0 and 1. So it will now look at the neuron that has the highest probability and say that that is the class that you're looking at. Again, in neural network, right, in a multi-class classification problem, we often use a softmax. Just for simplicity, I'm just going with the default activation, which is like linear in this case. You can also try with softmax and see how your model is working. You can basically just do some hyperparameter tuning with all these cases to see if you're kind of getting like a better performance. If you're, I mean, working with a binary classification, mostly we will use sigmoid, which is like good for binary classification problem, and softmax for, let's say, multi-class classification. So you can also try with that. So for now, I'm not going to change anything here. So I'll build my neural network. Next step is compiling the model. So compiling is just like making the model ready for training, where we say the optimizers that we have is Adam. So what optimizer will do is basically try to find the best parameters for our model. Okay, so basically your neural network will have like a set of parameters that it need to train on. When I say train, it just need to find the best parameter values for the neural network, and for that it kind of does this with this gradient descent kind of an algorithm or an optimizer, where it will like constantly have this gradients or change in this parameter values such that your loss function is decreasing. Here we are going to use one of the widely used optimizer called as Adam, and the loss function that we are using is tensorflow.keras losses.sparse categorical cross entropy. So sparse categorical cross entropy is used whenever you have the classes that are not one not encoded, right? So one not, I hope you know what a one not encoding is. So let's say that you have three class of images. So how we would represent that as 1, 0 and 0. This means class 1, and then you have 0, 1 and 0. So this is my second class, let's say, and my third class would be represented as 0, 0 and 1. So this is like a better way to kind of encode your classes or categorical variable. And whenever you're using one not encoded variables, you'll probably use like categorical cross entropy. So here we don't have one not encoded values, but just like numerical labels. I think we have printed this over here, as you can see, right? If this is one not encoded, right, this will basically contain an array with 10 different elements. All the elements will be 0 and the last element will be 1. So that is like a one not encoded. So in that cases, you can just use categorical cross entropy instead of sparse categorical cross entropy. And logic is, it's basically what I've explained you for this linear, right? So when you don't have the output in probabilities, we say from logic is equal to true. When it's false, it means that the output gives the value in the form of probability, and the metric it's going to train on is the accuracy. So I'll run this. Next step is model training. So we have this variable called as history, and for this variable we are calling this model.fit, where we are passing the train images and the training labels, epochs as 5, and the validation data will be test images and test labels. So the other thing that you can do is you can use this like as kind of like a final test data set, and you can split this training images as just like a validation data set. So what a validation data set does is at each epoch it will train on this training images, and it will also give you the evaluation on the validation set. So again, the one way to do this is split your training data as training and validation set, and then kind of like finally print the accuracy with the test images. Here I'm just using the test images as validation. Okay, just like a basic thing to do, but again, creating a validation split from your training image is also like a recommended one. So I'll run this. So this will train our 5 epochs. These are like smaller images, so this is not going to take a lot of time when you are running it on your GPU. But again, if it's running on a CPU, right, it's going to like take quite some time in a GPU environment. So that's one thing. I'll close this. You can see this like has a good accuracy of 82 percentage, which means like out of 100 images it can classify correctly for 82 images, and the validation accuracy is also like good. So here you have 82, 88, and you can see the accuracy is not like kind of going a bit above. It's just like just a mere 1% increase, and the validation accuracy also you can see. So there are like things like early stopping, where the, let's say you have 10 epochs, the training will stop before that 10 epochs. So it can even stop at 5 epochs when the model is not seeing a significant increase in the accuracy or the performance. That's also, maybe we can do it in a later use case, but here we are, let's not complicate things. Okay, so I've just gone with 5 epochs. You can also probably try to increase the epochs, but the problem is in some cases when the data is simple and you have like a lot of different epochs and a very complex model, it's highly likely that the model is going to overfit, where it can't generalize. So it performs well on your training data and it may not perform well on your test data, right? So that would happen. And next step is, yeah, so our training is done and I'm having this accuracy of 90, almost 92% in training, and validation accuracy of 90, which is a really good score. You can also improve this with better data pre-processing, or like having a better model architecture, or even you can use transfer learning, where you will use a pre-trained model with this specific data set. That would probably give you like even better results, so instead of building your model from scratch like this. So again, let's discuss about that later. So now we have the model evaluation, where we call this model.evaluate, passes test image and test labels. Verbose just like to give some information on like the basically just some informations like this. It's like nothing complex with this. So I'll run this one. So we are going to print the test accuracy. So we see the test loss for this dataset. Test dataset is 0.27 and the accuracy is 90%, which is basically the final accuracy. If you are, again, the better way would be to split the training to validation set and test it with test dataset. You can try that as well. Shouldn't be a big issue. So 0.90, which is basically 90%, and then you can plot the loss value and your accuracy. So if a model is trained well, that means your model's accuracy should increase over the epochs, and your loss function should decrease. Loss is basically the difference between your model's predicted value and the actual labels. Okay, so when your loss decreases, that means your model is performing well, so your model accuracy will increase. So the blue color line that you're seeing is like how your accuracy is changing over the 5 epochs that we have. So it's increasing. So there is like a good kind of increase from first epoch to the second epoch. So it starts from 0. That's why we have the numbers from 0 to 4. This we can kind of infer from here as well. So first it was in 82%, and then it was 88, and after that there was no significant increase. So that's what we are seeing here. First we have about 82, and in the second epoch we have about like 88, and it's kind of like a slight increase after that. Similarly with the validation as well. And the loss also, you can see because of this I mean a good increase in the second epoch. Here you can see the loss dropped drastically. Later it kind of dropped in a good way. For a test it didn't like drop that well. It's kind of like plateaued. So again, you can have a better model architecture and all of those things in order to get a better performance from the model. So the next step is, I'm going to save this model, this neural network, and I'm going to use or deploy this model as a Streamlit app, where the user can upload the image and get a prediction out of this. So you can just use a model.save trained fashion MNIST model.h5, which is like the usually used format. So this will save the file. You can see it in the directory. So this would be a smaller file, so you can just like basically download this from the Google Colab. And now let's move on to the Streamlit code that we have. Okay, right. So first maybe I'll explain you the code structure that we have. I mean, let's probably use this as like the standard folder structure in all the use cases that we are working on, so that we have like a better standard, right? So I would suggest you to work on PyCharm, so that you can access the terminals in a better way, and also you can use like a debugger in a better way, instead of like working on other, let's say, Jupyter notebooks or other basic IDEs. So PyCharm is like a good way, and even Visual Studio is good. The advantage of Visual Studio is you kind of can run notebooks in a better way as well. And here in PyCharm, right, in the community edition, which is a free version, you can't run notebooks. I think that's the case. Yeah, that's the thing. So but you can view it. So this is like the same notebook that I have showed you. I've created a folder, right? So that's the other thing. I would suggest you to use PyCharm again, but you can also use Visual Studio Code. That's like up to you. Okay, so here I have a folder called as this video record Jan 12, so the date on which I'm recording, and this is my project directory, and here I have my virtual environment v.venv, where all my libraries and Python packages will be stored. And I have an app directory where I have the trained model stored in a folder. So I've already trained this and I've saved this to the folder called as trained model. And then I have this config.2ml, credentials.2ml, and the Docker file. So these are required to deploy this Streamlit app as a Docker container. And then I have this main.py. These are like main.py is like a standard name. Docker file should always contain this name. So don't change like the names of this. But again, this main.py you can change, but I would recommend you to have the standard names for main.py and folder name as app. Okay, so this is a Streamlit code, and you also have requirements.txt. So these are the package versions that we have used for the Streamlit app, and these are the three libraries you need in order to run this. Basically your Pillow and OS are like inbuilt libraries, so you don't have to mention that in your requirement, so that will cause an issue. Just mention Streamlit, TensorFlow, and NumPy. It's better if you have used like this version as well, so no issues. And then yeah, that's what's present in your app directory. So we'll kind of transport all these into the Docker image and we will build it. So it's better in that way. And these are the things that we have used in order to train our model. So I have a folder called as model training notebook, where I've saved this notebook that I have showed you. And the test images, I have just like few images that I'm going to kind of test. So we have this ankle boot thing, and I also have this is like a pullover, and we also have like another ankle boot. So we will like test this once we deploy the Streamlit app, right? So you have app folder where you have your Streamlit code, Docker files, and so on, and you have this model training notebook. You have this test image. I'll give this same code structure in my GitHub repository as well. You can probably use that. Okay, so let's go through the Streamlit app code and understand what we are doing here. Okay, so first I'm importing a Streamlit library, which is used to create the web app for our image classification. Then I'm importing TensorFlow in order to load our model and getting a prediction out of this, and Pillow library in order to process the image. So here we will be the user will be uploading let's say a JPG or a PNG image, right? So that image needs to be processed. So further we'll be using Pillow library, and then we are importing NumPy and OS. In order to OS is just to use some OS features of reading and writing files and so on. And now this is like an interesting thing to do. When you run a Streamlit app code, right, it kind of doesn't run in this directory that you are specifying. It kind of runs in a different directory, so I'm not very sure about that. I think it runs on your users directory. So when I just mention this trained model of trained fashion, so ideally what should happen is, right, this is this main.py is running, and when I say train model of train fashion MNIST model, they should pick the model. But what would happen is the working directory will be different. So I need to give the full path of this trained model. So you can basically copy the full path of this, but the better way would be to get this from the script. So when I say os.path.directory name, os.absolute path of this file, what this will do is this will get the absolute full path of the main.py file, the current file where this line is present. So this will get this directory. So I'm putting that directory here, which is this video record directory is what I will get from this working directory. And then I'm calling this trained model and trained fashion MNIST. So this is, I mean, you can again paste the entire path manually, but I don't want to kind of hard code my path here, so that when I put this in a Docker file, I don't want that to happen, right? In your Docker file, you don't have this C uses your particular name of your system and all those things. It's better to have this in this way, where you call this working directory from the script itself. So we are concatenating, so we are having this F replacing this working directory with this trained model underscore MNIST fashion, just the model that we have trained. And then we are going to load the model. This is just the path of the model, and to load this we are calling model is equal to tensorflow.keras.models load model of model path. Okay, and these are the class names that I have showed you. We have 10 different classes of t-shirt, tops, trousers, and so on. And the next step is pre-processing the image. So again, you have a JPG image. So in the training, we have pre-processed it, like the data has been already converted to NumPy array, and it is a grayscale image, and again the shape is 28,28, right? So we have to do all those things along with the normalizing. So what we are first doing is we call this function once the user uploads the image, open it with image module from Pillow, and resize it with 28,28, and the user, this code will work if you upload any image of, image of any shape, right? Even if it's like 150, 150 image, because we are resizing it in this step. And even if this will work if you are uploading a colored image, because in this image.convert of L, we are converting to grayscale. L basically stands for luminescence, and basically represents a grayscale image in pillow, right? So even if you upload a RGB image of different sizes, it would work. Again, I can't recommend you if it would like predict it correctly, because the data set that we have used is a very basic one, and I mean, it's not a high resolution, right? And so if you put an image of different resolution, it's probably going to give you like wrong classification, but the code won't break. You will still get an output of this. So that's why we have this conversion. And then we are having this np.array of image. We're making sure that we are converting this to numpy array and dividing it by 255, just the same way that we add in the training phase, where we have scaled the pixel value between 0 and 1, and then we are reshaping this to 1,28,1. So this is just to tell the model that I'm just predicting it for one image. So this is like the batch number. So when I say one, that the batch is going to just contain one image and just give the prediction for one image. You're not passing like 10 images and getting like prediction for it. And finally it will return this numpy array that in the shape that the model expects, the trained model expects. Okay, if you're working with a different shape, you would probably change this resize and these things, and other things probably won't change. And then we are creating a title for our Streamlit app as fashion item classifier, and we are creating a file uploader, st.file uploader, writing a text as upload an image, and type can be jpg, jpeg or png. So these are the types that we are allowing. And once the user has uploaded the image, right, in that case only the below code will run. Okay, so you can see if uploaded image is not none, initially the variable will have none as the value because the user hasn't uploaded anything. So this code won't be executed, this if condition won't be satisfied. But once they have uploaded the image, this none will change. So this is not none anymore. Now we have this image.open of uploaded image. So basically we are opening this uploaded image using pillow again. So this uploaded image is basically what the user has kind of uploaded. And here I'm creating two columns. This is just a view of the Streamlit app, so that you have once this all this contents that we have over here will be in the first column or first view, and the other things will be in the second column. Just to, these are like the structure of the web app that we are looking at. So column 1 comma column 2 is equal to st streamlit.columns 2. Here you need to mention the number of columns that you have, and column 1 column 2 the corresponding columns. So you can call with column 1 resized image is equal to image.resize. Now what I'm trying to do is, once the user uploads the image, I want to display the image on the left side, and I need to kind of enlarge it. So I don't want to display it in 28,28 because it's going to be very small. So whatever the size of or the shape of the image the user has uploaded, I'm going to reshape it to 100,100. Okay, so that the image is large and the user can see it well. And st.image will basically display your pillow processed image, right? So that's what we have. So on the left we'll display the image, and the next is we are going to have classification button once the user has kind of uploaded it. And once this button called as classify is kind of clicked, we process this image by calling this pre-process image function. So this will do all those numpy array conversion, grayscale, normalizing, and all this reshaping and all those. So once this has been processed, we are going to predict it. So model.predict of image array. So as I said, your 10 neurons in the output layer will give you 10 different values, and the final it basically looks for the index that has the higher value. So that's what this np.argmax will do. So when you call this np.argmax, right, you pass an array to it, and it will return the index of the element that is like the highest number in that array itself. So that's what argmax is, and that's the index that we are predicting. So once we have this, we put that index to this classes list that we have. So let's say the ninth index as like the largest value, that means it says the predicted one is ankle boot. So we kind of pass this index to this list and say that it's a ankle boot, and finally say that st.success, the prediction is this one, this ankle boot, or like whatever it is, right? So now let's run our Streamlit app. I'll clear this terminal. Okay, so why my terminal is not running? Okay, so first, in order to install the libraries, right, you can just do a pip install r app/requirements.exe, because this requirements.txt is not in my default project directory, it's present in my app, right? So I have to say pip install r app slash requirement.txt. App is the folder that we are working on. So I've already installed the library, so this shouldn't give me any issues. I will just clear my terminal. Now to run the Streamlit app, say Streamlit run app slash main.py. So as you can see, I'm in this directory. If you're not in this directory, use the cd command and navigate to the project directory where you have this app folder and run the streamlit run app slash main.py. So this will open my web app that we have. So this will load the model and do all those things necessary, right? So here we are going to browse the files. I've just have some test files and we can probably test this, right? So as you can see, this is the column that we have mentioned. So this is column 1, this is column 2. On the left side we are seeing that image, and then we have the classify image. When I click the classify, it's going to say the prediction is ankle boot. So this is what we have done, and probably I have this st.write to show you how the actual prediction will be looking like. So I'll open this, browse the file, and I'll upload this pullover image and do a classify. This is how the prediction is going to be. So you have this values you can see, right? So we just need to look at like what's the maximum number is. So you have all the negative numbers, but this one has 8.63, this one has 0. So this is a larger number, so the index should be 0, 1 and 2. So 2 would be the output that you would get in np.argmax, right? And this 2 will be called here, so it will be 0, 1 and 2, which is pullover. So that's how this prediction is coming here. So you can uncomment this in order to see this, but I'll just comment it for now. So I'm just converting this result to a string and writing this on the Streamlit. So I can refresh this to so that the updated code is saved. And I have another image. So this is also an ankle boot. I'll classify this. I have this ankle boot. Some of the image may give you like a wrong classification. That's okay. You can just try it with a better model, transfer linear, all those things to get like accurate predictions. So this is a Streamlit app. Now we have deployed our image classification system where the user can upload the image and get the prediction out of this. Now the next interesting thing that we are going to do is build a Docker image for this and run a Docker container from this, so that it's kind of like in a better standards, right? So that you can share this instead of sharing the requirements file, the code and all that. You can just send it as a package that has like all the dependent resources and other things. So I've already uploaded a video on dockerizing the Streamlit app. You can refer to this, but I'll quickly show you what we have. So this config.2yaml and credentials.2yaml are like standard things. You can just copy this. These are like some configuration for a Streamlit app. You can just use the same files. You don't have to change anything. And Docker file also won't change even if you're working on a different Streamlit app, right? You don't have to change anything here except for the name of the Python file. But I would suggest you always to use main.py file. So Docker file again it's just like the set of instruction that we need to say to build the Docker image. So first we are saying that I want Python version of 3.10 slim, and I'm saying copy dot slash app. This means this app is not this directory. This app is present in your Docker image. In your Docker image or your Docker container, there will be an app directory. So when I say dot, I'm mentioning the directory of my Docker file. So when I say this will copy all the contents present in the folder where my Docker file is present. Say for example, Docker file is present in this app directory. So I will copy all these files from this directory and save it to the app directory present in my Docker container, because I need all this in order to run my Streamlit app. And I'm changing the working directory in my Docker container as /app. And then I'm running pip install underscore requirements.txt. Here you don't have to mention app requirements.txt because we are already in the app directory, so that's not required. And we are mentioning what's the port on which the Streamlit app is going to run. So you can use expose 80 and make dir. We are going to, these are like standard things in order to copy your config.2yaml and credentials.2yaml, creating a .streamlit folder, creating this directory, copying these two files to this directory, again cp, just like copying this and creating the command for this, just like the Streamlit run that we did. So we are calling the entry point as Streamlit run main.py, just the command that we did, but this runs on the Docker container, right? So this is the Docker file. So we have seen that first we need to app this Docker file and then build the Docker image and then run the Docker container. So I'm going to go into the app directory. So I'm going to say cd space app. Right now I'm in this directory. So now I can say sudo. If you're working on Windows, make sure you are running this PyCharm or your terminal as administrator. If you're working on Linux, you can use the sudo command to run the commands as administrator. So I'll say sudo docker build. And again, for uh, Linux users, you can use Docker from the terminal. In the Windows as well, you can do it. And in Windows or Mac, you also have this Docker desktop that kind of lets you easily manage your images and containers. So you need to install Docker desktop and start your Docker engine and then like work on it. I'll also give you the link where I've explained all these things in detail in a basic way to kind of Dockerize the Streamlit app. You can refer that as well. So here I'll say basically your Docker should be running before that. So I'll do that as well. I'll say cd this thing. So this will go to my home directory. Now I'll say sudo system ctl start Docker. So this will start my Docker engine. So I'll give my password. Okay, now I'll close this. My Docker will be running now. I'll say sudo docker build t. I'm tagging a name. I'll call this as fashion MNIST classifier app, and I'll call this version as v1.0. Okay, so sudo docker build -t fashion MNIST classifier. This is the name of the image. So I'm giving the password as I'm running as the administrator. Okay, so there is some image sudo docker build t. Okay, so I should specify other things. So sudo docker build -t fashion MNIST space dot is basically again the location of your Docker file. Here I'm in the app directory, so it's I can just say this dot. If there is another folder and within that if Docker file is present, I need to give that directory name, subdirectory name. So now I'll run this. So this is creating my Docker image now. So you can see all the steps running that I mentioned here. First is getting Python version. That should be happening somewhere here. Yeah, so Python 3.10 slim, and then it does this copying, working directory, all these things. So this has built my Docker image. So I've already done this. So this doesn't take me like much time. So for you it may take like, let's say, a couple of minutes maybe, depending on the code that you have. And now we can see the Docker images that's present in your system by calling sudo docker images. Again, in the Docker desktop is a graphic user interface version of Docker. You can see it there as well. I'd say 6 hours ago. Sudo docker images fashion MNIST classifier app. Okay, so now I'll say now we are going to create this Docker container. So for that you can say sudo docker run -p 80:80. This is to specify, so basically map the port that we have created, which is 80, and here I can say you can paste this name fashion MNIST classifier app along with the tag, or can just copy the image ID and paste it here. So this will start the Docker container, and this is the link from which you can access it. And again, Linux and Mac you can use this URL, but for Windows you can, this may not work. Just go to the localhost URL and there you will see this code running. Okay, so yeah, if you just go to this link, probably it will give you an error. This is my local thing. I've stopped it, but this is like now running from a Docker container. You can see the URL as well here. Now I'll try to upload this image and get a prediction. You can see now we have the Streamlit app, but now this is running as a Docker container, which has all those Python libraries and all this package. And yeah, so this is how we can build a Docker container like this. I'll stop this. If you can see all the Docker containers that you have built with sudo docker psa. If you just say ps, it will give you active containers, but you have stopped it. In order to see all the active stopped containers as well, you can see -a. So we have created like 13 seconds ago, and yeah, created 59 seconds and so on. So this is my image ID. So you can delete this specific container, but let's say you have 10 containers and you want to delete all those things. Don't delete it if you're going to present it, demo it, or let's say you're going to work on it. But I don't want this anymore, so I'll just say sudo docker container prune. So this will delete all the containers that I have. It's asked for a confirmation. Let's you can see the space that it has left, and yeah, sudo psa. Now you don't have anything here. So you can also delete your Docker images with, let's say, sudo docker RMA. So I'm not going to use this Docker image anymore. So I'll just delete this as sudo docker RMIF. Paste your image ID, which is this. Again, the other interesting thing that you can do is push this Docker image to Docker Hub. It's just like GitHub for Docker images. So that someone can like kind of pull it and they can build a Docker container out of this. So that's possible as well. Okay. So that's it for this. We'll quickly give you the overview of what we have done from the start. The first thing that we have done is train our neural network. We have used a basic model which is fashion MNIST. We are seeding the libraries in order to get reproducible results, importing the liquid libraries, loading the data set and all those basic things, checking the data types, other things and so on. And then we are doing a bit of processing where we kind of like normalize the images to be between the scale of 0 and 1, and then we are reshaping it for the model to kind of like I mean it's basically required for the model to have this 4-dimensional array, and then we are creating the architecture for our convolutional neural network, compiling it with optimizers, losses and other things, and then we are training the model, and then we are evaluating it with the accuracy and so on, plotting and finally saving this. The next step is process or basically creating your main.py file, which is your Streamlit app. We have this pre-process function that gets any image of any shape or channels and process it so that our model can handle it, right? And once we process it, once the user has uploaded it and classified it, click the classify button. We are pre-processing this, predicting it and displaying the prediction. And finally, once we have tested our app, we are creating this Docker file which has a standard instructions in order to run this Streamlit app, and finally we kind of like deployed it with Docker build and Docker run, right? And this is now still as in a local environment, right? If you want to share this, what you can do is you can deploy this Docker container with Azure and AWS in order to, so that these are kind of remote things, so anyone can access it once you deploy these Docker containers. So I hope everyone is clear until this part, and that's it from my side, and I'll see you in the next upload. Thanks for watching. Hello everyone, I'm Siddharthan. This is the 7th deep learning project video in my YouTube channel, and in this video let's understand how we can build a plant disease prediction system where we will be training a convolutional neural network for image classification. Once we have trained this model, we will build a simple Streamlit web app where the user can upload a plant image and predict with this trained model about what that particular plant disease is. Once we have this Streamlit app, we will Dockerize this Streamlit app and deploy it as a Docker container for better standards. So before going into the workflow for this use case, I'll just quickly show you how this Streamlit web app looks like. So this is the page of our Streamlit web app where the user can browse and paste the files from their local system, and I have some basic test files for this. The first one is like blueberry LT. So if the model is predicting correctly, once I click this classify button, it should say it is like a blueberry LT one. So just for reference, I have named the file with the same class name, which is blueberry LT, and this is like a test image. So I'll classify this. And here we are seeing the prediction as blueberry LT. So I'll also paste another image which is for this potato early blight. So we will also display this image here, as you can see, and we can classify it. So this is how you would get a prediction. So this is like the end product of what we are trying to build. And before getting into the coding aspects, let's quickly understand the workflow for this use case. The first thing that we will be doing is data curation. So we know that this is an image classification model that we are going to build. So we need proper image data for this. And in this case, we have a Kaggle dataset that we will be using. So I'll also show you how you can get the Kaggle JSON file which basically contains your Kaggle account credentials, and kind of load it in Python and get this dataset through a API. Okay, so I will be working on Google Collaboratory, so you can try that, or even you can work on your Jupyter notebook as well. So once we have our image dataset, the next step will be data processing. So in this data processing step, we will work with a image data generator class from TensorFlow, where we will kind of load this image data from the directory with appropriate classes and make it kind of suitable for the neural network to learn from it. So here we will understand like quite good amount of data processing steps. So once the data processing step is done, we will split our data set into training data and test data. So this is actually connected to the data processing step, where we will kind of build a pipeline for training data generator, and other one is for like validation generator. So this, both of these kind of will be interlinked with the image data generator method that we will be using. So once we have our training data and test data, we will build our convolutional neural network with appropriate convolutional layers and all the dense layer required. And once we train this model, we will evaluate and make sure that it is like working well and it has like a decent accuracy. So once all these are done, we will save this model as a file. And once this model has been saved, we can kind of build a Streamlit web app around this, where we will kind of export this trained file and load it in the Streamlit web app Python script, where again the one that I've showed you, where the user can upload an image and get a prediction. So once all these are done, the next step is dockerizing this. So the first step of dockerizing this Streamlit web app is creating a Docker file that has the list of instructions to build a Docker image. So once we have this Docker file, we will build a Docker image, and once the Docker image has been built, we will kind of create Docker containers out of this. So even if you want, you can kind of push this to some Docker repository like Docker Hub, or you can probably put it on Azure or AWS like container registries. So but we won't be discussing that. I've already made videos on that. So in this video, let's just build this Streamlit app and kind of build this Docker images. So for the first step, I'll show you how to train this model and kind of process this data. And this is the dataset link. So I'll give this link in this video description, or probably I'll also give you this repository that I have created. So I'll also give the link of that dataset, but you actually don't need it. But if you want to go through about the dataset, you can go through this, because I'll be using the API command that we have over here. So we will directly import this dataset in the Google Collaboratory environment that we are working on. So the first step is make sure that you are connecting to a GPU environment so that your training happens quickly. So I'll connect my system, so you can see the connection status over here. And the first thing that you need is, in order to load this data from Kaggle, you need a kaggle.json file. Again, as I said, it is basically the file that contains the credentials for your Kaggle account that lets you use these Kaggle APIs in order to import your data. So in order to get that, what you can do is make sure that you have signed up in Kaggle, and also you need to verify your mail ID and phone number. So in some cases the APIs are not working if you are like not kind of verifying your credentials properly in Kaggle account. So make sure that you have done that properly. And in the top right corner, you will see this account icon. So you can go there and go to this profile section. Yeah, so profile, probably I think you can go to settings, and then you will have this account section. Yeah, right. So go to the top right corner, go to settings, and this will open this page. And here in this API section, you will see this API section where we have this create new token. So give this, and this will download a kaggle.json file. So I have already downloaded my JSON file. So once that is done, right, so you need to upload this file over here. So come to these files and upload your kaggle.json. So I have this in my downloads. So I'll scroll down and I'll upload this kaggle.json file. So this basically contains two key value pairs. One is your Kaggle account username, and other one is your like KPI key. So previously we would have configured this file, but there is another easy way to do this, where we will just kind of load these credentials into environment variables, and from there Kaggle can pick it up. Okay, so let's understand the next step. So the first thing that I'm doing is seeding the libraries that we have. So we have this random library, NumPy library, and I'm importing this TensorFlow library. So all these are like pre-installed in Google Collaboratory. And if you're working on Jupyter Notebook on your local PC, right, so make sure that you have installed all these libraries with pip install or with Conda Navigator. You can do with this. And the first step is I'm seeding this again for reproducibility. This is because in a lot of the steps that we are working on, internally some random process happens. So think about it as, let's say we are building a neural network, and it has to train, right? So when a neural network trains, it randomly kind of generates its parameter value, which is its initial value. So there is some kind of randomness involved in it. So each time you run this code, each time it may give you slightly different results. So if you don't want that, we need to kind of set all these random process in such a way that each time I mention this seed, the same output is what I'm getting. So this is just to make sure that when I'm doing some experiments, all the results that I'm getting are kind of consistent and it is not varying. So that's why we have this seed. So this is just similar to the random state that we have in train test bed. So you can kind of think about that, where if you have a same random state, your data is going to be split in the same way, right? So it's kind of similar to that. First, we are importing this random library and seeding it with the value 0. And then I am importing this NumPy library and again seeding it with 0. And TensorFlow is also I'm seeding it with 0. So if you are seeding it with the same values, you will get like the same results that I am getting as well, right? So I'll run this cell. The next step is importing the required dependencies. So I have this OS library in order to access some files, and I have this JSON library in order to load my kaggle.json file. And once we call this Kaggle API, we will get the dataset in a zip file and we need to export it. Sorry, we need to extract it. And for this, we'll be using this zip file class in the zip file library. So this is also like pre-installed, so you don't have to do that. Next one is Pillow library is used to do some image processing works. And then we have, of course, the main NumPy library, matplotlib, in order to plot some results and the image. Again, MP image, matplotlib.image is used to kind of load and kind of display an image. And then we have tensorflow.keras.preprocessing.image. We have this image data generator, and this is like the data pipelines that we will set for training data and testing data. And then finally we have from tensorflow.keras, we have this layers and models. So layers is basically used to have all the layers such as convolutional layers, flattening, and the dense layers that we need for a neural network. And models is basically we will import our sequential from these models. So these are the required dependencies. So I'll run this. Next step is data curation. So make sure that you have uploaded your kaggle.json file that you got from here. And the next step is getting this Kaggle API command. So come back to this dataset link. Now you can run this pip install in your local Jupyter to make sure that Kaggle library is installed. Again, this is pre-installed in Google Collaboratory, so you don't have to worry about that. Next step is I'm opening this kaggle.json file with a JSON library, json.load open kaggle.json, and I'm storing it in a dictionary called as Kaggle credentials. So this will basically create a dictionary, and I'm storing it in this variable called as Kaggle credentials. So this kaggle.json contains two key value pairs. One is username and the other one is key. So that we are storing it as Kaggle username and Kaggle key in our environment variables. So I mean, the easy way would be to kind of copy the username and key and paste it here, but that's not like a good standard because you don't want your passwords or your API keys to be present explicitly in your code. So what we can do is kind of have a file like this and then load it in our environment variables, which is like a more standard way. So that you can probably like share your code without like you don't have to share those username and passwords for your account. So that's why we use this. So I'll run this Kaggle credentials thing and I'll run this where we are kind of setting up the environment variables with the credentials. This is the API command. So I'll go here. You can see these options in this dataset page. So you can go to these options and copy this API command. So this is the command that I've pasted here. Make sure that you are putting exclamatory mark, so because this is like kind of running as a command, so you just have to run this. So this is the same command, so I'll run this. So this will basically download a zip file and it will store it in our files. So again, you can do this in your local system as well in Jupyter Notebook. So you can see that the total size is about 2.04 gigahertz and it's kind of downloading it. So once it's done, right, I can run this ls, which basically lists all the files in your working directory to make sure that our data set is present, right? So this has downloaded it. So this is our kaggle.json file. This is the sample data is like the default folder that you have in Google Colab, and this plant village dataset.zip is the file that we need. So you can also see this here. So I've pasted this file name here. So if you want, you can also paste like the complete path of this file. So we have this with zip file, the name of the file, and we are reading it as the zip ref, and we are extracting the entire content of this zip file. So this will extract and this will also be saved in this working directory. So you can see here we have the folder called as plant village dataset. Okay, so probably let's wait for this file to be extracted. So this is the base directory where we have this plant village dataset, as you can see here, and this as other subdirectories, right? So this as like a folder called as segmented, color, and grayscale. So basically grayscale contains all these three subfolders contains the same dataset, same images, but the difference is all the image files in this grayscale folder are present in grayscale, black and white images, and color are RGB images, and the segmented ones kind of doesn't have any background, so it just have the leaf images that we'll be working on. So for our use case, we'll be working on colored images. If you want, you can also probably use grayscale. The only reason that I'm going with color is with this plant infection, right? It can be a factor that the color that we are seeing in the image may kind of give the model an idea of this is what that particular disease is. So that's the reason. So you can see this over here. So I'll expand this plant village dataset. So here we are seeing this color, grayscale, and segmented. So I'll go ahead and again open this, and you can see all the subfolders again, and these are the individual diseases that we will predict. So these are basically the class names that are present as individual subfolders within this color, right? So we won't be using this grayscale and segmented for now, but you can try it out with these set of images as well. So in this color, you can see again all these individual classes. If I open this, I will see like all the images that's kind of present here. So I can double click here to open this images, so you can see the image, sorry, the leaf image with some dots, right? So I'll close this. Probably I'll open the one apple with healthy images. So we will also need to understand how many classes are present within this folder. So you can see here we don't have any dots or kind of some markings that suggest that some infection is present, right? So this is for apple healthy. So similarly, we have for different plant and different diseases of those plants, right? So this is about this data set. So I'll probably collapse this for now. So that's what I wanted to see. First, I'm printing the basically the subdirectories in this plant village dataset, and then I'm printing the length of segmented, basically to see how many subfolders are there in each of this, right? So I'll run this one, right? So you can see this is the output of the first line, which is how many, or basically what are all the subdirectories in this plant village dataset, and this we already know. So it has grayscale, segmented, and color. Now I want to know what are all the number of directories, subdirectories that we have in the segmented, color, and grayscale. So we are basically this os.list directory, right? So this will basically return you a list that contains all the subdirectories of a particular directory. So if I call this os.list directory of this color, right? So it will kind of get all the names of the subdirectories in this color folder and create a list out of this, right? And I'm printing the length of that particular list, and I'm printing the first 5 names of that list. So I'll run this. So here you can see it says 38. That means we have 38 different diseases. So that's belonging to different plants like apple, tomato, potato, and so on, right? So similarly for grayscale and segmented, we have like these many numbers. So that's what I have printed here. So the number of classes that we have over here is 38. So it's basically a multi-class classification problem where we have like basically more than 2 classes, right? And as I said, this I'm just printing just to see like in this grape lt, right, how many files, individual files are there. So we know that these are all the class folders, and within each of these class folders, right, so we have individual images. So I'll run this. So this particular folder contains 423 images, and these are all the names of these images, right? So I didn't check like the individual numbers of all these folders. Probably you can do like check for some of these folders to make sure that the data is like evenly distributed and so on, right? So that is the next step. So these are the number of images. Now let's take this color folder and try to do some pre-processing out of this. So I'm creating a variable called as base directory, and I'm passing the path of this dataset that we have, which is plant village dataset / color, right? This is what we'll be using later. The next step is I just want to, let's say, plot and see how this image is looking like. So I've kind of chosen an image from this folder, and I'm going to do this. You can also like go through this folder and print like some other image as well. So this is the particular image that I'm taking in this image path. And we have this mpimg, right, that we have imported from matplotlib .image as mpimg. So using that we are going to plot it. So we know that this is a colored image, so we will do that, and we will also check what's the shape of this image. And then we are like showing this image and saying axis is off. So if you don't do that, right, so you will see that pixel number is the axis number, so I don't want that, so I'm turning off these axes and saying plt dot show. So before that I'll run this as well. So this base directory we will use a bit later. So you can see the image. So this is the image, and we see that the size, the shape is 256, 256, and 3. So I'm sure that all the images are of like this same shape. So that's other thing, right? So you need to make sure that all the training images and the test images that you're working on are of the same shape. So you can't have images of different shape and train a model. So this has to be uniform. So yeah, you, if you want, you can again print some other image and see how this looks like. And this 3 represents, it's a colored image, right, because this is basically your channel information. So 3 means we have 3 channels that are red, green, and blue, which are the RGB channels. And if you have grayscale, you wouldn't see any value here. That means there is one channel which is black and white, right? The basically it's the intensity of your white color, where in this case it's like for colored image you have like 3 matrices, where the first matrix should corresponds to the intensity of red color, and the next let's say green matrix is like the intensity of green, and similarly you have the blue intensity value. And when you combine all this, you would like get all the colors that you have. So that's like the idea behind the RGB image. And then we have this image parameters. So I'm going to resize all these images to 224 comma 224, basically the height as 224 pixel and your width as 224 pixel, because this is one of the widely used parameter. That's because like your image is basically like a bit large enough to capture all the features, and it's also not like that big, so that it's also not memory wise, it's not like that intensive. So this is like a usual kind of size that we can go with, but again it's not bad if you want to go with 256 comma 256, but make sure that you use that here, so that even if some images are of different shape, right, so we will resize this later. So that's the purpose basically. And then we have this image size and the batch size over here, and then we have this data generator. So for this data generator we will be using this image data generator, so that we have imported from TensorFlow Keras preprocessing.image data generator. And here I'm specifying that my rescale is equal to 1 comma 255, right? So the purpose here is you can kind of print this particular image values, or you can basically load it as a numpy array and see those values. Probably I can do it with this itself. So I'll show you, and I'll print this image. So these are all the pixel, basically the intensity values. So you can see the values are 179, 173, 79, so on. So this value ranges from 0 to 255, which is basically those intensity values. For grayscale also it's same. 0 means it's black, white, 255 means it's like highest intensity, which is basically your white color. Similarly, you have all these values for your RGB channels individually as well, right? So your range of values starts from 0, and it's kind of like ends with 255. So you can kind of train your neural network with this particular values as well, but it's not that good, because what we usually do is we rescale this in such a way that all the values are between 0 and 1. So by that way, right, so the range that you're working on is pretty less, so it's memory wise it's like less intensive again, and also it helps your model to converge kind of quickly. So we kind of used stochastic gradient kind of optimizer, right? And if you don't kind of rescale this to this 0 1 range, what would happen is that some pixel values are of like in a higher range of hundreds, and some pixel values are in the range of, let's say, 10 and 20s and so on. And at each iteration your gradient would change, which is basically your loss function with respect to the weights and parameters that you're considering. So if the range is more, then the change of these gradients are not so smooth. So what would happen is like your model may not have like a smooth performance, or basically your optimizer may not work smoothly, and it may not like converge at the global minimum. So you would kind of stuck in some local minimum, and there are like a lot of disadvantages there. So we would like kind of rescale this value, or what we call this as basically like normalization, where we are normalizing the values between 0 and 1. So there are like more things to it, which we will probably discuss more in detail when we kind of continue our deep learning series. But for now, we can just have this idea of it's basically better when you have this normalized images where the pixel values are between 0 and 1, right? So that's what we are mentioning in this image data generator as rescale of 1 divided by 255 and validation split of 0.2. So what I'm doing here is I'm reserving some image for validation, or basically for my test data. So when I have this training data generator and test data generator, 80% of images will be kind of considered as training image, and 20% will be considered for testing image, just like your train test split, right? And the other thing is you can do this separately as well. So here we are kind of building a pipeline and kind of working with it with a batch wise way. The other way is you can kind of write a for loop and load all these images individually, resize it, apply this rescaling and so on. So you can do that as well. But what would happen is in the way where we are having a for loop, right, all these images will be loaded together in your memory, and that will like kind of probably crash your collab session, or it's not ideal, right? Because what this data generator do is it will process your images in batch so that you don't have that many number of images at a moment in your memory, in your RAM. So it kind of works more efficiently with your memory as well. So that's the other thing. So considering your memory intensity and the workload on your CPU and memory is like very crucial when you're working with the deep learning as well. So that's the other thing that we need to consider. So in this case, we are just like mentioning the rescale value. So where we are just dividing it by with the maximum value, right? So what would happen is the max value is 255. So when you divide 250 by 255, you would get 1. And when you divide the lower value, which is 0 by 255, you will get 0. So all the values will lie in between. So the end result is that all the pixel value between 0 and 255. So that's the idea. And there are like other things to this. We are just doing two things, right? There are other things such as data augmentation, where we can augment our training data. So we usually don't augment our test data. So data augmentation is just to kind of add like more number of training data points, and this is also helpful to make sure that your model is not overfitting. So what would basically happen in data augmentation is that once we have an image, we kind of flip it, rotate it, so that it's kind of like add more to your training data and kind of generalize your model so that it doesn't overfit. So if you want, you can basically like do those as well. So you have like kind of parameters that you can mention in order to say that I want to rotate this images by this degree. So this will basically again increase your training data. So this is my base data generator, so that I'm storing it as in this data gen variable, and then I have this train data generator and validation generator. So these are all the things that would happen in my training generator, and these are all the things that should happen in my validation generator. So I'm calling this data gen instance. So this data gen is an instance of this image data generator, which has this parameters of rescaling and validation. So I'm calling this flow from directory. The other interesting and very useful technique about this, right, you don't have to kind of say that these are all the class names, this is how my, or basically you don't have to kind of label your images. What this will do is this flow from directory thing that we have, right? So this will recognize that your data is present in these subfolders and all these are individual classes. So all this like will kind of pick it will pick it up from this flow from directory thing. So all the labels are kind of like properly passed on to the model, like after applying this one not encoding and all these things. So you don't have to worry about kind of having your your target variable y and all those things. So your x and y, all these things will be splitted in appropriate way required for the model. So this is basically like a better efficient way to kind of process your data in pipelines. So you have this data gen flow from directory, and this is where we are passing our base directory, which is our plant village dataset color, right? So this is where why we have this base directory. So you can do this with any dataset, but make sure that you have a main directory, and within that main directory you have like all the classes kind of in a folder, right? So you have all the images. Now what would happen ideally in this case is, right, so you have all the images. All these images will be tagged to the class apple underscore apple scap. So similarly, all the images in this black rod will have a label as apple black rod and so on. So and then you can extract the label names from this generator as well. So that will also will be doing that, we can see later. So we are passing this base directory that contains all the subdirectories of classes and the images for that. And then we are mentioning the target size as image size. This image size is the target size that we have mentioned, which is 224. So when you have this image size comma image, it's basically that saying that I want 224 comma 224 as my height and width. So that's what we are seeing here. So your resizing will happen here. So even if you have some other shape, right, so it will be resized in such a way that all the images are of this same shape. And here I'm mentioning the batch size. So batch size is another crucial thing. You can kind of like increase this batch size if you have access to a larger memory, larger RAM. So this is this 32 is nothing but we kind of train our neural network by passing the images in batch, and this 32 basically represent that each batch has 32 images. And once kind of the model looks at all the images in this batch, right, after that it will kind of update its parameter, so your optimizers would work. So this is like the importance of batch. Again, increasing your batch number would speed up the process of training, but again it's like a memory intensive process, so make sure that you have more RAM if you are kind of increasing this batch size. So you can kind of do some trial and error to see that what's the proper size, batch size for your data set and for your machine. So that's okay, you don't have to go with the number that I'm mentioning here, right? So that's the other thing. So we usually go with 32 64, just multiply it by 2. 32 64, 128, 256. So these are some of the batch sizes that we would kind of work with. So that's what we have over here, and we are saying that subset is equal to training. So when I say subset is training, it will kind of look at the images that we kind of research for training. So when you say validation split of 0.2, which is 20%, 80% is reserved for training. So that's what will be flowing to the train generator. And then class mode, we are saying it's categorical. So similarly, we are doing the same thing for validation generator, where all these steps would kind of work here. The other thing that you could probably include in training generator is basically your augmentation step or other processing or other things that you want to do to your training. But yeah, you don't have to do the augmentation one test. So these are the two things that we have over here. So this validation, right now this will look at those 20% kind of reserved for validation or your testing data, and it will like kind of take it and work on it, right? And then you have this class mode as categorical as well. Right. So, and the other thing is you can also initially as well, you can segregate some amount of data as your global test set, so that that data is not present in your training as well as validation. So once you are like, what we are doing is, right, so your training data acts as your basically the data on which your model trains, and based on validation it we understand how the model is performing. But in order to get a better idea, you can probably have a global test set which the model has never seen, even for let's say the validation, and that will act as your final kind of data set that acts as the benchmarking data set for your model. So you can kind of set some global data set separately as well. So this is for the data processing step. So these will take care of all those train, test, split, data processing and so on. So which kind of makes things much easier for us. So I'll run these steps. Right, so you can see for the training we have 43,456 images belonging to 38 classes and 10,849 for those other 38 classes, the test images. Now let's build a simple convolutional neural network. So as these are some initial use cases that that we are working on, I'm just keeping things simple. So I haven't kind of went with like more complex model, but once we kind of move on to other use cases, right, so I'll try to include more complex architecture and probably like other pre-trained models that we can use for transfer learning. But for now, let's just stick to simple architecture to just understand the flow better. Okay, so here we have this variable called as model, and we are kind of initiating a sequential model. So this sequential, we have imported it from TensorFlow keras.models. This is where you can see. So TensorFlow.keras import layers and models. So this models have this sequential class which will be using, and layers contains all those your convolutional layers, max pooling layers, and so on. So we have this models.sequential. So sequential we basically use when we have a linear stack of layers. So it's like you have layers kind of stacked upon one another in a linear way, where like each layer kind of get a tensor as input and it kind of sends out another tensor as output. So for image classification, this is like a good approach to use like a sequential layer, sorry, the sequential kind of a model. So to the sequential model, now we are adding the layers. So model.add layers.conv2d, which is two-dimensional convolutional layers, and this 32 represents our filter. So you also call this as kernels, and these are kind of like these 3 comma 3 is the shape that I'm mentioning. So you have a 224 comma 224 image, and on this image, right, this kernels or this filters kinds of scan through these images as a matrix of 3 comma 3. So there are some animations that you can look up on. Again, we will understand more of this in detail in our deep learning course. For now, I'll just give you a high level overview. So you have a filter, 32 filters, and all these filters scan through these images in this 3 comma 3 matrix size, and this as an activation function of ReLU. So you have different activation functions of this sigmoid, softmax, ReLU, and so on. So for these layers, ReLU is a good activation functions that you have. You also have other activation functions as well, of course, right? So first is your filters, and the next one is the shape of your filters activation function in input shape. Input shape mention the size that you are working on. So the size that I'm working on is 224, which is stored in this variable. And 3 is the channel, number of channel. If you are working on grayscale, you don't have to mention anything, so that the model understands that it is a grayscale image. Now, but this is a RGB, so I'm putting 3. And then we are adding max pooling layer. So the work of this convolutional layer is to basically kind of find the different features present in the image. That's what like basically happens here. It kind of like figures out where those edges are, where those, let's say, some spots and all those things are. And max pooling layer reduces the spatial dimensions, your height and width of the image, and that's why we are using this. Again, later we will understand more about this in detail. And I have another set of convolutional and max pooling layers. So this is my first set, and now I have this another set of convolutional and max pooling layers, but I'm increasing this number of filters to 64. So it's not that you should always increase this kernels, you can also have same numbers. So the idea behind increasing that is, as we kind of go into more deeper layers, right? So the model should be able to find more complex features, and for that we would need like more number of filters to scan through the image and kind of do the convolution operation. And here also we are kind of applying the activation ReLU functions. And then again we have the max pooling layer. So these are our convolutional and max pooling layers. In between you can probably also add this dropout layers and other things as well, but I mean, for all those we can probably discuss later as well. The next thing is we need to flatten this. Till now the data that's flowing within it can be like a 3 dimensional array or 2 dimensional array, but later this we are going into dense layers, which are like the fully connected layers. And these dense layers expect the data to be 1 dimensional, as let's say a vector, right? So it shouldn't have a matrix kind of a shape, but a vector which is like a single dimension. So that will be done by this flattening operation, where your data will be flattened to 1 dimension. And then I have a dense layer, a deep layer with 256 neurons, and I'm using activation function of ReLU. So you can have more number of dense layers as well. You can again add some dropouts layer in between to make sure that your model is not overfitting, your model is not like that complex, and so on. So what basically dropout will do is it will turn off some of the neurons in your neural network. So that's the purpose, right? And the next final part is adding your top layer. So top layer, or this is your output layer, where this is the one that predicts the class of the image that you are working on. So I'm calling this layers.dense, and the parameter that I'm using is train generator number underscore classes. This basically returns you the number of classes that's present in your data set. So probably I'll print and show this to you. This should give 38. Yeah, so this is this output layer basically should always contain the number of classes that you have, which is 38, right? And the activation is softmax. So softmax is a good activation function that you can use whenever you're working with this multi-class problems. Whenever you're having a binary classification, you can go with the sigmoid. So sigmoid should probably work well in those cases, right? And what would happen is, so we have 38 neurons in our output layer, and each of this neuron would give you the probability that image belonging to a particular class. So think about it like this. So we have 38 neuron, and let's say the first neuron corresponds to the class that is apple being healthy, and the next one is the apple having a black rod disease, and so on. So when you pass a prediction image, each of this neuron would give you a probability. And how we predict it is, we get all the probabilities and see which neuron has given you the highest probability. Let's say the fifth neuron gave you the highest probability, which is 0.65, and other neurons have probabilities like 0.1, zero point 0.2, and so on, right? So let's say that's the case. Now we say that fifth neuron is the prediction that we got because that has higher probability. And now we look at the class names, and let's say the fifth neuron corresponds to let's say apple being healthy, and we say that that is the class it belongs to. So this is how this final output layer would work. Okay, so this is where we are building the architecture for our model. And you can always do this model.summary in order to kind of understand or see how your model is connected. And if you are kind of facing some errors, this is actually like helpful for you in order to debug it and see like how your architecture is looking like. So maybe I'll quickly give you again an overview of how you can infer this summary of the model. So this is a sequential model. So the first column that we have over here is the layers. So each row corresponds to each individual layers that we have built over here. So this is the first layer, second layer, and so on. So that information will be present. And this output shape is each kind of layer would give you a tensor as the output, right? So that's what I've told you. So that output shape will be kind of represented here, and the number of parameters in each of these kind of layers is kind of given in this basically in this third column of parameters. So that's what you can see. So this is the output of 2 triple 2 triple 2 comma 32. So all these are kind of depends this output of this convolutional layer, right? So this depends on the kernel that you have, and basically like the kernel size or the shape that you're mentioning. So this is the output. Similarly, the max pooling layer would, again, as I said, this would reduce your spatial dimensions. As you can see, your height and width have been kind of reduced by 2, right? So this is how your kind of max pooling layer kind of works, and you can see the difference over here. So you can use this in order to kind of see how your dimension or how your shapes of your matrices and tensors change as the data flows through the different layers of your neural network. And finally, in the dense layer, right, we have this 38, which is basically like you would get a matrix with 38 probability values, and from that we can infer it. And this basically shows you the total number of parameters and the trainable parameters, out of which like how many parameters are trainable. So if you are working with the transfer learning approach, right, so we can kind of freeze some of these layers, some of these parameters, so those won't be kind of adjusted. Only the when you say trainable parameters, right, so when the model kind of trains, it updates those parameter values that you have. So that's the basic idea. And the other thing, the none that you're seeing here is basically your batch size, right? So the number or the batch number basically. So we didn't give that batch information here yet. So this says none, which is basically that you can have any number of batch size. So we are going with a different batch size. So that will come into play only when we pass the data. So that's why it says none and so on. That's about it. So the next step is compiling the neural network that we have built. This is where we say that this is the optimizers that I want to use, which is Adam optimizer is one of the widely used ones. So it kind of is based on like couple of good optimizers. And then we have loss function as categorical cross entropy, which is usually used when we have this one not encoded labels, and when you pass this image to this data generator, right, so we would get one not encoded labels, and this is where we are using this loss function. And the metric on which it should train is accuracy is what we are saying. So this will like use accuracy as the metric when the training happens. So I'll compile the model as well. The next step is training it. So we call this model.fit, right? And we also have this storing this in a variable called as history. So this history will basically kind of store all your loss training, the loss accuracy and other kind of characteristics or things that you're getting throughout this training process. So this will store this in history, and later when we want to look at the performance of the model, of your accuracies and your loss function changes, we will use this history variable. So that's the idea. So we are calling this model.fit. Now we need to pass our data. So you call this train generator. So this will pass your training data along with those labels that it has created, right? So we are not like manually creating those labels, processing these images. So we have the pipeline, which is train generator, that we have created over here, and we are passing that, right? And then we have the steps per epoch. Steps per epoch is basically like how many batches that you have. So if you see train generated.sample is the number of training images that you have. When you divide it by batch size, so batch size is 32, that means one batch should contain 32. So when you divide it, you would basically get the number of batches that you have. So that's what we are passing to steps per epoch. Epoch is nothing but let's say you have 10,000 images in your data. So when your model kind of goes through all of these 10,000 images and learn from it, we call that as one epoch. So in this case, I'm having like 5 epochs. So that means my model kind of trains 5 times in the entire data set. So that's what you call a epoch. And each epoch we are kind of having a step, which is basically the number of batches is what we are passing here. And validation data, we are passing the validation generator, that which we have kind of created here, right? So that's our validation generator. So the purpose of this, again, the validation step is like the number of patches that the validation data would contain. So the idea is the parameters, your model's weights will be adjusted based on this training data. And once each epoch is done, right, we would evaluate our model with the training data as well as the validation data. So this is because training data can be misleading. So your model can perform well on the training data, but it can like may not perform well on the validation or the test data. So we could see at each epoch level to make sure that if a model is kind of starting to overfit in a particular epoch, or it's kind of overfitting like throughout all the epochs and so on. So it's always good to kind of get the metrics and validation data as well. So the other way would be to kind of with this within this training data itself, you can separate validation data, but here we are going with a separate validation set. So I'll run this. So this will uh, take like few minutes to run. If you want, you can increase the epochs, but make sure that your model is not overfitting. So you can see the loss function decreasing and the accuracy value increasing. Loss is basically it's the difference between your predicted value and your true value. So yeah, we want our last value to decrease, and that will increase our accuracy value. Like that's the basic idea. So you can see the steps it's taking. These are the steps that we have seen, and we have this loss value and accuracy value. So once this one epoch is done, right, we would see the metric for validation data as well. So this would take some time, and in the meantime we can probably look into the other pieces of code as well. So and then we have this model evaluation step. Again, model evaluation, we actually need to do a bit more than just comparing or just getting the accuracy and loss value. So you can kind of plot a confusion matrix to see that if let's say two particular diseases are kind of being classified inappropriately, it's like let's say apples black rot and potatoes black rot are kind of always misclassified, to understand that these two classes can be, or these two diseases can be kind of like a bit similar when you kind of see the leaf of that image, sorry, the leaf of that plant, right? So those information we can get from confusion matrix, and other metrics can also be helpful, but for keeping things simple, right? So I'm just going with accuracy and loss value. So I'm having this val loss, validation loss, and validation accuracy, model dot evaluate, and I'm passing my validation generator, which will pass my validation data and its labels, and I'm again having this steps with this validation generator dot sample divided by batch size, and I'm printing my validation accuracy. So let's run this as well. And now in this case, this is like a simple thing. So we are plotting the accuracy uh, curve as well as the loss curve for both training data and the test data. The first one is the accuracy curve for train and test, and the second one is the loss curve. So accuracy should increase in each epoch in an ideal case, but we may not see that case, as our model may not be ideal, right? And again, loss should decrease as the epochs kind of go by. So that's about it. So how you can infer it. So here we can see the first epoch has been done, and we are getting a loss value of 0.9, which is a decent thing, and accuracy is 0.72 on training set. Validation loss is, I mean, even lesser than the training loss, and the validation accuracy is, it's good, 0.84, but this is, I mean, we can't say for sure if it works really well just by looking at first epoch as well. In the second case, we are seeing that the accuracy is kind of increasing by a significant amount. And what would generally happen is, right, uh, you can again go with 10 epochs or even 20 epochs, but your accuracy value may not increase by a significant amount. So in this, let's say our accuracy increased by 20%. So it can be a case where your accuracy is 50% in your first epoch. It increases to, let's say, 80% in your second epoch, and it increases to 95% in your, or 90% in your third epoch. So after that, it's kind of not predicting well. So your accuracy just kind of increases by 1% or 2%, right? So that often leads to overfitting, and it's not like a good way to kind of work. So in that case, we follow a process called as early stopping, where in the training itself, if the model is not increasing its accuracy, its performance by a significant amount, right? So the model training will stop then and there. Even if you have 10 20 epochs, right? If the training process hasn't seen enough increase in the accuracy over, let's say, 2 or 3 epochs, it will stop the training there. So that's again a good thing that we can include in later videos. Yeah, you can probably do some research on that as well. So the other thing that we need to note here is neural network often tend to overfit because of the complexity of the model, and if you are using a simple data set as this plant images, there is a chance that it can overfit. So you may need to kind of see how you can process the data better, again adding augmentation to this, or keeping your model kind of like more simpler, adding the dropout rates. You can basically do a lot of those things, or you can also try some hyperparam tuning and so on. Okay, so that's other thing. So till now, so yeah, it's on the third epoch. Maybe let's go through the other pieces of the code as well. So now we would have trained our model. Once all these epochs are done, and we would have this model where we would pass a test image and predict it, right? And here I have two functions. So when you pass a new image, this should also be processed in the same way that your train data and your validation data has been processed. So for that, I'm writing this function. So I have this load and process image function and a predict image class function. So in this load and pre-process image, right, so we pass the path of the image. So basically what probably can do is I can like upload a image and copy these 3 test images that I have. I mean, it can predict correctly or it can predict wrongly. Both things can happen. So we can't be sure that if our model is pretty good, it should have a good accuracy on training and test. But if not, we probably can see like some misclassification. But yeah, that's okay for now. Yeah, we probably have this test apple black rod. So maybe we can take this example alone for now. So I have this load and pre-process image path, target size. So the reason is we need to resize the image, right? So the training data image that we have taken as the size of 224 which we have resized. So the new image that we are predicting, we don't know what's the shape of the image that the user want to predict. So we need to make sure that once they upload an image, we are kind of resizing it and making it like kind of suitable for the model to kind of predict from it. So we have this image.open from pillow library. So we have imported this image class from pill library, and we are opening this image and resizing this with the target size. Here the target size is 224, 224. So this will resize it, and we are converting it to a numpy array, which is like the better suited data type for the neural network to predict, and then adding the batch dimension, right? So even if we are predicting for a single image, the model requires or needs the data in the kind of a batch. So this is like saying that I have single image, or it's like I have a batch that has a single image. So this, your model would give you the prediction for that particular batch, right? And that's what happens in this like expand dimensions thing. And then we also shouldn't forget that we need to resize our model with 255, right, to make sure that the rescaling happens. So that's what we are doing. Again, the same normalization that we have done. If you normalize your training data and your validation data, if you're not resizing your test data, it's like the model doesn't understand it. So it should probably give you a prediction, but your prediction may not be accurate. So make sure that you're doing that normalization in your kind of pre-processing things as well. So I've also added comments, required comments in these functions as well. You can note it out. The only thing is just making sure that it's in the floating data type. So we are converting it to floating type and dividing it with the floating alias 255. And if you can kind of do this without this, make sure you can just try this to see if this is required, or you can probably remove this and try as well. So I got some issues, so I've added this conversion factor. And finally we are predicting it. So once we have processed this image, now it's suitable for us in order to pass this to the model and get a prediction out of this. So we have this this is the function that we will be calling, and we will pass the model, the image path, and the class indices. Class indices is, again, your model would just give you the prediction output in probabilities. From this we would get the index as 0, 1, 2, or all the way up to 37. So you would have from 0 to 37, but we need the class names, whether it's apple black rod or it's blueberry healthy and so on, right? So that class names we can get from this train generator dot class indices dot items. So you have this train generator class indices dot items, right? So you're basically, I'm creating a dictionary that has a key value pair where your key will be 0 to 37, and your value would be that class name, the name that you are seeing over here in this folder names. I'll probably also print and show it to you once the training has been done, right? So once we get the prediction, we pass that integer values over here and get the class name. So that's why we have this class indices. So this predict image class function requires the model as first parameter, image path as the second parameter, and the class indices that we have over here as the third parameter. So we are creating a variable as called as pre-processed image and calling the function load and pre-process image. So we are passing the raw image that the user has uploaded, the path of the image, and this load and pre-process will make sure that the image is properly kind of pre-processed for the model to predict, and then we call this model.predict on this pre-processed image, and we get the predictions. Now the prediction that the model is giving you is, again, as I said, it would give you the probability value, the probability value of the image belonging to all those 38 classes. So you would have 38 probability values, and we need to see out of these 38 values which has the highest probability. And this np.argmax will basically return you the index of the highest probability value. Again, that 5 example that I've told you, right? So you have let's say 38 probability values, and the probability value in the fifth index is the highest value, which is, let's say, 0.65. Now we put that index value of 5 in this class indices. That's what we are doing here, and get the name. So that name is that those subdirectory name, the class names that we have, and this will return that name, and then later we can print it. So that's what we are doing in this function. So I'm also kind of storing this json.dump. So you need to save the model as well as this class indices, so that we can use this in our Streamlit web app in order to kind of predict and show the class name to the user. So once all these are done, right, so we have uploaded the image. Probably I'll uncomment the one that has this apple black rod, test apple black rod. Yeah, that's the name that I have over here. Again, this may give a wrong prediction, but let's see how this is working. So the model has trained. Let's go back here and look at this. So the training accuracy has increased, and it has not increased after like the third epoch. So it stopped at 97. So I'm just having like lesser number of epochs. So you can go with higher number and see if the validation accuracy is also increasing. So you can see validation accuracy doesn't change, accuracy also doesn't change much. So we can basically improve our model. This is like, I would say this is not overfitting, but there is like a very slight overfitting issue, but we can again augment the data, pre-process it better, and we can have like a better model architecture in order to solve this. But for now this is okay. So let's see how we can use this model and get a prediction, because validation accuracy should be the same as this one, right? Because this is the accuracy of the model on the validation set after the fifth epoch, and that would be our final epoch. So that's why you're getting like the same values over here. So we are printing the percentage value, and then we are printing the curve. You can see the accuracy of training started with about 72, and it increased it after that. It has like a decent increase, but test accuracy doesn't increase that much. So that's why you're getting this kind of a curve. Again, this loss should be slightly inverted to this. So your loss should decrease, because your decrease in loss would increase your accuracy. So what you're seeing is basically like the opposite of the curve that you're seeing for accuracy. So we have this blue line for training and the orange line for testing. So this is like pretty easy to infer, so don't think much complex about it. And then we also have a predictive system code. I'll run this, and I'll also run this class indices. This is what I have been telling you. So we have a key value pair 0, and the key of, the key is 0 here, and the value is apple underscore apple scab thing, and we have the index and the corresponding class name, right? So I'll run this in order to save this class indices as JSON. So this would have been saved here. You can download this. So this is very important. So you need this JSON file in order to get your prediction. I'll open it. And other interesting thing here is, this is something that we need to note. If you see, the index that we are seeing over here is in the form of integer, but once I've downloaded the JSON, I'm getting it as a string. You can make sure that the processing happens properly. But what this would create an issue. What would happen is, when you are passing this index, right, when you're passing 0 or 1, so when you call np.argmax, this would pass an integer value, index value here. But when you put that on a Streamlit app, the index is actually a string. So what we have to do is, we have to convert this integer np.argmax into string and basically predict it. But let me not make things complex. So I'll tell you about it when we have the Streamlit app. So that's the idea. The difference is once your dictionary has been saved, the key values are getting converted to string. So that is something we need to handle later. That's one thing. Okay. So we have saved this class indices.json file with the same JSON library with the dump function. We're passing the dictionary and opening a file called as class indices.json and writing it. Now let's pass this image and get a prediction, and hopefully this should tell me that this is a Apple black dot image. Oh, this says the image is not there. Probably the path is wrong. Okay, it says JPG in caps. We'll copy this and paste it over here. Yeah, it says Apple black dot, which is the correct prediction. So again, this may work correctly for some of the images, and some of the images may not give you the correct prediction. Again, for that we need to improve our model, have a better data processing strategy, and so on. All this again, it's not easy to cover all those things in a single video, right? So as I make more videos, I'll try to add each of these individual more advanced thing so that it's not heavy for you to understand as well. So that's about building this model, and next you can save your model with this model.save, and you have this plan disease prediction.h file. The other thing that's hard to work on Google Collaboratory is, right, when you save the model without, I mean, if you don't save it in your drive, if you try to maybe I'll run this, but yeah, I'll copy this. This is like basically saving my model in my Google Drive. But if I do this by saving it in my default working directory, which is this space, this will, I mean, save the model quickly, but when you download it, it will take a very long time. So I would suggest you to connect your Google Drive from here. So you can mount your Google Drive by kind of clicking it, and you will kind of, I think it will ask for connecting the Google Drive. You can do that, or it will kind of show you this cell, right? You can run this in order to give your credential and save your model. So from your drive, you can quickly download the file. So that's the thing that I would prefer. So this is the path in my drive that I'm kind of using if you want to get this particular path that you're working on, right? So once you have mounted it, I'm sure you know this, but if you are not sure about it, I'll explain you. So once you mount your Google Drive, you will see a folder called as drive. So you can navigate through your drive and create a folder and save wherever you want. So I've already saved my file in my Google Drive, so I'm not going to run this. But if you want to save this file, I would suggest you not to do this, because as I said, it would take a very long time for you to download your model. So save it in drive and then get it. So that's about it. So now what we have done is we have trained our model, processed the images, trained our model, and this is the model.h file is the one that we are interested in. Now I'll open my PyCharm where I have the code for my Streamlit app. I'll stop this previous Streamlit app that I run to show you the demo. Right. So you can probably use the same code structure. So this is my working directory, and then I have this app directory where my Streamlit app is present called as main.py file. All these other files I have for dockerizing this, but all these things we can see later. The important things that you need to see are this requirements file, which has this numpy, Streamlit, and TensorFlow. So you need to install all these libraries, probably use the same versions to make sure that it's not throwing you some errors. Main.py file, which has the code for your Streamlit app, and trained model is the folder present in the same directory as this main.py. So we have this app folder in your project directory. You have this within that you have a trained model which has this planned disease prediction model.h file, and then you have this main.py file where we will be loading this class indices as well as our where is this, yeah, so our model as well. So make sure that you are putting your class index file and your model file in the same directory. So I've given all those things in my repository. I'll share this repository with you as well, so you can use that class indices.json and yeah, class indices and the train model. So again, I couldn't upload this model in Git because it was like a larger file. So I've given you a text. What you can do is you can either train your own model in the Google Colab, or I have given the model link of the model that I have trained. So you can go to this link, download this model, and then you can kind of put it in this trained model folder and run it. If you just clone this repository and run it, it won't run because this actually doesn't have the model file. So it just have the link. I've also given that link in the readme file, so you can download it from here for your convenience. But I would suggest you to run your own collab and kind of get the model from there instead of using the one that I'm providing you. So that's about it. So this is our main.py file. Maybe now we can understand the code for it. So I'm importing all the required libraries: OS, JSON, Pillow, NumPy, TensorFlow, and Streamlit. So here I'm changing the working or basically storing the working directory in a variable called as this thing, because when you run a Streamlit app, the working directory may change to your the PC's user directory. So to make sure that you kind of say that this is the directory that you should look at. So I mean, in this case it may not be important, but I would suggest you to always use this whenever you are using Streamlit, because when you call a file, right? So here if you see, I'm calling this working directory. So when I run the Streamlit app, if I just say trained model plant disease detection, plant disease prediction model, it won't look at this app, because as I said, the working directory would have changed. So when you pass this working directory, what this line basically does is, it gets the absolute path of the file. In this case, the file is nothing but main.py. So it gets the path of the file and it stores over here. So it's like copying the entire path of the model file and it pasting it there. So instead of hard coding it, I'm getting it from the Python file itself. So it's just similar to going here, copying the entire path of this train model thing and pasting it here. But that's not the ideal way, because if you are working on it right now, you need to go to the code, change the directory according to your PC folder structure and so on. So instead we can just get the absolute path from this file itself by calling this kind of function and getting it, and then passing it to your trained model, class index model, and so on. So that's the idea. So here we are calling this working directory, giving the model path, and now we are loading this model with tensorflow.keras.models.load model, and then we are loading this class indices JSON file to this dictionary, and then we have the same functions that we have seen in the Google Collaboratory. The only thing that's different over here is, so once we find this np.argmax, I'm converting this integers to string, the index to string, because as we know that the index have been changed to strings. Probably you can work on some methods to retain the values as integers. So yeah, nothing wrong in that. So we have those two functions. Again, the same functions that we have seen here, so I'm not going to explain those. Now is the Streamlit app structure. So I'm creating the title as plant disease classifier, and I'm creating an upload tab with st.fileupload and the type that we can approve our JPG image, JPEG, and PNG images if uploaded file is not none. So this will appear in the web app only if the file has been uploaded, right? So once the file has been uploaded, this uploaded image won't be having a none. So when the uploaded image is not none, this will run. So we will open the image and we have these two columns to display. Just you can do this without these columns, but this is just to organize the web app in a better way. So in the first column, we are resizing the image to 150, 150. Again, we are not passing this. This is just to display. We are kind of resizing this to 150, 150. So don't confuse it with the 224 and 224 resizing that we do in this particular function. This is just to display the image. This resized image won't be used anywhere. Instead, just for displaying it, we'll be using this. And then we have the second column where we have this classify button, and then here we call this predict image class that also has this load and pre-process image function. So we process the image and get a prediction out of this. So while predicting this, we need to pass the model uploaded image. So instead of path, right, once you have loaded this in below, you can also pass this uploaded image. So that will like take care of that, and you pass the class indices in order to get the name of the index. And finally we say st.success. So when you put st.success, it will create a green bar and it will print the prediction there. So that's about it. Now let's see how we can run our Streamlit app. And in PyCharm you can use in order to access your terminals, and it's a better IDE for debugging purpose as well. So my default working directory is this Jan25 thing, and but my main.py file is present within this app, right? So what you can do is either first step, probably you can do this pip install to make sure that NumPy, Streamlit, and TensorFlow that I mentioned here are kind of installed in the proper library version. So for that you can do pip install or app/requirements.txt, because my txt file is within this app folder, right? Because this is required for building the Docker image as well. So that's why I have this in this instead of having this in the project directory. So this will install NumPy, Streamlit, and the other things. So I've already installed it. So that's what it's saying here. And the next step is we need to run our Streamlit app. For that you can say Streamlit run app/main.py, or the other way is you can kind of do a cd space app. This will take you to that particular directory. Now you can just say streamlit run just main.py, because we are within this app directory, so that you can kind of work upon properly. So I'll delete this and clear this and I'll come out of this app. So for now I'll just come out of it and just run this streamlit run uh, app slash main.py. So this should open, or yeah, open my browser and show the Streamlit app where we can upload the image and get a prediction. So here I can go ahead and browse the files, and I'll upload this test apple black rod JPG. So if you see this, this is the two columns that I have mentioned. So the image that we are representing in this left hand side are column 1, and this classify is present in the right side, just are column 2. So that's why we have this column 1 and column 2 thing. If you don't do this, this classify will be in the bottom of this image, but even that's okay, right? So that's not a big deal. So I'll click this classify, and this should give this st.success in a green bar, and it should say the prediction, which is a black rod. You can, this is just for reference to make sure for us to understand, right? If the model is predicted correctly, I've renamed this, but yeah, you can probably download the some images from this color folder, and probably see like how this is predicting. Again, if you have trained a grayscale image, you should use a grayscale image. I'm sure that you already know this, just pointing this out. If you are using a colored image, make sure that you are using that. And probably I'll test this potato early blight and see if this is classifying correctly. Again, I've tested few images, it was like not predicting correctly. So again, we need to improve our model. So that I'll kind of leave it to you as an exercise that you can do. But yeah, for these we are getting like proper predictions. So this is how you can build your Streamlit app. And now we are in the final step of deploying this in a more standard way, where we will be kind of dockerizing the Streamlit app and building Docker containers out of this. So I'll stop this and clear all these things. So for that, what we need is a Docker file. So Docker file is basically a file that contains all the instructions or commands in order to build the Docker image. So once you have built the Docker image, right, so it's like a template. You can create the instance of this Docker image, which is your Docker container, that has all the dependencies like Python, all the libraries, and all this main py file, the train model files, and so on. So you have all these things in a Docker container, and then you run it as a Docker container as a package, so that you don't have to worry about like another person having a different library version, different Python version, and so on. So you can also deploy these Docker containers and Docker image easily in cloud platforms like Azure and AWS. So these are like other advantages to this, right? So that's, yeah, that's the good thing about deploying this as a Docker. So that's what we'll be doing now. So we won't be going into cloud aspects of this. I'll just show you how you can build a Docker image out of this and build Docker containers from this. So this Streamlit app has been closed. So I'll close this for now. Again, this config.2yaml and credentials.2yaml, I have given this in my GitHub repository itself. The same code structure, you can use this. These are some default files that the Streamlit app needs. So you can just kind of have this. Let's quickly go through this Docker file. So I've also made videos recently on I mean, what are these Docker files, what are these commands mean, and so on. So if you want a detailed video, please refer to that one where I've explained like how you can deploy Streamlit app as Docker containers. Here I'll just give you a quick overview of this. So first we are setting up the Python version, Python 3.10 Slim, and we are copying all the contents to the folder called as app. So this is like a tricky thing. So when I say copy dot, it's the directory where my Docker file is situated. So when I say copy space dot, it will copy all the files present in the directory where my Docker file is situated. In other words, in this case, it will copy this trained model folder, class indices file, all these things, and it will store in a folder called as app. So this app folder is not the same as this one. This app folder is the one that's present in your Docker image and your Docker container. So basically, we are copying all this contents present in our local in this working directory to the one that's present in the Docker image that we are building. And within this Docker container, we are kind of changing the working directory to /app, where all our code files and required config and credential files are present. You don't have to change anything in this files. You can just use the standard one that I've given you. And then we run this pip install r requirements.txt command. So here you don't need to put slash app, because the working directory would be this app and that would contain this requirement.txt. So you don't have to change anything on this Docker files. Next is that this is saying like which port the Docker container should run. So we are saying expose 80. So on this particular port, our Docker container, which is basically the Streamlit app, will be running. And then we are creating a folder called as .streamlit, this make directory, and copying this config.2yaml and credentials.2yaml to the streamlit folder. So these are like standard things that you need to do with these files. And finally, I'm putting these commands which are streamlit run main.py, the same commands that we have run. So these are the commands that should run when we kind of run our Docker container and we build our Docker image. So that's what we will do. In order to do this, make sure you navigate to the folder where your Docker is present. And the other prerequisite for it for this is, right, so make sure that you have installed a Docker. Again, I'm on Linux, so I have installed Docker. Again, if you are also working on Linux, you can install it from the terminal and access Docker from terminal. You can do the same in Windows, but in Windows you also have a graphic user interface for Docker called as Docker Desktop. So you need to go there and start your Docker engine before doing this. And in Linux, right, you can also do this by starting the Docker with sudo systemctl space start Docker. But for my system, it's kind of, whenever I start my PC, it's kind of starting by default, so I'm not doing that. But if you are facing some issue saying that the Docker daemon or something, it's not started, you can run that command. You can find that online as well. It's no big deal. So once we have all those things, now I'm in this Jan 25 code prep directory. I need to navigate to this app directory. So here I'll say cd space app. Now I'm in this app where my Docker file is situated. So I'm going to build this. I'll say sudo. And the other important thing is, if you're working on Linux, run sudo commands. So we need to run this as administrator. And if you're working on Windows, make sure you are running PyCharm as administrators. So here I'll say sudo docker build t. So we are going to tag it with a name. I'll call this as plant disease prediction image. So this, and space dot. Oh, okay. I can also give a tag saying that this is, let's say, v1.0. This is like usual standard naming convention that we use, which is like, let's say this is the version that we are working on, and space dot. Again, dot is the home directory. So when you say dot, it expects that Docker file is present in this app directory. So that's why we say this dot. Similarly, what we have over here. So if you have a subfolder within this app and there you have this Docker file, make sure that you are mentioning that folder here. This dot is like really important. So we say sudo docker build -t plant disease prediction image. So this will build my Docker image. I have to put my password as I'm running the command as administrator. So you can see all these commands will be running. First, it will install Python, copy the contents, working directory, all those things will be happening. So you can see Python 3.10 is getting installed and it's copying the files and it's changing the working directory and it's running the pip install command. This should take few seconds. Okay. And then, yeah, we would have this, yeah. So once this has been done, right, we would build the Docker container from this image. So again, this is the usual analogy that I have been using in my previous videos. I'll probably use this in this video as well. So you can think about this Docker file as, let's say, the template in order to build the Docker image, right? Or you can think about this as like the plan and the steps that you need in order to, let's say, build a car, or let's say a car manufacturing plant. Our end goal is to manufacture a car, but for that you need an infrastructure, which is your plant that manufacture it, right? Your car manufacturing plant. You can think about your Docker image as this manufacturing plant, and you have the steps in the Docker file, and the Docker containers are like the final cars that we are building. So you have a plan of action, which is your Docker file, and you have the infrastructure to do that, where you have your manufacturing plan. Like similarly, you have your Python, all the required libraries and so on. And finally, you can build any number of cars from your plant. Similarly, you can build any number of containers from your image. So images are nothing, sorry, the containers are nothing but the individual instance of the container that you are creating. So that's how you can probably understand Dockers and this Docker containers and so on. Again, the other advantage is that you can deploy these easily in cloud services like AWS or Azure. And I've also uploaded a video on how you can deploy Docker containers as Azure container instance. So that may not work in this case because it would be better if you have a GPU instance in Azure, but container instance doesn't give you. So you probably need to deploy it with Azure Kubernetes service, but that's going to cost you a lot. I'll probably upload a video on better way to kind of deploy the deep learning models on Azure and probably AWS at a later time. But yeah, this is something that you can keep in our mind. So yeah, I think Docker images completed building. Now you can check the Docker images present in your systems with this sudo docker images. This is the one 30 seconds, 33 seconds ago. So this is the image that I built, planned disease prediction image v1.0. So now I'm going to run this create this Docker container. So I'll call this sudo docker run -p. So make sure that you use this thing -p 80 is to 80, which is just mapping the port that we have, which is 80:80. And give the image name. So you can either copy and paste this image ID, or you can copy this image name along with the tag, which is this v1.0 that you're seeing here, v1.0. Sudo docker run -p port 80 to 80, this one. So this should give us a link. A command not found. Oh, made a typo, so I'll correct this one. Sudo docker run p80. This is the port that it's running. Again, I've tested this on Windows. So Windows, this port is not working. So you can just go to localhost, and on localhost this would work. And probably after localhost you can try 80. So I'm not very sure, but you can try it and let me know in the comments. So but Linux and Mac, this URL would work. This is the 80 port that we did. But again, Windows, just go to just type localhost and see if this is opening. So here we have the same Streamlit app. The only difference is we are not running it as a main.py file, but we are running this as a Docker container. So I'll go ahead, browse this Apple Blackrock image thing, and yeah, so it's displaying. Now I'll classify this, and this is working as expected. So this is how you can build a Docker image out of this and deploy this as a Docker container. So I can kind of stop this by Control-C, and you can see the list of currently running images by running the sudo docker ps. You can see nothing is running. If you want to also see the stopped Docker containers, you can see sudo docker ps-a. This will show the ones that have also been like stopped. This is the one that has been stopped 16 seconds ago. And if I want to delete it, what I can do is I can, again, you can delete this individually, but if you have a bunch of containers you want to delete at once, you can say sudo docker container prune. Will ask for confirmation and say yes. And again, you can see the list of Docker images that you have. So I'll say sudo docker images. My image is still there, so I can, if I want, I can create another Docker container out of this, and see, you can see it's a pretty large image. If you want to delete it, you can just run the command sudo docker rmi and image ID. Sometimes you need to do a force delete, so for that you can do a -f. I can probably paste a image ID or complete image name with the tag. So this will be deleted. You can again run the sudo docker images to see if it's there. So this is how you can build a Streamlit app and deploy it on Docker. Yeah, so that's it from my side. I hope everyone understood what we have done. So please make sure that you have tested and you have like practiced all this code. So this probably would be helpful for you if you're working on some other use case. So that's it from my side, and I'll see you in the next upload. Thanks for watching. Hello everyone, I'm Siddharthan. This is the 8th deep learning project video in my channel, and in this video let's understand how we can build a neural network using PyTorch in Python. And for this purpose we will be using the breast cancer dataset, where we will be building a classification neural network using PyTorch. So we have already worked on this breast cancer dataset with machine learning models as well as neural network with TensorFlow. But the main objective of this particular video is not this particular use case itself, but how we can do this in PyTorch. So that will be the agenda for today's video, and let's get started. And before going into the coding aspects, I just wanted to quickly discuss about the different frameworks that we kind of use for deep learning. So we have already worked on TensorFlow and Keras, right? So TensorFlow is, again, we know that it's developed by Google, and the other famous deep learning framework is PyTorch. And PyTorch is developed by Facebook's AI research team. So initially, TensorFlow used to work on this concept of static computational graphs, where we kind of declare all the computational operations that should happen and all the variables and so on. So this is what we call as a statistic, basically a static way of doing things. And then we have this PyTorch, where all these computational graphs are built dynamically on the fly, right? So later what happened is, like, this seemed to be a better approach, and from TensorFlow 2.0 version, they have kind of included that version as well. But again, both of these are widely used. People kind of always say that PyTorch will be a bit easier compared to TensorFlow. And then we have this Keras, which is kind of a wrapper of this TensorFlow and few other libraries, like Microsoft's deep learning framework. So Keras kind of gives this high-level APIs that you can use in order to build this neural networks. But the problem is, you can't kind of build this custom training loops when you want to build like a more complex neural network architecture. So that's where the limitation of Keras comes. But again, it's super beginner friendly and so on. So if you're just starting with deep learning, Keras would be good. But at a particular point, you have to kind of learn either TensorFlow or PyTorch. But again, I would tell you, like, not to just say that I know only TensorFlow or I know only PyTorch. So it's always better to kind of stick to one library, but also make sure that you have a good understanding and like practical skill of the other library as well. So that's the agenda, and that's why I wanted to make this video on PyTorch as well. And in my channel, I maybe try to make videos on both TensorFlow and PyTorch wherever possible. So that being said, now let's get into the hands-on part, where we can try to build this neural network for this breast cancer classification problem. Okay, so I have my Google Collaboratory open, and the first thing to do here is make sure that you are connected to a GPU runtime, so that your training is kind of happening faster. This is a small data set. This is like a numerical data set, so this won't take a lot of time. But if you are working with an image classification problem, then you really want to connect to your GPU so that we could accelerate the training. So in your collab, go to your runtime and change runtime type, and you can choose a GPU. So we have this runtime type as Python, and I'm going to choose the hardware accelerator as T4 GPU and save this, and you can connect your system. So now we would be allocated a GPU session. So now let's get into this coding part. So the first step is I'm creating a text cell, and I'll call this as importing the dependencies. Okay, so here let's import all the required dependencies. So let's start with PyTorch. So PyTorch, it's not imported as PyTorch but just as torch. So I'm importing torch, and then I'm importing this torch.nn as nn. Okay, so from this torch we are importing this class called as nn, which stands for neural network. So we will be using this, and then I'm going to import torch.optim as optim. So this is basically used to load our optimizer. So we have this Adam optimizer, stochastic gradient descent, and so on, right? So we would have used this in TensorFlow in model.compile, and here we kind of use this from torch.optim. And then for dataset, I'm going to use the dataset from sklearn library, the breast cancer dataset. So I'll say from sklearn.datasets import load breast cancer. The next thing is, so let's keep the data processing and all this like things simple. So the main focus is to build this neural network. So I'm not going to do a lot of EDA and stuff like that. So let's just keep things simple. So here I'll import from sklearn dot model selection. I'm going to import my train testlet. The next thing is, let's also standardize our data. So for that we need from sklearn.preprocessing import standard scalar. Let's run this. Okay, so these are all the required dependencies and the functions. So the next step is we need to kind of configure our device, whether it's going to run on CPU or a GPU. So in TensorFlow, it automatically picks that up. So if you have a GPU, it's going to use it. But for PyTorch, we kind of need to explicitly mention that. So here I'll create this text cell and I'll name this as device configuration. And here we need to say that you can use CUDA. So here I'll put a comment saying like check for CUDA. So check for CUDA availability. So here I'm going to say device is equal to torch.device, and here we need to set it up with either CUDA or with CPU, right? So these are like the two options, and basically CUDA is the one this is like a parallel processing architecture that's developed by NVIDIA's, and it's work well with NVIDIA GPUs, and the ones that we connect here are also like NVIDIA GPUs. And what I'm trying to do here is let PyTorch know that you can use this CUDA architecture so that you can do the parallel computing wherever required if GPU is available. So I'm going to say CUDA if torch dot CUDA dot is available. So this basically, so we have this torch.CUDA is available, right? So this basically checks if you have a GPU and that supports CUDA. If that's the case, this is going to turn out as true, and in that case we are going to use CUDA. If we don't have a CUDA enabled GPU, in that case I'm going to say else CPU, right? So the device would be CPU. So if there is an NVIDIA GPU where you can use this, I'm going to go with CUDA. If not, it's going to be a CPU thing. And we can also print and make sure that we have this CUDA now. So here I can say if using device, and here we can substitute this device thing to basically can run this and check if it's able to access your GPU. So this should say CUDA. So that means like it kind of found this GPU that's available for us over here, this 15 GB GPU thing, and yeah, we can kind of go with the other steps. So the next step is like simple data curation and the pre-processing steps. So I'll call this as a data collection and pre-processing. So as I said, we won't be doing like regressive data pre-processing and analysis here. So we will just like split the data into training set and test set, and we will apply our standard scaler. So here I'll say load the breast cancer dataset, and let's call this as data. So data is equal to load the same one that we have imported from sklearn. So call this and say x is equal to data.data. So this data.data contains all the features, and your y contains the target. So data.target. So if you want, you can also train it with a CSV file of this breast cancer data instead of this sklearn, so that you can use it for some other data set. So you can definitely try that, but for easier usage I'm just going with this particular version. So let's run this. So your x should contain your data and y should contain the labels. Maybe we can just try printing this x and y and check. So we have all the features, and then I can print my y. So y contains like all this labels. So maybe one is for benign and the another one is for malignant case. So that's like the two classes that we have, and then we can split. Maybe I'll try printing only like 5 rows, okay, for this label. So as you can see, so now let's split the data set into training and test set. Here let's say x train comma x test, y train comma y test. So these are the two things that we have. So we have a training data in x train, and the corresponding labels will be stored in y train, and then we have the test data features in x test, and the labels for test data is getting stored in y test. So this is equal to train test split, and within that we can give this x and y. So we have this uppercase x and lowercase y, the usual way of representing this. I'll say x comma y and let's say the test size is going to be 0.2 and my 20% and my random state is equal to 42. Let's run this, and you can also print and check the shape of this x and y. So we have this explain dot shape, and copy this and print this. Let's first maybe print x shape, and then we can try printing x train and x test shape. So your x is like the complete data set, x train is your training, and x test is your test data set. So we can see, so in total you have 569 data points. So 80% of that, which is 455, goes to your training data, and 114 goes to your test data on which we will do our evaluation. So the next step is standardizing our data. So for this, we can do this like after splitting our data into training and test data to make sure that we don't face any data leakage issues. So here I'm going to say standardize the data using standard scaler. Again, this is used in order to make sure that your data is kind of normally distributed. So if your data is normally distributed, your mean is going to be 0 and your standard deviation is going to be 1. So in order to test this out, what you can do is put this through a distribution plot. So put your training data through a distribution plot and see like what's your distribution plot is for the different columns or the different features. And once you do your standardization, and then you can check it again, and later now you will see a normally distributed curve. So previously you won't be having a normal distribution. So again, the main purpose of doing is like the linear models like logistic regression and SVMs expect the data to be normally distributed. So we kind of have to do that again in neural networks as well. Like it's kind of good to do the standardization, right? And if you are working with mainly tree-based models like random forest and XGBoost, it's kind of not required to do this standardization, but that's the overall idea. So here, let's say that this scalar, so I'm creating a variable called a scalar, and this is equal to standard scalar. And then let's scale our data, scale our x train and y train. So let's say x train is equal to scalar dot fit transform x train, and then for test data we don't have to do a fit transform, we can just do a transform. So it should be scalar dot transform. Okay, so this is because we always fit our transformer or the scalar on the training data and then transform it. So you shouldn't kind of fit your scalar to the test data. So your test data should be scaled based on the scalar that you got after fitting your training data. So this is how you should do it. So scalar should be fitted and transformed on your x train, and it just should be use that scalar to transform your x test. So we can run this, and now your data will be normally distributed following all those process. And the next step is now it's probably in a numpy array. You can also check the type of x train and y train. So let me check this type of x train, and it says numpy and d array. And now we can't use this numpy array in PyTorch. The preferred data type through which we kind of do this computations in PyTorch is tensors. So we need to convert this numpy array into tensors. So for that we can just we'll write a command saying convert data to PyTorch tensors. And yeah, and the other step that we can do here is move it to GPU. Again, we know that GPU is available, so we are doing it. If not, you can just maybe move it to CPU and try that out. So this is because we want our processing and training should happen in GPU, right? So we kind of move all this data to the GPU's memory. So that's the idea over here. And I'm going to say xtrain is equal to torch, which is the library that we have imported, dot to tensor, sorry, just tensor, and within that I can say xtrain, and we have to mention like the data type as well. So I'm going to mention d type is equal to torch dot floating point. So let's take like 32-bit floating points and say dot to device. So this device is nothing but CUDA, the GPU that we have already kind of loaded right within this variable called as device. So that's what I'm saying. So this will move your training data into GPU after converting it to PyTorch tensor. And we have to do this for the labels as well as the test data. So I'll paste all these things here, and we can just you know, copy and paste these things here. So first we are moving the training data, so white train also goes here and it moves to the device, and then we do the same thing for test data as well. So we have this x test, and finally do this for your white test. Okay, so basically we are converting our numpy arrays into tensors and then moving it to device, but you probably know what a tensor is, but if you don't know, I'll just like have this picture to explain you. So it's again, it's think about this. So scalar is like a single value, right? So it's in this case, in this image it says 11, so it's a single value. And vector, it's kind of like an array. So it's, let's say it has like one dimension, so it has like one row, 5, 3 and 7. And then this is like a column vector, just like the same vector, so no issues with these two. And then we have a matrix which is like a two-dimensional data type. So you have this rows and columns. So in this case we have 2 rows and 3 columns. So this is what a matrix is. But tensor, you can think about it as like multi-dimensional matrix. So if you see this one, right, so it has like, it's kind of has this depth as well. So it's 3 rows and 3 columns, but also it has like 3 other values as well. So this is what we call as tensor. You can just think about it as like an higher dimension of a matrix, right? So that's what a tensor is. So we need to convert all this data into tensor for PyTorch to be able to do this processing. And again, tensor has this advantage of making use of the GPU acceleration, and computation kind of happens faster, and it has all these benefits. But yeah, just understand that we need to do this conversion, but maybe all those details you can look up later, or maybe later I can post a video for that as well. But yeah, that's the overall idea, which is to convert these to PyTorch tensors and move it to the device, in this case which is a GPU, so which we have already loaded here. Now I'll run this. Okay, so the next step that we are going to do is build the neural network architecture. And again, this is the first time that we are building our neural network in PyTorch. So let's keep things simple here. So it's going to be a bit different from what we have done before. So previously we have kind of used Keras with TensorFlow backend. So things were like pretty simple here. Basically simple there. But here it's going to be slightly different. It's not hard, but it's just different. Let's understand that. So here I'll say neural network architecture. Let's make this in bold, and here let's say define the neural network architecture. So again, this is not CNN or something. This is just like a simple artificial neural network. So later maybe we can build a CNN with PyTorch as well. And then here I'm going to create a class called as neural network, or let's say neural net, and within this I'm going to say nn.module. Okay, so this may seem a bit new to you. Maybe before that I'll just add this one thing alone. So diff, we're going to use this init function or init method so that we can initiate few parameters over here. Okay, so let's understand this. So we are creating a class called as neural net, and within this parenthesis we are kind of passing something called as nn.module. So nn is nothing but the torch.neural network that we have imported as nn, and within this nn we have another, let's say, subclass called as module. So when I say class of neural network nn.module, I am inheriting the characteristics of this particular class, the nn.module class, to my class called as neural network. So this is what we call as inheritance, where we kind of inherit let's say the methods and the variables of, not variables, let's say parameters. So we inherit the parameters and the methods of this class to this class called as neural network. So that's what we do. And in the next step we have like all these functions. So first is like init function, where we kind of define all the parameters that the model needs. So within this init I'm going to say first parameter is going to be self. I hope you know what this self is. So later we will load this neural network into a class, sorry, into a variable. So this is what we call as initiating a class or instantiating a class, and the self is kind of addressing to that. So let's say that later we create a variable called as model is equal to neural net. and within this parenthesis we would pass some values, whatever the values that we are going to give here. So all these basically we have this model is equal to neural net, right? So this model is basically we are giving an instance of this neural net to this, and this model is what we refer as self in this case. So yeah, that's about it. And then we need like some input parameters like the input size, and then we are going to give the return size, and then we need this output size. So input size is basically how many number of neurons should be present in your input layer. So we would have used this layers.flatten in Keras, right, where basically the input layer that contains the same number of neurons as the number of features. So this is that number, like how many features are there in your data set, so that how many neurons should be there in your input layer. And then you have this return size. Return size is how many neurons should be present in your return layer. So that's what this return size means. And then we have this output size, which basically represents the number of neurons in the output layer. So here we are working with a binary classification problem. So let's say that we have two neurons or something. It's usually equal to the number of classes that you have in your data set. In this class, it's going, in this use case data set, it's going to be 2, so your output size is 2. So that's how we can initiate these parameters. Again, you can do this differently. This is just like one way of doing this, right? So next step is I'm going to do another interesting thing calling super neural net comma self dot init. So you might not have seen something like this. So here what we are doing is, as I said, so we are inheriting the components, or let's say the methods and the parameters of this NN module to this neural net, right? So when we call this super, again it does this inheritance. It's kind of like a check. It makes sure that whatever we need from this module class is kind of initiated properly. So all the parameters and stuff are getting initiated properly, and the super is like kind of like a built-in function that we have in Python. So again, it's mainly for inheritance. So inherit all the things that this nn.module needs, so that again it's like a validation check that you need to do. So that's the step we are doing here, super neural net. So I'm kind of inheriting all these things to this class called as neural net, and then we can create our init parameters. So I'll say self dot fc1 is equal to nn dot linear. So I'm taking like a linear layer, and here I'm going to say input size comma return size. So I'll explain you in a minute after writing this piece of code. So what's the purpose of this? And then I'll say self dot relu is equal to nn dot relu. So E should be in lowercase, R, L, and U should be in uppercase. And then let's put a parenthesis here. And now I'm going to say self dot fc2 is equal to nn dot linear hidden size. And then we have this output size self dot sigmoid is equal to nn dot capital S, and then we have this sigmoid. So let's understand this. So in TensorFlow, or basically in Keras, when we build our neural network, we would mention our input layer with this layers thing, right? But in PyTorch, you don't have to do that explicitly. So when you give this input size, that input layer is kind of taken care of. So we have to start with the next layer, which is the hidden layers. So FC basically represents your fully connected layers, or basically your hidden layers, right? So your fully connected layer, and FC1 is your first fully connected layer, and FC2 is your second fully connected layer. So basically I'm having like two fully connected layers here. If you want to add more, you can do that as well, right? So okay, let's maybe first understand this. So I'm calling this self.fc1. So whenever you're initiating these stuff inside this unit, you do this self dot, because again it's referred to that variable that we would later create for this particular class. So we have the self dot fc1 is equal to nn dot linear. So we are taking like a linear network where it basically does a linear transformation of the data that it takes in. So here we are passing two parameters. One is input size and hidden size. And this is basically the first input size represents how many neurons should be present in your fully connected layers, and this should correspond to the number of input data that is coming to it. And the second parameter is like what's the output sizes, what's the output or basically the number of neurons in the second layer. Maybe I'll show this to you with a diagram that would make more sense. So let's say that okay, so I can take this one. So we have this input layer, and then we have like 3 hidden layers and 1 output layer, right? So consider that the input layer is already taken care of when we gave the input size, and then we have this, let's call this as the FC1, the fully connected layer 1. Okay, so this is my FC1. So here count the number of inputs that it is getting. It's kind of getting, so we have 1 2 3 4 and 5. So your input size is going to be 5, and hidden size is how many output it should give out. So for that you need to count this one. And in this case the hidden size is going to be the same, right, for all the hidden layers. So we can just go with that, but if you want you can also change this number for, let's say, a particular hidden layer has a different number and another hidden layer has a different number. You can do that as well. So basically the first parameter takes in like the number of inputs that it's going to get, and the second parameter is like how many output it has to send. So we have this input size coming into it, and output hidden size is like how many values it should pass. So this is for fully connected layers, and here we are going to add like a ReLU activation function so that we can add non-linearity. So in this step it basically does a linear transformation because we have added like a linear layer to it, and this ReLU makes sure that the model has some non-linearity to it so that it can capture those complex relationships in the data. And then we have this FC2, which is, let's say, the second fully connected layer. So it has this hidden size. This would be the input for this layer, right? So for first layer the output is hidden size, and for FC2 the input is going to be that hidden size. So we have that, and the output is going to be output size, which is 2, because let's say this is kind of our final layer. So we have this output size, and we know that for binary classification we use sigmoid activation that gives you the output between 0 and 1. So just like probability. So recently I've made video on different activation functions and why it is used. So that's for this purpose. Okay, so this is the stuff that we have in it. If you want to add this dropouts and other layers, you can maybe like add it here and work on it. But just to keep things simple, I'm just going to use this one for the example. Okay. So the next step is we are going to create another function and call this as forward. So this is basically the forward pass or forward propagation for our neural network. So let's say that forward, and we know that the first parameter is going to be self, and now we are going to pass this x. So x is nothing but we would have this batch size and pass the data as batches, right? So that's what this x represent. So let's say that this out is equal to self dot fc1. So we know that FC1 is your input for fully connected layer 1, and we are going to pass our x here. And now let's say that out is equal to self dot ReLU, and within this we have to pass this out, and then the next out will be self dot FC2, and again we need to pass this out. The next step is out is equal to self dot sigmoid, and finally you return your out. Okay, let's understand that. So what this basically gives you is, so you pass a data to this forward function, and that would process your data through the neural network, or basically your training or evaluation happens and you would get the output. So that's what this function does. And now basically we pass the data through all the layers that we have created here. So we have this x, and first like we have this input layer that's getting created implicitly, and then we are passing our data to the fully connected layer, and this fully connected layer, as I said, it would perform a transformation on the data set. So here it's going to be a linear transformation, right? So we pass this to the fully connected layer, and then we store this output in the variable called as out, and then we pass this out through the ReLU activation functions to apply the activation functions, right? So ReLU basically, if the output value is negative number, it's going to turn it to 0. If it's a positive number, it's going to give whatever number it is. So basically we are passing it through the fully connected layer 1 and then applying the activation function, and all this output are saved in the same variable. So this out variable is basically getting replaced with all the outputs, and then we pass this output value to this fully connected layer 2, get the output here, and then apply the sigmoid to the final transformation, the same order that we have over here, and finally you would return your out. So this is the forward propagation, or basically what basically happens when your data or your batch passes through the neural network in the forward propagation. And we know that the another important aspect of the neural network is backward propagation, and that we would kind of build in the part where we would build this training loop for our model. So before that, we kind of need to define some hyperparameters, kind of say like what kind of loss function and optimizers that you need. So let's work on that. So let this part is, let's say, initialize the, or maybe first we have to create the hyperparameters, right? So I'll say this as define hyperparameters, and here the first hyperparameter is input size. Basically not just hyperparameters, but like all the parameters that we would need. So let's say that the input size is going to be the number of features, right? So the number of features is xtrain.shape. It's going to take the value 1. So when I say xtrain.shape, it's nothing but this is my xtrain shape 455, 30. So xtrain.shape of 0 is this value, xtrain.shape of 1 is this value. So I'm going to pass this 30 here. So that's what we are taking, xtrain.shape of 1. And my hidden size, let's maybe take 64 neurons in this case. You can also take like 32 neurons or 128 neurons, anything of your choice, but I'll just go with this 64. And output size, I'm going to give this as 1. This is because I'm having a sigmoid, so I don't need two neurons, but it's just a single neuron that would give the value between 0 and 1. And if the value is greater than 0.5, I'm going to say that it belongs to class 1, and if it's less than 0.5, I'm going to say it's the value is, I mean the class is 0, right? So it's basically like the output of a logistic regression. So based on that, we would kind of map it to the classes. So I'm having like one neuron that would give the value between 0 and 1, and then you can again set some learning rate. So I'm just going with 0. Let's say 001. You can also try with different things, do some hyperparam tuning as well. You can do this maybe manually first and you can check it out. And let's say number of epochs is equal to 100. So this is like a smaller data set. You can also check with smaller number of epochs to anything of your choice here. So I'll run this. So we have like we have the hyperparameters like learning rate and number of epochs, and then we also have the parameters like the input size, hidden size, output size, and so on. So the next step is we are going to initialize this model. So I'm going to say initialize the neural network, and we also have to move it to the GPU, just like the way we have moved the PyTorch tensors to the GPU. So here I'll say model is equal to neural net, and within this we need to pass the parameters. So the parameters it's going to need are your input size, hidden size, and your output size, right? So we need to pass those as well. So here we say input size comma hidden size, and finally we have our output size. Okay, and then we need to move this to device. So to device, so we are moving this to CUDA, or let's say the GPU, neural net to device. Okay, neural net is not defined. I think I didn't run this cell, that's why. Okay, so we have this one, and then we have to define the loss here. So define loss and the optimizer. So we kind of call this as criterion, again the same loss that we have. So I'll use this term criterion itself dot BCE loss, which is basically your binary cross entropy loss, and this is the one that we would use in logistic regression as well. So I have to check, I kind of forgot, but yeah, I think that's like the binary cross entropy loss. And then we have the optimizers, right? So let's call this as optimizer, and optimizer is equal to optim. So if you remember, we have imported this torch.optim as optim. So I'm saying that optimizer is equal to optim dot Adam. So we are going to use the Adam optimizer, which is again the widely used one, and the parameters that we are going to pass are the model parameters. These are the steps like where you're creating this and kind of like a step happens to optimize your parameters and your bias and so on. So you have this model parameters, and then you also pass your learning rate as the parameters LR. So these two are enough. Okay, so we have our model dot parameters and learning rate. So basically you have this forward propagation, and in the step of backward propagation all your weights are going to change, right? So that's what will happen here. So we are mentioning this loss and optimizers. In Keras we would do the same thing, defining your loss and optimizer in model dot compile step. It's again similar to that one. And the next step is we can now move on to the model training step, where we kind of have this for loop and say like what are all the sequence of steps that should happen. So here this part will be training the neural network, training the neural network. So here I'm going to say we can create a comment here as well, training the model or training the neural network, whatever. So here I'm going to say for epoch in range num epochs. So here we have defined the number of epochs, right? So this one, number of epochs is equal to 100. So here, again in Keras we use this model dot or sequential dot this thing dot fit, right? But here we need to kind of build a loop for this. So for epoch and range number of epochs is when your entire data set has gone through the model for this forward propagation and backward propagation is what we call as epochs. So for epoch and range of number of epochs, it basically this for loop runs for 100 times, and here I'm going to say model dot train. So this is an interesting step. So model dot train basically kind of puts your model in training mode. So here you can see this help section, right? So whether to set training mode or evaluation mode. So later we will use something called as model.eval. So that would basically put your model in evaluation mode. So the purpose of this is when you are in training mode, the model should learn from the data. So it should optimize your weights, or it should change your weights and bias depending on how it's making the prediction. But it shouldn't do that in evaluation. So in evaluation, you have a trained model and it's going to give you a predicted value, right? So these are the things where these are things why we need to set this. So here we are saying that the model is in training mode, and then you can kind of do your training, learn from it, and optimize your parameters. So here I'm going to say optimizer dot zero grad. So this is an interesting kind of step. So all this kind of happens in Keras and TensorFlow as well, but all these are implicit in Keras. So that's why we call that as a library that gives like high-level APIs to train the model. Again, it's easier for beginners, but again, we can't customize it a lot. So that's like the downside of this. So we have this optimizer. I have a spelling mistake here. Okay, so we have this optimizer. So zero grad. So what it does is each time the batch is passed it's kind of resets the gradients to 0. So if we don't do that, it's kind of do something called as this gradient accumulation takes place. So we kind of reset the gradients like each time of this, basically each time of this epoch. So we have this model dot train and optimizer dot zero grad, and then we have this outputs is equal to model of x train, and this is where you're basically predicting the values for it. So this is your training data, and when training happens, we know that it passes through the neural network, and our neural network gives out a value, right? And that's what happens in this particular step. So when you call this output is equal to model of x train, so model is your neural network, so it automatically calls this forward function. So that's what basically happens here. So you don't need to explicitly mention calling the forward pass, but that's what happens when you say model of x train, and then you kind of calculate your loss, which is equal to criterion, which is the variable that we have created here. So it should be loss is equal to criterion output. So we know that loss function basically compares your predicted output to your true label and find how distance your predicted value and true labels are here, right? So you need to pass your y true, I think it's white train in this case. Dot view. This is again, it's a simple reshaping that we need. So the criterion thing expects the model in this particular shape. So we are passing this white train dot view. This is just like a reshaping thing, like nothing complex in this. So we have this loss is equal to criterion, and then the next step is we have this loss dot backward. So this is where your backward propagation happens, and we would kind of change the model parameters. So here I'll say optimizer. We can copy this. So optimizer dot step. Okay, so your updation of your weights and your bias, all those things happen. So this is basically your training step. So we are running this for this many number of epochs, putting the model on training mode, and each step we are kind of zeroing the gradients, and we are getting the prediction for the training data, and then calculating the loss function with the predicted the outputs that we are getting and the y train, and then calculating this loss function here, and then we have this backward propagation step and the optimizer step where it updates the weights and bias. And this is all. So once this is done, you can you have your trained model within this model, and you can evaluate it. But if you want to log the performance of the model, you have to write some lines of code in order to print the accuracy as well. So here I'll say calculate. Again, I hope by this point you know like how all these things are automated in Keras, so we don't have to worry about all these things. So it automatically prints the loss and accuracy at the end of each epoch, but we have to kind of do this in PyTorch. So let's say that calculate accuracy with torch.nograd. Again, this is like we just need to find the accuracy. While predicting it, we shouldn't update the weight, so we are not going to have this gradient over here. So that's why we say that with torch.nograd, where it basically, as you can see, so saw this help thing here, so it won't update your weights, or it won't kind of worry about the gradients. So gradients are not updated, so that flag is turned on. So that's what we are doing with this torch.nograd. And within this torch.nograd, I'm going to create this variable called as predicted, which is equal to outputs. So we know that our output is going to be a single value because we have only one neuron, so it's going to give out value between 0 and 1. So here we are getting this predicted is equal to outputs dot round. So a value is greater than 0.5, it would turn that to 1. If it's less than 0.5, it would turn that to 0. You can, let's say you want to increase this threshold to 0.6, you can manually do that as well. So instead of this rounding, you can put a if condition that would do that particular conversion. And then I'll say, so here we need this count of correct predictions. So I'll say a simple step of predicted is equal to white train dot view. Again, we do this reshaping minus 1 comma 1, and then I'm kind of converting this to float dot sum. Basically, in this step I'm counting like how many correct predictions are there. So when I check this predicted is equal to white train view, so again, don't worry about this reshaping. This basically counts whether, like, I mean, how many predicted values are the same as the white train, and then we are kind of finding the sum of it and storing it in correct. So this would give you the number of correct predictions, and then in order to calculate the accuracy, you can say accuracy is equal to correct slash white train size. White train size is your, I mean, the entire size of the data points. Let's say that you have 100 data points or 115 data points, so you divide the correct prediction by the entire number, you would get the accuracy, right? So that's what we are doing. And then we can, let's say I'm not going to print the accuracy and loss function in each step, so I'm going to print at every 10th epoch. So it will be printed in 10th epoch, 20th epoch, and so on. So if you are, let's say, having 10 epochs total and you want to print it at each epoch, you can rewrite the code in that way as well. So this is basically for logging your performance. So let's say that if epoch plus 1, again, this is because your number starts from 0, so I'm putting plus 1 because so that the count here is like from 1 to 3 and all the way up to 10th epoch. That's why it's like a simple thing. So we have epoch plus 1 percentage of 10 is equal to 0. Again, this is not complex, it's just like simple operation where we kind of get the reminder. Basically the model is operator. So we basically check, we take this number divided by 10 and check if the remainder is 0. If the remainder is 0, that means it's divisible by 10. So it kind of, this condition gets satisfied in 10th epoch, 20th epoch, 30th epoch, and so on. So that's the idea. You don't, I mean, I'm just complicating things, but yeah, that's the idea here. So this if condition would run at every 10th epoch. So in every 10th epoch, I'm going to print these things. So we have epoch number. So epoch, let's say epoch plus 1. Let's put an F. Okay, F is already here. So let's say epoch of epoch plus 1 slash number of epochs. So the number of epochs is basically 100, right? So you will understand like when we are printing it. So don't worry if you are not getting this. And the next one is I need to get the loss. So loss, you can get it from this loss dot item. So the loss, the one that we have created here. So you can just say loss dot item, and you can just say like how many decimal points you want. Let's say I want three floating point values, and then we have the accuracy, and this accuracy we need to print it, the one that we have calculated here, right? So accuracy, let's say accuracy dot item, we're going to multiply it with 100 to give the value in percentage, and let's say that we need it in 2 decimal values dot 2f, and finally we can just put a percentage symbol here. This is just like some string concatenation thing, just like a complex way of doing it, where we are basically printing the number of epochs. So 10th epoch would display this as 10 by 100th epoch, and what's the loss function at that point, what's the accuracy at that point. Similarly at 20th epoch, 30th epoch, and so on. So if we run this, we would get the epoch number, loss function value, as well as the accuracy at 10th iteration of this. Let's run this, and this is where the training actually happens. As no attribute sum. Okay, I did something wrong here. So it's float dot sum white train dot view dot float. Okay, I missed the parenthesis here. Okay, let's run this again. We'll initiate this model again. So this is what we kind of built using this square bracket thing. So it says at 10th epoch out of 100th epoch, your loss function value is 0.56 and your accuracy was 87, and it kind of went all the way up to 97.36. So that's what it means, and the loss function value decreased. So this is what we have logged using this print statement. Okay, so this is how we kind of train our model with this 100 epochs, and the last final step is evaluating it. So similar to this training while loop, we can kind of calculate this model's performance as well. So maybe we can evaluate our model on the training data set as well as the test data set. So here I'll create something called as model evaluation, and here we need to pass our, maybe for training data accuracy you can pass your x train and y train, and for test data you can pass your x test and y test. So maybe first I'll evaluation on training set first, so that we can make sure if overfitting, underfitting, all those things are not happening. So the first thing is put your model in evaluation mode. So previously we put it on training mode, right? In evaluation mode, when you pass your data, it's not going to change the gradients or change basically your weights and bias. That's the idea. Here also we have to say with torch.nograd. So here we are not kind of focusing on calculating any gradients, updating them. Gradient, you know, right? So it's used basically to update your weights. So gradient is like how your loss function is going to change when a particular parameter changes. So we don't have to do that when you're finding the accuracy or your evaluations. So that's why we are putting this on nograd. And here I'm going to say outputs. As you know that outputs basically call your output from the model. So I'll say model dot, okay, model extrain. So this would give the value, put this data through the forward pass and give the value. And again, this is getting the prediction out of this. I think I use this same thing over here. So prediction is equal to, I can use this same accuracy. and use this over here. Okay, and this is the number of correct prediction. All the things are okay. And train view float. So we have this outputs isn't predicted. Okay, so this is cool. Let's run this and check if, I mean, like, what's the accuracy that we are getting. So we have this accuracy score over here, and maybe we can use this thing as well. Yeah, we can use this to convert it to percentage, so no issue. So I'll just say print accuracy on training data. So that is the same thing, accuracy dot item. This thing can be used to just convert it to convert it in percentage and add a, okay, go to this curly brackets and add a percentage symbol here. So let's maybe run this and check if this is working. Yeah, the accuracy on training set is 97.36, the same value that we got in the last epoch, right? So yeah, it's working. And let's also calculate it for test data. So for test data, you need to convert this X train to X test, and for Y train, here it should be, we have to compare it with Y test, right? So this should also be the case here. So this is to, yeah, count the items. Let's run this and check what's the accuracy on this data. The accuracy on test data is 96.49%. So this is how you kind of take a data set and train your neural network. But the key thing is doing this on PyTorch instead of Keras. So it may seem a bit different because everything was easier in Keras, but again, you have to learn either TensorFlow or PyTorch. It's going to be really helpful when you're kind of building these complex neural networks, so that you have this liberty and freedom to customize the network as you want. So that is the idea for this. Maybe I'll just give you a quick walkthrough of what we have done, just like a quick recap. So first, we are importing all the required dependencies. So these are like the basic standard things. The critical things here are your PyTorch library, NN from this PyTorch thing, and then we also have this optimizers. And here we are configuring our device to use CUDA, and the data collection step, pre-processing, all these usual things that we used to do. And the other interesting step that we did is convert all this NumPy arrays to PyTorch tensors and move that to GPU. And the next part is model architecture, where we are using this inheritance kind of concept, where we inherit the, let's say, parameters and the methods from the CNN.module to the custom class that we are creating called as neural net. So mentioning all the parameters that we need to pass, which is the number of input features of the input size, the number of neurons in the hidden layers, output size, and so on. And then you have a fully connected layer, ReLU, fully connected second, fully connected layer, sigmoid, and so on. And then you have a forward pass, and then you have this hyperparameters. All those are set up here, and then we are creating an instance of this neural net model, compiling our model with the appropriate loss function and the optimizers. And finally, we are kind of creating this training loop where it runs for, let's say, 100 epochs in this case, and at each at 10th epoch we are printing this loss, accuracy, and so on. Finally, we are putting our model in evaluation mode and getting the training accuracy and testing accuracy. So that's it from my side, and I hope that you understood all these things completely. So please try this code out and learn from it. So that's it from my side, and I'll see you in the next upload. Thanks for watching. Hello everyone, I'm Siddharthan. This is the 9th project video in our deep learning course, and in this video let's understand how we can build a handwritten digits generator using a deep convoluted generative adversarial network, commonly known as DC-GANs. So before going into the coding aspects of how we can build this GAN and how we can train it, first let's understand what is meant by a GAN and what are all the building blocks of it. So in a generative adversarial network, the two main aspects are a generator and a discriminator. The work or the purpose of a generator is, given a particular random input. So random input, when we say, it's what we call a latent noise, where it contains some numerical values, and getting this as the input, it would generate an image. that closely resembles the real image. So let's say that in this case, we are the dataset that we are taking is handwritten images, right? The MNIST handwritten datasets, and this generator should generate the image that closely resembles the handwritten images. And then we have the discriminator that kind of looks at both the real image and the image that is generated by the generator. So this doesn't know which image is which one. So it doesn't know which image is coming from a generator and which image is coming from a real image dataset. So it has to look at both of these samples coming from real images and generator, and it should say that whether it is a real image or fake image. So ideally, the discriminator should say that all the images coming from this sample from the real images are real, and all the images coming from this sample from generator are fake image. So in the training of the generative adversarial network, the key factor is training both the generator as well as the discriminator simultaneously, and both of these kind of collides. So the generator tries to build images, generate images that is close to real image, and it tries to trick the discriminator, saying that, let's say, the discriminator won't be able to say that this is a fake image. So it should reach a point, the generator should reach a point where the discriminator cannot distinguish between a real and fake image. So that is like the core concept of this generative adversarial network, where again we are building this generator that is as good as building images that resembles the real data set. So I hope everyone is clear about the conceptual aspects of this. Now let's understand how we can build this in Python. So the main part of this is building two separate neural networks for generator, where it takes this random input, builds an image, and the other one is like just a classification neural network that classify an image as real image or fake image. So for this, we will be building this code in TensorFlow. So we'll be using a bit of Keras, but it will mostly be on TensorFlow. All this training loop that we do, maybe at a later point I'll make a video on how you can build this DC GAN in Keras, so that it can be a bit slightly easier. But yeah, in this video it's going to be like mostly TensorFlow. So I have this Google collaboratory environment, and I have all this code, and I'll explain this code line by line to you. And GANs actually require stronger computation power, so it definitely needs a GPU. And in this case, the image that we are taking are smaller images, so we will be working with 28,28 pixel image, which is like, we know that it's like a really small image, and we have one channel which represents the grayscale image. You can also build GANs that can generate larger images with RGB channels, but you will need like a larger GPU. So for now we are just going with like a smaller data set, so it's like computationally heavy process. So open your Google Colabs, and share you the link of this Colab notebook as well. Go to the runtime, make sure that you are connected to a GPU environment. So CPU is going to take forever, so make sure that you are on GPU. So I'll save this, and I'll run the first cell where we are installing the required libraries. So we are installing TensorFlow image, I want TensorFlow docs. So these are the things, and we are importing the required dependencies. So we have this glob. So this glob library is basically used to match the patterns. So it's when you give a directory, so it scans through the list of files in the directory, and let's say that we give a pattern. So extract all the files, or give a list of files that start with the word image or ends with the extension .jpg. So it would return the list of all the files with that names. So it's mainly used for that particular pattern matching thing. And then we have image IO, used for reading and writing of images, and a matplotlib.pyplot as PLT. So this we'll be using in order to display the images generated by the generator, and so on. And then of course we have the NumPy library, used for some scientific computation of arrays, matrices, and so on. And then we have OS library in order to navigate to directories, create directories, and so on. And then we have the deep learning framework TensorFlow, which we'll be using for building those networks, and kind of creating this training step, training loop, and so on. And then from TensorFlow.keras we are importing the layers. So from this we'll be importing layers like convolutional layers, convolutional 2D transpose layers, and so on. I'll explain you later like what all of these means. And we also are importing time library to kind of find how much time it takes for each epoch of training. And then we have IPython. So from IPython we are importing display. So this is used to display the images that we are getting like at the end of epoch. So basically for displaying the images. So that's about importing the dependencies. So I'll run this cell, The next step is loading the data set. So as I said, here we are working on generating handwritten digits. So for that we will be using the MNIST dataset from TensorFlow. So the main concept, or I mean the main outcome of this video is not to generate handwritten images, but to understand how we can build a GAN, so that you can use this code to build a GAN for any images. Let's say that you want to generate car images or medical scan images, so you should be able to do that. So that's the main purpose. So let's understand the process of doing this. So in this case we are going with this tf.keras.datasets.mnist load data. And if you can also, instead of this, you can read it from a directory where, let's say you have thousands of images, so you are going to load that to a numpy array, and let's say you're going to train your GAN. So you can do that as well. You just have to replace this particular line of code. So the tf.keras.datasets MNIST load data. So this basically downloads your data, and we are going to save that to this two tuples. So this is the first tuple and this is the second tuple. So this basically returns two tuples. The first tuple is for training data set and the next one is for test data. But again, here we are not working on classification, so we actually don't need the test images. So the training images are sufficient for us. So the first element of this tuple is the training images, the numpy arrays, and the second element is the labels. Again, the labels are also not required for us. We are basically interested in this images only, so that we can generate images that are similar to it. But this is how you can load it. So we will be later using this train images. So that's about this line. And now we are going to do some processing on this image. The first step is kind of reshaping this. So here I'll create another cell and I'll show you what's the shape of this train images is. So let's say train images dot shape. And here the output that we are going to get is 60,000. So we have 60,000 images, 28 into 28. So we have 28 image with 28 pixel height and 28 pixel width. But we also need another critical information, which is the channel. So the number of channel here is 1, right? So we need to reshape this array such that we are getting this shape as 60,000 comma 28 comma 28 comma 1. So we have this train images. So train images is equal to train images dot reshape and train images dot shape of 0, 28 comma 28 comma 1. So when I say train images dot shape of 0, it's nothing but 60,000, right? So I'm kind of reshaping this just by adding another channel. So your RGB image would have 3 channels, red, green and blue, but again grayscale it's a single channel. So that's what we are doing, and we are changing all the elements present in it. So to float 32. So we can show this too as well. So we have train images. When I print the first element of this, so we are seeing the value, right? 28 comma 28 array. So I'll click the show data. So this is the data. So if you see, this is actually in the form of integers, right? So this is a grayscale image and we are kind of seeing this integers, but I want to change this to floating points. So I'm saying as type float 32. So this again is useful because when you have all those values in this floating point, it also helps in your training. So it kind of stabilizes it a bit. So it's like slightly better if you have this as floating. And later we will also do this normalization process as well. So it's better to have this as float. So this step is reshaping this such that it has this channel information and also the data points is floating. And once we do that, the next step is normalizing it. So you probably would know this at this point. So normalization is in an image, right? All the pixel values range between 0 to 255. In a grayscale, 0 means black and 255 means white, right? So 255 white and 0 black, and all the other values are different shades of white or black. You can think about it that way. And when we train a model, it always the model is able to work well. The neural network, if you are working on a classification neural network, convolutional neural network, it is going to predict well if your data is like normalized. When I say normalized, we scale the values between 0 and 1. So instead of between 0 and 255, we normalize it, we scale it between 0 and 1, right? Just by dividing it with 255. But in the case of GANs, it's kind of like it's observed that the network kind of performs well if the values range between -1 and +1. So instead of 0 and 1, here we are going to have the data between -1 and +1. So for that, this is the formula. So we have the train images -127.5. That means like all the individual pixel value. So we are subtracting 127.5 and dividing it with 127.5. So your 0 would now become your -1 and your 255 would become +1, and all the other values in between would be between this two, -1 and +1. So that's the step here. And you can again check the shape as well. So we have train images.shape. So I'll show it to you. So here we would have 60,000, 28, 28 and 1. And let's also print the first element here and see like how the value is. So we have -1, +1. So -1 is basically 0 and all those values. So that's how we are reshaping this and kind of saying this. So this value is again 0.06, which is again between 1, right? So this is how we are scaling this, normalizing this thing. So I can delete this particular cell. And the next step is we are creating two variables. One is called as buffer size 60,000 and the other one is batch size. So buffer size, so this is actually used in order to shuffle our data. So the main aspect here is, right, or the purpose of doing this is, let's say this is a MNIST data set, and let's say the first 10,000 images corresponds to the digit 1, the next 10,000 images corresponds to digit 2, and so on. Let's say that there is an order. We don't want our model to look at this order and make predictions based on that order. So for that, we are making sure that the data set is perfectly shuffled so that it doesn't kind of look at the order and make a prediction, and basically your model is not influenced by the order of the image present in the data set. So for that purpose, for shuffling, we will later use this buffer size. And then we have the batch size. Batch size is again a critical, very critical aspect in a neural network training. It's one of the hyperparameters. So you probably would have seen epochs and batch size together. So batch size is, so in a neural network, how a training would happen is, right, so I can maybe show this to you. So we have a neural network, and when we say training is happening, so one main thing happens. So we have this forward propagation and backward propagation. That means your data propagates in this forward direction from the input layer to the output layer. This is what we call as forward propagation, and it comes back, and that's called as backward propagation, right? And when the backward propagation happens, your weights kind of gets updated. So it goes here and your output layer gives a prediction, and we compare it with the true values and say that no, you're not making good predictions. Now the model updates its weight, so that this process actually continues. So we continuously updates the weight so that our model can make like accurate predictions. So that's the idea. And we say this one forward propagation and one backward propagation, right? This happens for each batch. So you have two, when I say 256, that means each batch has 256 images. So all these 256 images will go through this forward propagation, and when they come back for backward propagation, the weights are updated, right? If you have a 32 batch size, it's going to go in this direction and it would come back, right? So if you consider one epoch, in one epoch, all the batches should go through this forward propagation and backward propagation, and the updates would happen at end of the processing of each single batch. So here we have 256, right? So that means divided by the 60,000. So now you know that how many times this backward propagation and forward propagation kind of happens. So that's the idea. So you can call this as a training step. So your data flows in this direction, forward direction, comes back. So let's call this as a train step, right? And at one train step, during the backward propagation, your weights are updated. So at each train step, one batch is processed, okay? And in order to find the number of train step, you can just divide this 60,000 by 256. Let's say that we have this 60,000 divided by 256, and we have, let's say, about 234. So almost you have 234 number of times this forward propagation and backward forward propagation happens to complete this 256 batches, and these many times your weights will be updated. Again, this would change if you have a smaller batch size and so on, but this is the information about the batch size. And here is like an interesting factor about it. So you can't just go ahead and use any batch size that you want, because if you are using a larger batch size, right, that means you need like a larger computation power. So if I'm using 256, I need like a larger GPU, and if you increase the batch size, your training is going to happen faster. In this case, I'm working with a dataset that has smaller images, 28, 28, so I can use a larger batch size. But if you are working with a large image, epochs or more, then you probably have to reduce the batch size. It's kind of like we need to do this empirically, try to find which is like the proper value. Again, for this case 256 is okay, so it's not going to take that much computation as the images are not that large. But in general, as I said, training GANs are like pretty computationally heavy. So here, that's about these two variables. One is buffer size 60,000 to shuffle the data, and the other one is batch size is uh, creating this 60,000 as 256 individual batches. And usually for batch size we use 32. That means 32 images in batch, not just images for any data point. It can be a numerical data too, right? So it's like 32 data points in one batch. So we can use 32, 64, 128, 256, something like that. So I'll run this. And the next step is we need to shuffle the data and batch it. So for this, we are using this tf.data.dataset from tensor slices train image. This is one step, this is second step, and this is the third step. So we are basically doing 3 steps here. The first is we are creating a dataset object. So tf.tensorflow.data.dataset. So this create a dataset object, and this is because this dataset object is it's basically a better way to pass the data to your model, right? So that's why it's used. So we are creating this dataset from this tensor slices. Tensor slices is nothing but this training images that we are going to pass. So this creates this dataset object, and after that it's going to shuffle it. And when we give this shuffle size of shuffle, it's basically the buffer size of 60,000. That means the entire size of the data, it makes sure that the data is properly shuffled. It's not like only specific number of data points are shuffled. So some data points are still like following some chronological order, so that some order that won't be there. And you put the buffer size as the same as the size of the data set. And then we are also using dot batch in order to create batch 256 batches of 60,000. So here we are giving this batch size as 256. So we are creating the 60,000 or batch of the 60,000 and storing it in train data set. So you can try printing this. I'm not sure you would get some proper information, but we can definitely check. Oh, I need to run this first. Sorry. Train dataset has no attribute shape. Okay, so yeah, the dataset object probably doesn't have it, but this is how it would be. So it would have like this 256 batches, and you have 28 comma 28 pixel, and at one channel and so on. So this is like probably like a single batch dataset information, but yeah, that's about it. So we have this train dataset. Now let's move on to the other aspect. So now this would act as your real image, or I can come back to this slide. So we have this real image, right? So this is what we represent by this train data set, right? And then now we would kind of use this generator in order to generate random images, or sorry, the fake images from this random input. So that would be the next step. So here we are going to create a function called as make generator model, and this function would return the neural network that is nothing but our generator. And later we would also create another function called as make discriminator model. Again, that would return the neural network for our discriminator. So as I said, the purpose for this generator is to get random input, basically random numbers, and generate an image out of it. So that's the purpose of this. And what we would give here is something called as a latent noise. So this is something that we would create. I can show this to you. It's nothing but a normal distribution data. Let me run this maybe. So we are creating this using tf.random.normal. This is going to be some random numbers, but not just any random numbers. The numbers are going to be normally distributed, or you can call this as a Gaussian distribution, where it follows basically you have this bell-shaped curve. So I'm creating one array, and that one array has 100 elements, right? 100 numerical values that follows a normal distribution, and then I'm storing this in the noise. So this is what I call, or this is what I have mentioned using this random input. And from this 100 values, right, it's just, you can think about this as a vector. It is like a single dimension array. From this, it should upscale this data, upscale this numerical values to build a two-dimensional image that, as the 28 comma 28 pixel and one channel grayscale image. So that's what we are going to do. I can print and show you this image. So when I say print noise, it would, I think it would say 1 because it has like one array, right? So it has one array of 100 elements. So you can say, when I say print length of noise, it should say 1. That means it would say that there is only one array. But when I say print noise of 0, this would give like this, yeah, 100 elements. And now I can make sure that it has actually 100 elements, right? So this is what we call as this random input that we are going to pass to the model. So here we are having this make generated model and the input shape is 100. So this is what we kind of like building this 100. Again, it's not like you have to use only 100. It's this step is also like kind of an empirical. There are like some implications, so it can also affect how well your model is handling overfitting and other issues are there, but it's mostly empirical, trial and error kind of a thing, where you run it with this number, see if you're kind of getting a decent model, and you kind of change it and then see like what's like the best number for your particular use case. That's again empirical. So we have this define make generator model is equal to tf.keras.sequential. That means we are going to stack the layers sequentially or linearly. So we are initiating the model with tf.keras.sequential and model.add layers.dense 77256. So first we have this dense layer, densely connected layer 77256. You can multiply this to get the actual number of units, and use bias is equal to false. So when we say use bias is equal to false, that means we are explicitly mentioning that we don't want any bias value. And again, this kind of also observed in the case of GANs, that your model kind of converges faster, performs well when you don't have any bias values. Convergence is basically the ability of the model to kind of get the optimized weights. So again, we call this as global minimum, right? Global optimum, whatever it is, global optimum, right? So where after this point, you can't improve your model significantly. So at this point, your loss won't decrease significantly. So you have like the perfect weights and bias, right? So that's what is called as convergence. But when you don't have bias, your convergence is going to be faster and the model is a bit efficient. So we are saying that use bias is equal to false. It's not kind of a thumb rule, but you can always, it's preferred to have this bias is equal to false when you are creating this generated model. And input shape, we are going with 100 latent dimension that we had, and then we are adding this model.add ts.batch normalization. So we are getting this output from this dense layer, right? And we need to make sure that this output is normalized, because again, this would change the range in which the data is coming out. So it's like you have a layer, and from this layer some output is coming out of it. So we have to make sure that the data is like normalized. That means like the range is like proper. This also helps in like faster convergence, and there is also another issue called as covariate shifting and so on. So let's not go in detail about all those things. Let's discuss about it in detail when we discuss this convolutional neural networks, all this neural networks in detail. But just for now, understand that when we move from one layer to another layer, it's better to normalize this data that's coming out of one layer. And again, this happens only in the training. When your model is on inference mode, or basically when you're getting predictions out of this batch normalization won't actually happen. So that's one thing about it. And then we have this model.add layers.leaky relu. So you probably would know what is a relu activation function is. So I can maybe show it to you in a graph. You have this relu activation function. So it's nothing but if your input value is kind of greater than 0, it's going to give that same value. So you have a layer, some output comes out of this, and we apply an activation functions to this. So we apply sigmoid when we want the value between 0 and 1. And these activation functions are the factors that add this non-linearity factor to our model, so that it could understand complex information. So it's not limited to understanding linear relationship, but also non-linear relationship. So relu is one of that, where if the value is greater than 0, it would just give out that 1 as the value. So here, let's say x is this input and y is the output that we are getting. If the x value is greater than 0, it's going to give out the same value. If it's 2, it's going to give value 2. If it's 100, it's going to give the value as 100. But if it's less than 0, or in other words, if it's a negative number, it's not going to give you the negative number, it's going to give you the 0. So there is a cap on the lower extreme, which is 0. So that's about ReLU. But leaky ReLU is another interesting variation of this ReLU, where it has like slightly smaller negative slope. It's not that much, but for negative numbers it kind of allows a smaller slope, right? So this is again works a bit slightly better than ReLU in some cases. So we are using this leaky ReLU here. So this is our first dense layer with proper batch normalization and leaky ReLU, and then we have this model.add layers reshape. So we are reshaping this output coming from this layer, so that we finally end up with this 28 comma 28 comma 1. So this happens in a step by step process. So here we have this 7 comma 7 comma 256, and then we have this assert. So we also have this assert condition that basically checks or makes sure that this shape is none 7726. This none basically, again, as I mentioned there, it takes the batch size later. If you are passing like 32 images, this 32 images should be considered here. And I forgot to mention, this code is actually it's this is the code present in TensorFlow's documentation of DC GAN, deep convoluted GANs. So I didn't add anything much to it, so you can kind of find this code there as well. So yeah, I didn't add anything new, so I just wanted to make that one clear, right? So we have this asset condition here, and then we have this con 2D transpose layer. So this is an interesting one. Not sure if you have heard about this, but you definitely would have heard about Conv2D. So convolutional 2D layers that is used in the convolutional neural networks for this, which is again used for this binary classification and so on, where these layers are kind of really helpful in order to find these edges, find these features of present in the image, right? The convolutional 2D transpose works in the different way. So there we have this kernel size and so on, filters through the images, find critical information. But this is more of a opposite of how that works. So this would upscale the data coming from, let's say we have this single vector, single array, one-dimensional data. So we are going to upscale it. So this kind of do this convolutional 2D transpose operation where we are upscaling it to multiple dimensions, so that finally we would reach to this 28 comma 28 comma 1. Again, you don't have to worry a lot about the numbers that are kind of used here. So later we will understand what's the best way to arrive at these numbers and so on. But again, the main purpose here is just to understand the working flow of the GANs, working flow of the generator and discriminator. So don't worry if you are not like sure why these numbers are used. So that's okay. You can actually change these numbers to make your model better too. This is like a very simple generator model, just that works well for this smaller images, right? So if you're, let's say, working with the image of a different size, you probably have to change this numbers a lot. So you need, like, let's say you're working with 100 into 100 image, so you need to change this and kind of change all these layers such that it's proper for your particular image. So this is kind of customizable depending upon the data set that you are working on and the use case that we are working on. In this case here we are having like 128 units, 5,5 as this size, and then we have the strides and so on, padding. So we have this max padding and the same padding, bias as false and so on. So these factors are used. Again, we don't have to worry about this that much. So we have this filters, right, the units, and then we have the kernel size strides and so on. And then we have assert, making sure that it has like these many things. And here if you see this, the channels that you are seeing here, output of this convolutional 2D transpose is equal to the whatever the number of units or the filters that you have in your particular layer. So here you have 128, so the output channel is going to be 128. And here we are having these strides of 2,2, same padding. So here you are getting the 64 units, the channel is going to be 64 and 14 14. Here the units is 1 and you are getting the channel is 1 and so on. So this is the architecture that we are currently using, where we have 3 convolutional 2D transpose layers, and the final output is 28 comma 28 comma 1. So if there are like 10 images in a batch, we would output like 10 images, right? So in a single batch, so you don't have to worry about this one. So we have 28 as height, 28 as width, and 1 channel grayscale images, and return the model. So basically this make generator model function would return the architecture for your generator. And then in this place we are going to just pass some random input to our model and see if it can generate an image. So using the untrained generator, that's one important thing. So we haven't trained our generator yet, we haven't compiled it with a loss function, we haven't compiled it with an optimization and so on. It's just like a simple generator neural network that if you give a 100 input value, it would generate an image. but you wouldn't know what an image is. It's like a random mix of white and black pixels. So that's what we are going to do. So I'm kind of initiating this make generated model in the variable called as generator. I'm creating this noise vector using this tf.random.normal. So normally distributed random values, single array of 100 values, and then I'm passing this. So we have this generator, right? So I'm passing this through the generator, which is this function basically, right? So we have this generator is equal to make generator, and I'm passing this noise. And the important thing is I'm saying training is equal to false. That means when training is equal to false, it's not going to update the weights. So it's just going to, it's like giving a prediction. It shouldn't update the weights in this case. So if you are working with neural network or even in machine learning thing, right? So you train the model, and when the training happens, you update the weights and you evaluate the model, and while evaluating you wouldn't train the weights, you just get a prediction out of this. So similarly, we are saying training is equal to false. That means, you know, we are not going to update the weights. And finally, we are storing this generated image coming from this generator in the variable called as generated underscore image, and then displaying this with plt.im show grayscale, color map grayscale, and so on. Let's run the previous L2 and run this. So now we would see this image. So this is the random image generated by the model. So I mean, this is no way closer to our data set, which is MNIST digits, right? So we will come to that. So later we will set up this discriminator, let the generator know how you should generate the images, how it should be closer to the MNIST data sets, and so on. But this is at the start. So this is how an untrained generator would generate an image. Okay. So the next part is building the discriminator. And as I said, the purpose of the discriminator is given in image, it should say whether it is a real image or a fake image. If the discriminator is 100% accurate, it should say, if an image is coming from this real image dataset, it should say it's real. If it's coming from a generator, it should say it's false. It's a fake image, but we need to train both of these. Discriminator should not be weak, because if it's weak, right, generator can generate an image that is like really bad. It's not similar to real image, but discriminator can't say like it's a fake image. So discriminator should also be kind of stronger. It's like both of these trainings should happen simultaneously, and generator and discriminator trying to kind of, so this generator tries to fool discriminator, and discriminator tries to catches the fake images coming from the generator. So this is how this would work, and this is what we call as this adversarial way of training. So that's what happens. And as I said, discriminator is not as complex as a generator. This is just a binary classification convolutional neural network that would tell you whether an image is a real or fake. This is a binary classification, right? So we are going to label one class as 1 and the other class as 0. So let's see how we can build this discriminator network. So we have the function called as make discriminator model. Just like the generated model returning your neural network, this make discriminator model will return you a binary classification neural network. So we have this TF Kara sequential, again a linearly stacked sequential model.add. We have this convolutional 2D layers. We have the filters, kernel size, traits, and so on, padding same, and the input shape is going to be 28, 28, 1. Again, the same shape of the generated image, as well as the same shape of the the real image, which is this 60,000, 28, 28, 1. So it should be that shape. So input is this shape, and then we have this leaky ReLU as activation. We are also having dropout. Again, dropout helps you in making sure your model is not overfitting, so it turns off few neurons and so on. So you have another set of convolutional layers. If you want, you can add more too, but again, it should be again, the two models should be close to each other. So your generator should not be very complex and your discriminator is like very simple. So that shouldn't be the case. It should be like it should be like a level playing field, so that both can train in a good way. So that's one thing. So and then you have this flatten layer, and finally you have the output layer model.add layers dense, and this is just contains like one neuron. So if you look at this, if this is a classification problem, we would generally use a sigmoid activation function, right? But here we are not going to use it directly. So instead we are going to play with the loss function. So for binary classification, we usually use binary cross entropy. So we are going to use it. So instead of kind of putting this through a sigmoid activation functions, we are directly going to use the loss. And later we have this calling this function called as discriminator, make discriminator model, store that to the variable called as discriminator, and decision is equal to discriminator. So it basically we are passing an image to this discriminator model, getting a prediction. Which image we are passing is nothing but the random image that we generated from the untrained generator. Similarly, this discriminator is now also it's untrained, so it's just going to give some values. To run this first, okay. So it's going to give some values that's stored in this decision because it's not trained yet. And then it's the value is not between 0 and 1 because we haven't applied sigmoid to it, so we are getting this minus 0.0001 something. So this is what we call as logits. Logits are nothing but raw output coming from a particular layer or a neuron, so we haven't applied any activation function to it, right? So and the next step is we are going to set up the loss function and optimizers. This is a very critical step. Using this loss, we are going to give feedback to the generator. So again, as I said, this is a critical thing where only by this the generator know how well the model is performing, how well it's able to generate images that is close to images. So when the training happens, there is a constant feedback loop that runs between the discriminator to the generator. So let's say the generator generates 100 images, and we have all those 100 images here, and we take 100 images from the real sample. Let's say the discriminator is able to find this correctly, so it tells that these 100 images are real image, these 100 images are fake image. Then the generator has not done its job properly, right? The discriminator can easily classify that. Now this information is passed to the generator via the loss function parameter. Now the generator know, yes, I haven't done my work properly, so I have to update my weights and make sure that I'm generating good images. So this feedback loop goes on until a point where the generator generates good images, or until a point the number of epochs stop, right? So that's also like other way to look at it. So it runs for as many epochs and there is a constant feedback loop. So that's what you need to kind of remember here. So that feedback loop is given by this cross entropy, and this updation of weights, this improvement, model improvement happens through the optimizer thing, where it optimizes your parameters so that your loss function is reducing. So when a loss is more, that means your model is far from accurate values, accurate predictions. If a loss function value is less, that means your model is good at kind of predicting the values. In this case, when I say prediction, generators prediction is nothing but creating images, generating images, and discriminator prediction is predicting real and fake. So yeah, that's the term that I'm using. And we have this method returns a helper function to compute cross entropy loss. So we have this binary cross entropy, which is again usually used in binary classification to say how well a model is performing. And here we are saying from logits is equal to true, because we are not applying any sigmoid activations. We are just returning like raw inputs called as logits. So we are saying it's true. So we are storing this method of computing this cross entropy loss, binary cross entropy loss, to the variable called as cross entropy, which will be used later. And then we have two losses, one loss for your discriminator and the other loss for generator. If you think about it, discriminator loss is nothing but it's how well the discriminator can distinguish real image and the fake image, or how well you can also see this in a separate way, how well your discriminator is able to find real image. That is one part, and the other part is how well your discriminator can find fake images. So you have two losses, and then you kind of have these two losses, so that would be the loss for your discriminator. But generator loss doesn't have to worry about the real image loss, so it just need to look at the fake image loss and say that how well it's kind of able to kind of build this fake images. And that information, that fake loss, is also similar to the fake loss that you have here. So discriminator would have these two losses, but generator is, it's just a part of this loss, which is how well it can generate fake images. Let's see how this comes together. So discriminator loss, this method quantifies how well the discriminator is able to distinguish real images from fakes, as I said, and it compares the discriminator predictions on real image to arrays of 1. So we label the real images to 0. So let's say that in the sample we have 100 images, we label all those to 1s, and out of those 100 images, discriminator predicted correctly for 80 images. So you have 80 ones and 20 zeros. So it basically compares this 100 ones to the 80 zeros, just like the accuracy score thing that we do. So we compare that. So that's what is represented in the second statement. It compares the discriminator predictions, let's say of 1 or 0 or real or fake, on the real images to an array of ones. Let's say the real images are labeled as ones, and the discriminator's predictions on fake images, generated images, to an array of 0. So let's say that the fake images are labeled as 0. So we are just comparing it. So real loss is equal to cross entropy TF dot ones like real output and real output. So real loss, as I said, how well the model can find or basically classify real outputs, right? So for that we need a ground truth. Here the ground truth is your TF1's real. This is your true labels. This is your predicted labels. Similarly, this is your true labels for fake image. This is your predicted labels for fake output, right? So just understand this. Don't confuse real and true thing. So here we have two set of data points, two set of classes, and here this is the ground truth. So when I say TF dot ones, like it will create an array where all the values are 1 and it's the same shape as the real output. So let's say that we have TF dot ones like, right, and in this let's say that we have an array that has real output, right? So real output, that means let's say there are 10 images, and out of those 10 images the model says 8 are real, 2 are fake. So it failed at 2 data points. Let's say that TF dot ones, here I have an array that has 10 values. One, I have 5 over here, and I'll copy this and put another 5, right? And let's say this is how the model should have predicted it, but for last 2 data points, let's say it has predicted it as 0. Now when I say TF dot ones, like this is the array. You can think about this as the output coming from the model, so real output, where it should have been all ones, but it's 2 of them are 0. When I put this to TF ones, like it's going to create an array with the same shape as this one, but all the values will be 1. So as you can see, so we have an array that has 10 values, all the values are 1. So basically this TF ones like is used to create an array in the same shape as the attribute that you are passing, but all the values should be 1. Similarly, zeros would create an array same shape as this fake output, but all the values will be 0. So here this would be a ground truth because we know the real images, right? So this real output are the predictions made on the images coming from the dataset, the MNIST dataset, or the real images. So ideally all these images should have labeled as 1, but let's say the model was not able to do it. It's 0, 0. Similarly, all the images coming from this should be labeled as 0, but let's say the model was not able to do it. So here we have the ground truth as the first parameter, TF ones like in case of real loss and the real images comparison, and we have TF ones, TF zeros like in the case of fake output, where ideally it should have given all zeros, but let's say the model has given only 5 as zeros and 5 as ones. So that's the real loss and the fake loss, and we add these two and we get the total loss. So it's the ability of the model on distinguishing real image and fake images. So how well it is working for real images and fake images. So that's about the discriminator loss. So, and in the case of generator loss, that just it's cross entropy TF ones like fake output, right? So it's again how well the model is working in terms of generating fake images. So here if you see it, here it doesn't matter if you use ones or twos, because in this case you have two labels, ones and zeros, so that's why we are using it. Here we are using just ones for fake output, but here we use zeros, but it's immaterial because this is a separate loss and this is a separate loss. This is a loss for discriminator, this is loss for generator. So don't confuse this. Ones is coming with fake, here ones is coming with zero, so don't confuse. You have to look these two separately. So here the generator loss quantifies how well it was able to trick the discriminator. Intuitively, if the generator is performing well, the discriminator will classify the fake images as real or 1. Here, compare the discriminator decision on the generated image to an array of 1. So let's understand this statements. So generator loss, it kind of quantifies this. It puts a numerical value on how well the generator is performing. If it's performing well, that means the discriminator couldn't look at the image generated by the generator and say it's fake. So the discriminator couldn't do it. So it's kind of fooled by the generator. So that's where it should be added, and that information is coming to the generator from this generator loss, and that we are comparing it with the ground truth in this case, where and the output that is fake output, this output is coming from the discriminator. So let's say that discriminator says out of 10 images, 2 images are fake and 10 images are real, but in reality all the images are fake. So the generator is like, let's say 20% good, but it's not that good. So this information comes to it from the generator loss. Okay, so that's how we have to look at it. So the next step is we are done with the loss, and the next step is kind of working with the optimizers. And in Keras we have this model.compile where we pass this loss and optimizers and so on. But this training of GAN should happen a bit differently, where we are going to train two models simultaneously with all these flaws and optimization. So that's why we are kind of taking a different route. So this is not like as simple as a binary classification or a classification problem where you're training a single network, but that's the beauty about it, right? So it's like an interesting use case and interesting concept to understand. So yeah, going forward, so we have this generator loss and run this, and now the next step is setting up the optimizers. So here it's mentioned, right? So the discriminator and the generator optimizers are different since we will train two networks separately. So there is a feedback loop that goes in the manner of a loss function value, but these two networks, generator network and the discriminator network, are getting trained separately. So we are having separate optimizers. So the generator optimizes the weights of generator neural network, and the discriminator optimizes or changes the weights of the discriminator network. So in both the cases, we are going to use Adam optimizers with the learning rate as 1 e per e minus 4. Both cases, again, you can experiment it with different learning rates or different optimizers too. So no restrictions on that. And the next step is saving the checkpoints of your model as well as your discriminator. So again, for different epochs. So here the directory, we are going to create a directory called as training checkpoints dot training checkpoints. So we're creating this folder, and then we are joining this with the prefix of CKPT, short form for checkpoint. Again, it's not complex at all, just creating a directory, putting all those model artifacts there. So checkpoint is equal to tf.train checkpoint. So we have this function in TensorFlow itself where we are saving this generator optimizer, discriminator optimizers, and generator model as well as the discriminator model. So we are doing that. So while training, all these checkpoints will be saved for your model. So the next step is kind of setting up this training loop. Training loop is nothing but how your training should happen, when your loss should change, how your optimizer should work, and so on. So here we have this number of epochs defined as 100, noise dimension as 100, and the number of examples to generate is 16. So again, this is not used for training. This 16 examples, right? We are going to use this to visualize how well our model is generating the images at the end of each epoch. So we have 100 epochs. At the end of each epoch, I'm going to send the same input, same 16 input. So if you say this seed, right? So we are creating 16 arrays, similarly the one that we have seen before. So when you call this noise tf random 1, 100, it will generate one array with 100 values. So similarly, we are going to generate 16 arrays with 100 values. So that's what we have given here. So seed is equal to tf dot random normal, normally distributed 100 values should be there, and we need 16 such arrays that has this normally distributed 100 values. So this 16 values are used to visualize how well your generator is generating the images at the end of each epoch. So you have 100 epochs. Again, you can change it to 50 epochs or even 1000 epochs depending on your computer's size or your GPU, right? So it can be any number. So it's all those are like kind of hyperparameter and these to be tuned. But here I'm just going with this value of 100 and the noise dimension is 100. So yeah, so seed, and the reason that we are generating the seed is at the end of each epoch the input data should be same, right? The 16 input data should be same, and at each epoch end we will see for that input how the model is generating the output. So it's like, let's say this is our it can be like understanding how the model is performing. So we put 16 input data, look at the image it's generating. So at first it wouldn't generate good image for the 16 examples. Later it would just generate good images for the 16 example. No specific reason for using the 16. It was the same number present in the TensorFlow documentation, and we were able to kind of display the 4 images properly. So we will just go with that. So you can see you will reuse the seed over time. Yeah, so this step is early, but yeah, you will use this over time at the end of each epoch, and this is used to visualize the progress in an animated GIF. So the final result that would be, it's kind of a GIF where we could see in an animated way of, how well the model was in the first epoch and how well the model was in the 100th epoch. So we could see that in the form of a animation where we could see that progress the generator has made. So we need the seed for that purpose, and then we have this training loop. So the training loop begins with generator receiving a random seed as input. So we give a random seed as input, and the seed is used to produce an image. So we kind of put random images to the generator, just like the one that we have given here. So we put random input to the generator, and then the discriminator is then used to classify real images drawn from the training set and the fake images produced by the generator. These two lines is what is represented here. So the discriminator is made to classify real images and fake images, and the real images are drawn from the data set and the fake images are drawn from the data generated by the generator. So this graph or diagram that you are seeing is right, that's what is represented in lines. So the discriminator is then used to classify real images drawn from the training set and fake images produced by the generator, and the loss is calculated for each of these models, and the gradients are used to update the generator and the discriminator. Now we have this loss, right, the discriminator loss and the generator loss. So we get the loss function value for discriminator as well as the loss for the generator. Using this loss, we are going to update the parameters using our optimizers, Adam optimizers. So that's what is given here. So we yeah, this is what basically happens. So you put random input to the generator, generate images, put those images to the discriminator as well as real images to the discriminator, so it predicts it. You get a loss value here, you get a loss value here, and then you let the model know that this is your loss value, update your weights, improve yourself. So it kind of happens over 100 epochs, and at the end of 100th epoch we would have a decent model where the generator would kind of give like decent images close to it, and the generator wouldn't be able to do this alone. So we need a discriminator in order to make this generator win, so that the generator knows how well it's performing, right? So that's the beauty of this. So here we are going to use this tf dot function. So this annotation, this @ causes the function to be compiled. So here we are going to pre-compile all the steps that would happen. So this is what we called as TensorFlow computation graph. So it's like laying out all the steps that should happen in a computation graphs, and all the steps should happen. So in the previous video we were discussing about how we can build neural networks in PyTorch. So initially PyTorch kind of came with the ability not to be compiled, but the ability to build these graphs on the fly dynamically. Initially TensorFlow has this ability only to be compiled. Later from TensorFlow 2.1 they added this ability to dynamically create these graphs. So now it has both this option of compiling this and building this graphs on the fly. So here we are just going to compile it where we say that this step should happen after this step, this step should happen after this step. So we are just laying out the process in the graph. So that's what this decorator does. So we call this as a decorator function. So @tf dot function. So this tf dot function is applied to this function called as train step. So we are defining a function called as train step, passing a set of images. This images is nothing but a batch of image, right? So just think about it. As I said, each training step would take one batch, do a forward propagation, do a backward propagation, and while doing backward propagation it would update the weights. So you have this noise tf.random.normal batch size noise dim. So we know noise dimension is nothing but 100, batch size is nothing but we are generating 256 images. So you put 256 real image to this function and you generate 256 random noise vectors. So with TF gradient tape as gen tape and TF gradient tape as disk tape. So generator tape and discriminator tape, this is used to calculate the gradients. Gradients are all those differential things, differentiating loss in terms of parameters. Let's come to that a bit later. Look at this one. So now you have two sets of images. One is your 256 noise, 256 random input, and 256 real image coming from the batch, because we have already created a batch out of this, right? Train data set, I think so. We have created a batch each with 256 images. So now you have two set of data. One is your images, this is your true data set, sorry, not the true data set, the real images, and the fake images are going to be generated from this 256 noise. So you put this 256 noise array to this generated model. So your training is true. That means here your model's weights should update. Previously we add this training is equal to false when we generated this image, but here we are saying training is equal to true because we need to update the weights, because this is where your training happens. So this is generated image. You are putting 256 noise to your generator, generating 256 images. So you have two sets now. One is your 256 generated images and 256 real images. And now you put these two to the discriminator, just like the diagram represents here. So let's say we have 256 images here, fake images, 256 real images. Put that here, get the prediction, get the loss. So that's what happens in these two steps. Here also the training is equal to true because we also need to train the discriminator as well, right? So we have this discriminator. Real output is nothing but the real images are getting passed. Training is equal to true, real output, and fake output is discriminator, generated images, fake output. So we are getting this, and generated loss equal to fake output, real output, fake output, and so on. So it's basically all those generated loss and the discriminator loss that we have at. So generated loss you should put fake output, for discriminator loss you should put real output and fake output, so that it could add these two losses. So we are just calling these two functions over here. So for generator you just need to put fake output, right, as we have discussed. It just need one parameter. For discriminator it needs two of this, we would add this. So that's why you have these two things, and once you get this loss you are going to find the gradients. Gradients is again nothing but how much your loss is going to change if you are going to change a parameter, right? Again, partial differential of loss in terms of your parameter or your pi-C1, right? So you are getting this gradients using GenTape, where GenTape is the gradient calculating system for your generator, and DiscTape is your discriminator taping thing, so gradient calculation system. And then you have this gradients tape. So you're also passing generated loss, generator dot trainable variables, discriminator loss, discriminator like trainable variables. So these variables will be changed. Again, this is like this differential of these two things. So once we have this gradient, we put this to the optimizers, and your optimizers would look at this and change your variables, trainable variables or trainable parameters, and the step would go on, right? Again, if you're working with a different data set, these steps won't change. You probably would change like the number of epochs, the batch size, and the generator model and the discriminator model, but probably the train step won't change much. So yeah, you can just understand this in a clear way. You can just change all those models and other hyperparameters. So the steps is as we have given here. Now you can look at this statements. Now this would make more sense to you. Training loop begins with generator receiving a random seed as input. This one. So generator is receiving random noise as input, and that seed is used to produce an image. So this noise is used to generate image that is stored in generate images. The discriminator is then used to classify the real images drawn from the training set and fake images produced by the generator. These two things. And the loss is calculated for each of these models, and the gradients are used to update the generator and discriminator. So this is what happens in these two things, right? And finally we would kind of apply this to the optimizers. Once we kind of find the gradients, we apply this to this, and yeah, kind of this completes the training step. So the end of training step is nothing but updating the weights. So you start with a single batch, go to the forward propagation, do a backward propagation, update the weights. So your train step is done, your single batch is done. Now you put another batch, do the same thing, update the weights, done. Again this goes to the next batch and so on. So this is for one step, one batch. This has to happen for all the batches, and this should happen for all the epochs. So when we say one epoch, that means all the batches should do this. So that's what happens in the function called as define train. So here it takes in the input data set and epochs. This in turn would call the train step, right? So let's understand this. So we are calling this train function. So actually this is what happens even in a classification model. All this finding this generator, not generator, finding this loss, gradients and optimization happens in your classification model too. Instead you wouldn't have a generator model, you just have this binary classification model. Here we are naming this as discriminator. So we would do the same thing, but in Keras just makes all these things easily, so we don't have to worry about all these things, right? But under the hood this is what is happening. So it's again a good way to understand what's happening so that we have a clear idea about it. So here we have this train step where for epoch and range epoch. So here we have taken 100 epochs. So the model should train for 100 epochs, and at each epoch it should train with each batch. So at each epoch from 1 to 100 it should train with each 256 batch, and at end of each batch it should update the weights, and this updation of weights and all those things happens in this train step. So that's what happens in this training, and the other things are just pretty simple. So here we are going to generate and save images, and this is used to display the image at the end of each epoch. So later we would have this function called as generate and save images. This is in a function, so we are not calling it, so it's okay if you have this function later as well. So maybe you can look at this first. Predictions is equal to model test input, training is equal to false. So model is nothing but your generated model that we are passing here. Again, you can just go through these things. These are pretty simple. So we generate images and display it there. This is those 16 images that I was talking about. So at end of each epoch, so you would generate 16 images from the seed and display it there. So that's what we have here, and we would save the model at the end of 15th epochs to this checkpoint prefix, to the checkpoint directory that we have over here, right? So to log the model, and we also would print the time taken for each epoch. And finally, once your model is trained for 100 epochs, we would display, and here we would display the images, right? So we have display clear output this thing, and here we are displaying the model. Actually in this generate and save images, we're displaying it at the end of each epochs, we are calling this. And once all this epochs is done, also at the end of 100th epoch we are displaying all the images. And again, other things are pretty much simple. So we again call this train method. So call the train method defined above to train the generator and discriminator simultaneously. Note, training GANs can be tricky. It's important that the generator and discriminator do not overpower each other. Example, that they train at a similar rate. Again, all those, this is like the notebook that I downloaded from TensorFlow documentation. So yeah, so all these are like kind of warnings and note that they have given. So make sure that you are following these two. So it shouldn't be overpowering. This is what I was telling you before. So you shouldn't have a very complex generator and a simple discriminator. So you would never get a decent generator in that case. So it should be a level playing field. And at the beginning of the training, the generated image looks like random noise. As training progresses, the generated digits should look increasingly real. After about 50 epochs, they resemble MNIST dataset. So we call this train function that would again further call this train step and do all these trainings and so on. We'll run these steps. And yeah, let's train this, save this to the checkpoint that we have created before, and then we can just display the images. Display a single image using the epoch number. So you can just give a single epoch number and display image here. We are basically using this in order to, again, this function, right, this display image, we are going to use this in order to create this anime thing where, let me show this to you. Yeah, so the training is happening. So time for first epoch is 20 seconds. This is how your image looked like at the first epoch. It's no way close to MNIST digit, right? But as the epochs kind of increases, we would get like more accurate image, not accurate, but images that are resembling your MNIST digits and return digits. So we are saving this images at this image with this particular number. I think it's getting saved here. So generate and save image, it's getting saved here. And in order to create this animation of how your epoch, how your image looked at first epoch, second epoch, third epoch, all the way up to 100 epochs, we are using this particular code. You can go through it. It's not like that complex, simple code of creating a GIF, and then we are going to display it. But yeah, that's the overall concept. Starting to look like a number, but yeah, so that's about it. So all your images will be saved here. So at the end of first epochs, so you would save the image with a number 0001. So you are using 04s and 1 number here. So we have 0, 1, 2, first epoch, second epoch, third epoch, and so on. And if you want, you can train it with 1000 epochs too. No issues there if you have that much computation. So later we will use this in order. So if you see this code quickly, right? So we are reading all these images. We are using this blob. As I said, it's used to match patterns of files. So it would load all the files with image prefix and ends with .png and sort this based on this number 1, 2, 3, all those things, and then display it in the form of a GIF, an animation, and store this in dc gan.gif, and later we would display that. and this line basically embed this and display this. That's why we are using this TensorFlow docs, and you will see this GIF here. So this is about the code. Have this code executed here. So this is going to take some time. So yeah, I can show this to you how the numbers look like at the end. Here you can see it's like 0, 8, probably 8 or 6 or something. Again, it's far from perfect, but again, you can increase the epochs or improve the model in order to get better predictions. But yeah, it's slightly similar to the handwritten digits that we are getting. So finally, you would also get an anime from this as well, like a GIF. So if I would save this as a GIF, but let's see if I can open this. Right, so you can see this GIF, right? So from the first epochs, this is how the model has evolved on building this handwritten digit. So this is the GIF that we are creating, and this is the code for it and embedding it. So I hope everyone is clear until this point. I know that this code is pretty complex compared to a simple image classification code, but again, once you practice this, if you even have some doubts, rewatch that particular section of the video again. It's like a really interesting use case, and again, it's like a really good thing to know. It's not like you know deep learning, you just know image classification and simple stuff. So you can just put this on a resume, build some interesting applications of this image generator too. So that's like a great thing to do. So please go through this, try this code for yourself once, maybe to make things simple. I'll just give you a quick recap of what we have done. So first we are importing the dependencies, and then we are just loading the train images. We don't need the labels and stuff. We don't need the test data set. Train images, and reshape this, normalize this between -1 to +1. It's better for GANs. And buffer size for shuffling, batch size. This is how we can create normally distributed random noise, and creating generator neural network, and then discriminator neural network. And then you are kind of setting up the loss. So discriminator should get the loss for real as well as fake images to understand how it can distinguish real image and fake image, and generated image should know how well it can generate fake images. And then you are setting up the optimizers, giving the checkpoints, 16 images to print at the end of each epoch. And then we have this TensorFlow function compiling it with saying that generate images, put those real images and fake images to the discriminator, calculate the loss, find the gradients, and update the parameters using your Adam optimizers. And finally, run this for 100 epochs. At each epoch, all those 256 batch should undergo this particular step. And then finally, you generate and save the images, put this to the animation. Yeah, so maybe you can just run this collab file again and see how this numbers are getting generated. But please go through the code line by line, or even look at this code and type it in your collab environment. I'm sure that you probably follow that process, but yeah, this would really be helpful. And I'll probably at a later point, next video, or probably at a later video, I'll show you how you can do this in Keras. It should be easier in Keras, but I'm not very sure about it, but I'll see if I could make a video for that. So that's it from my side, and I really hope that this is helpful for you. And I'll see you in the next upload. Thanks for watching.
Hello everyone, I am Siddharthan. This is the 10th deep learning project video in my YouTube channel, and in this video let's understand how we can build a sentiment analysis system with IMDB movie reviews dataset using a LSTM neural network. LSTM stands for long short-term memory, and let's understand how we can get this dataset from Kaggle and how we can build this neural network in Google Collaboratory. So that will be the agenda for today's video, and let's get started. So I'll open my Google Collaboratory. So first of all, let's just set up our environment with a GPU session, and we can get our dataset from Kaggle using Kaggle API. So first you can open your Google Collaboratory and go to this runtime setting and change this runtime type to T4 GPU. So we do this because the neural network training is going to take a long time. So in order to reduce that time, we are going to connect to a GPU session instead of a CPU session. So that will be the first step. So the next step is installing Kaggle library. So just do a pip install of Kaggle. So I'll say pip install Kaggle with this exclamatory mark, which is to run some commands. So here we have to connect this session. So it's connecting, and you can run this cell with shift enter. So this will install this Kaggle library, and in Google Colab, this Kaggle library is pre-installed. So it would say like requirement already satisfied. But if you are working on, let's say, Jupyter notebook in your local machine, in that case you have to install this Kaggle library separately. So that's one thing. So as you can see, it's already as this Kaggle library and the other dependencies. So that is the first step. So the next step is we need to import the dependencies, and also we need to import the dataset from Kaggle. So here I'll create a text cell and I'll call this as importing the dependencies. And also, while building this code, I'll explain you what is meant by this LSTM model and how this entire thing works. And it's okay if you don't completely understand about this LSTM and other NLP processing techniques. I'll explain all those things from basics, so you should be good if you are like starting from the basics too. So first I'll import my OS library and import this JSON. So this is like a standard way of importing. So these two libraries are kind of like pre-installed with Python. So first we can import those libraries, and then we can import like the other libraries that we want. And finally, if you are having like a custom packages, let's say you have this data processing.py Python file, those can be imported at the last step. So this is like one standard thing that you can follow. So first I'm going to import this zip file. So from zip file, import zip file with uppercase Z and F. The next library, so we are using the zip file because once we call this Kaggle dataset API, it's going to give you a zip file. So we'll be extracting that zip file using this zip file utility. And then I'm importing pandas. Import pandas as PD. So the dataset that we are going to work on is this IMDB dataset of 50k movie reviews. So we have this CSV file called as IMDB dataset.csv, and this has two columns. One is review and the other one is sentiment, where the unique values for the sentiment is positive and negative. So we have this movie review and we have the corresponding labels of whether it is positive or negative. So this is the dataset. So we will be loading that CSV using this pandas library, and then I'll import this from sklearn dot model selection, import train test split. So train test split, of course we know that it's used to split our entire dataset into training data and test data. And then from tensorflow.keras.models, import sequential. So Keras basically provides this eye-level APIs so that it's easier for us to build the neural networks with TensorFlow. So we will be using the sequential API from Keras. So sequential is basically used in order to build the sequential models where you can linearly stack the layers. So in the case of convolutional neural network, you would stack this sequential layer with convolutional 2D layers, dense layers, and so on. So here also we will use layers like embedding, dense, and so on. So that is the next step, sequential. So tensorflow.keras.models. Okay, so the next is from tensorflow.keras.layers. So here let's import dense, embedding, and LSTM. So these are the three layers that we will be using. So we have this dense layer, which is the fully connected layer, and then we have this embedding layer, which will be the first layer in our LSTM network, and then we have the LSTM layer itself. So these are the three layers. I'll explain you the purpose of all these three layers when we build this neural network. And the next step is we need to load the tokenizer from tensorflow.keras.preprocessing .text, import tokenizer, and then from tensorflow.keras.preprocessing .sequence, import paired sequences. So these are the dependencies that we need. So I'll run this one. So we have this OS and JSON. So we need this in order to access a configuration file. So we'll be downloading this kaggle.json, which has the credentials for our Kaggle account. So we are using this OS and JSON library in order to read that file, and we have the zip file in order to extract the zip file that we are going to get from Kaggle API, and pandas library to load the CSV file into a pandas data frame, and then we have train test split to split our data into training data and test data. And then this part is for building the neural network. We have this sequential to build the sequential layer of neural network. And then we have this dense embedding and LSTM being imported from Keras layers. And then from preprocessing.txt we are importing the tokenizer. So this we use in order to tokenize the data, which is basically we would map this words in the data to certain integers or vectors. So I'll explain you all these things in detail when we are using this class of tokenizers and other things. And then we have patch sequences. So this patch sequences is just to ensure that all your input data is of the same shape. So let's also discuss about these things in detail, but it's okay if you just have this basic understanding for now. So we have run this all, and all these libraries and the functions have been imported successfully. So the next step is data collection part. So I'll create a text here and call this as data collection, and this will be through Kaggle API. So in order to use this API, your collab environment should be authenticated with your Kaggle credentials. So I hope that you have a account in Kaggle. If not, please create an account, and once you create this account, you need to verify your email ID and phone number. Then only your Kaggle API is going to work. So once you're in this Kaggle home page, right, so kaggle.com, so once you have registered and you're logged in, you will see this account profile picture kind of a thing. So you can click there and go to the settings. So once you go to the settings, so you need to verify this phone number and all these things. So here under this API section, you will see this create new API token. So create new token. So when you click this, so this will download a particular file. So let me click this. Okay, so I've already downloaded a file, but again you can click this after you have verified your account, and this will download a kaggle.json file. And once you have downloaded it, you have to upload it in this file. So let's say that you have downloaded the file. So come to this files section, go to this upload tab, and from here you need to upload your file. So I'll go to my downloads and search for this Kaggle. So I have this kaggle.json, which is the latest file that I downloaded. Okay, so this is like in Kaggle 1 for me. So but if you download this for the first time, it will be just kaggle.json. So I'll rename this. So this basically has my username and other credentials that helps this session to connect to this API. So now I'll create a variable called as Kaggle dictionary. So Kaggle dictionary is equal to json.loads or json.load, say open, and kaggle.json. You can also use this with thing in order to load this file, but this is like much simpler. json.load open kaggle.json. So this open function basically an inbuilt function in Python to open a particular file. So here we are opening this kaggle.json file, and this json.load basically converts a JSON object into a Python dictionary. So that dictionary is then stored into this variable called as Kaggle dictionary, and that as basically your Kaggle username and your authentication key. So let's run this. So make sure that you have this kaggle.json file in your files, otherwise this thing won't work. So this is nothing but the path of the kaggle.json file. So I'll run this. Now I have this dictionary which has my credentials. Now I have to set up the Kaggle credentials in my environment variables. So here let's say set up Kaggle credentials, or you can just say Kaggle API key. So set up Kaggle credentials as environment variables. So there is like an easier way to do this. You can just copy and paste your username and key from this kaggle.json, but it's not recommended. So you should never kind of paste your passwords or your keys in the code, because you are probably going to share your code with someone else if you're collaborating, right? So it's not recommended. So it's always better to put this in a kaggle.json or some config.json file, or use .env files. So that's one thing. So here I'm going to say os.environ, and I'll create a variable called as Kaggle username. So this thing shouldn't change. So this Kaggle username shouldn't change, because when we call the API, this will look for this particular environment variable in your OS. So this shouldn't change. So now let's say Kaggle dictionary, and here the key is going to be username. So even you can print and check this Kaggle dictionary thing. So I'm not going to print the value, but I can print the keys and show you. If you want, you can print your values and see it. So this Kaggle dictionary basically contains two keys probably, so username and key. So we are going to store that in the environment variables. So you can use Kaggle dictionary.values in order to see the exact values. And the next thing that we are going to set up is my key. So this will be Kaggle key, and then this will be just the key, the Kaggle dictionaries key. Okay, so this should be in lowercase as we are seeing here. So here we are creating two variables, Kaggle username and Kaggle key in OS environment variables, and then we are passing these username and key. So let's run this. So once this is done, we can go ahead and kind of run this API. So come back to this IMDB dataset. I can share you this link, but I mean this link, this is not required. So all you need is this copy API command. So this is the API thing. I'll put an exclamatory mark and run this. So I'll share you this Google Collaboratory notebook. You can refer to this. So when you run this, this will load the dataset from this Kaggle thing. So this dataset will be loaded to your Google Collaboratory as a zip file. So let's run this. Make sure that you are using an exclamatory mark, as this is a kind of like a command. So once you run this, you will see that this is downloading a zip file. So we have this IMDB dataset of 50k movie reviews.zip. So you can see this file over here. And now we have to unzip this. So you can also run this exclamatory mark ls. This is a Unix and Linux based command for list the files. So we have this IMDB dataset of 50k movie reviews.zip. So this is the file that we want to extract. So this part is unzip the dataset file. So here I'm going to save with zip file, which is the function that we have imported from the zip file library. So this is this thing. So with the zip file, and here paste the name of the file, or you have to paste this path, but again our default working directory is this one, so I don't have to copy the entire path. If you want, you can do that. So within quotes put the path or the name of the file and then say R. So it's going to read this file as zip ref. So this is going to read this file with this particular variable name, and now we are going to say zip ref dot extract all and run this. So this will extract all the files within this compressed file, and again you can run this exclamatory mark ls in order to see the extracted files. So we have this zip file, and from there we have extracted this imdb dataset.csv, which we are kind of seeing here. So this is how you can load your dataset using Kaggle API after configuring the credentials in your environment variables. So now you can see this dataset here. So this is about data collection. Now we can understand how we can load this dataset, do a lot of pre-processing, and then train our LSTM neural network. So here I'll create a text cell and let me call this as loading the dataset. And I mean we'll be doing some pre-processing too. So I'm going to say data. Let's call this as data, or even you can put df, so it shouldn't be an issue. So I'll say pd.read csv. And within that we have to paste this IMDB dataset. So you can just paste this name, but if it's in a different path, right, you can copy the entire path too, which is like, I would say that's more recommended thing. So copy the path and paste it over here. So if you're working on Jupyter Notebook and it's in a different directory, it's better to copy the entire path. Again, if you're working on your local. So let's run this, and this will load the CSV file, imdb dataset.csv, into this variable called as data. Now let's check the number of data points here, data.shape. And this says it has 50,000 data points and 2 columns, 50,000 rows and 2 columns. You can run data.add in order to print the first 5 rows, just to get an idea of how the data is looking like. So first we have this review, and then we have the sentiment. So again, this is like a movie review. You can go through this in detail, print the entire first review and check the sentiment and so on. You can do that, or you can also do this data.tail, which will print the last 5 rows in this data frame. So again, you can do some data analysis and understand about this data more, but let's focus on building this neural network for now. So the next thing is to understand the distribution of this target variable. So we need to understand how the data is distributed, whether there is an imbalance. So we have 50,000, right? So let's say that we have 40,000 reviews as positive and 10,000 reviews as negative. Then it's going to be an imbalance class, and then we have to do this undersampling, oversampling, and so on. So we have to make sure that the class distribution is almost even. So let's do that. So for that, you can just say data, and within square bracket you can say sentiment dot value counts. So this will tell you how many positives are there, how many negatives are there. This is basically takes a particular column and finds the number of unique values in that particular column. So in this sentiment column, we have positive observations as 25,000 data points and negative data points as 25,000. So again, there is no class imbalance, so it's like perfectly balanced, so we don't have to worry about the data being imbalanced. So that is one thing. So the next step that we can do is, so I can't pass this positive and negative as the labels to my neural network, so it has to be encoded to numerical values. So let's convert this positive to 1 and negative to 0. So I'll say data.replace, and you have to create a dictionary kind of a data type and say sentiment. So the key of this dictionary is the name of the column, as you can see here, and you have to create another dictionary, and here say positive is 1 and negative is 0, and make sure you are putting this in place. So in place is equal to true. Okay, so we have this data.replace, so we are going to replace certain things. So here you, again, as I said, you have to create a dictionary, and within this dictionary there will be another dictionary. So first we are saying that in the sentiment column I want you to replace some stuff. So what we are replacing is, in this I am replacing positive words with the integer 1 and negative with the integer 0, and in place is equal to true is like if you don't include this in place, so this won't be changed in this data. So what if you are not doing this in place, right? So you have to create another variable, and you have to kind of store that here. So in this case you can kind of remove this in place, but if you want to avoid creating another variable and do this, you can just change this in the place of this data thing itself. So I'm putting this in place, so make sure that you are including this and run this. Now you can again run this data.head to make sure the sentiment column has changed, so to make sure that it has encoded. So let's run this. As you can see now, the positives are kind of converted. So you have 3 positive, 190 and positive, so all these are converted to 1 and zeros, and you can also run this value counts again to make sure that the encoding has happened properly. So let's run this. Okay, so with this basic analysis we understand that the data has like a good distribution, so we don't have to worry about that, and we have also like encoded the labels. The next step is splitting the dataset into training data and test data. So I'll create a command saying split data into training data and test data. So here let's create two variables, train data and test data. So we are not going to pass this reviews and sentiment as x and y separately as we usually do. So I'm going to pass this entire data frame and get separate data frames for train data and test data, do some data processing, and maybe later we can split this x and y separately, the reviews and sentiment separately. So I'll say train data and test data is equal to train test split, which we have imported from sklearn.model selection. So we have train test split, and within that I have to pass the data frame, the original data frame, that is nothing but data, and then I'll say test size is equal to 0.2. so that means I want 20% of my data to be test data, and the remaining 80% will be my training data. So and then I'll create a random state is equal to 42. So random state is just to make sure that there is a reproducibility of the code. So if you use the random state as 42 as well, then your data and my data is going to be split in the same way. So you would have the same training data and I would have the same training data. If you use a different number, then you're going to have like different combination of training and test data, and 42 is generally used as like kind of a convention. So there is no strict rule to say that you have to use only 42 or any particular number. So let's run this. So this will split my data into training and test data. So we can print the shape of these two and check this. So train data dot shape, and I'll run this test data dot shape as well. So 40,000 and 10,000. So we have this 20% data of 50,000, which is 10,000 going into test data, and 40,000 goes into training data. So the next steps are critical steps before building the model itself. So this is about data pre-processing. So I'll create a text cell and call this as data pre-processing. So this is like a very important step when it comes to NLP problems, because when you are having like a tabular data with some numerical values, then it's going to be a simpler process to pre-process those data. So you would just like kind of handle some outliers, replace some missing values. But when it comes to text data, you have to do some different pre-processing, like tokenizing the data, and you have to convert them to feature vectors and so on. So we have to do a bunch of stuff. So in this section, let's understand how we can pre-process this data. So the first step is tokenizing the data. So I'll call this tokenize text data. So we are going to take this review column and convert this into a format that the model is going to understand. So that is the step. So here I'll create this variable called as tokenizer, and this tokenizer is equal to, so we are going to initiate this. So from tensorflow.keras.preprocessing.txt, we have imported this tokenizer, right? So I'll copy this. So I'm creating an instance of this tokenizer and say num underscore words is equal to 5000. So let's understand the purpose of this tokenizer. So a tokenizer is basically used to convert your words or phrases into particular numbers. So let's say that in your data you have this word called as good. So let's say we are mapping that good to an integer called as 1. So that is like a different word, like something like better. Then we, let's say we use 2 as the representation for that word better, and let's say that you have bad. So bad can be represented as integer 3, 4, or basically any numbers. So this tokenizer is used to kind of convert those words into integers. Again, it can also be used to convert these words to vectors, but for now we are just going to convert these to integers. So for that we are going to use the tokenizers, and num underscore words is equal to 5000. So this is nothing but, so we will be having a vocabulary. So in this case the vocabulary is nothing but, so we take the entire text present in this training data, and in that training data, so we would have like several words. So I mean, we don't know how many words are there. So again, of course, it's going to be more than 5000. So the reason that we are doing this is we are going to take the most common 5000 words from this entire training data. So that will be kind of like this base data, and then these 5000 words are kind of converted into integers, and later we kind of plug in this training data, apply this tokenizer, and convert the data into numbers. So this is the overall step, but again, if you don't understand everything, that's okay. So we will do a few steps, so that will make more sense to you. So here I'll say tokenizer.fit on text. So we are going to fit the tokenizer on some text, just like we used to fit the model, right? So similarly on standard scalar also we would do this fit transform and stuff like that. So it's similar to that. So we have this tokenizer dot fit on text, so it should be texts, and then I'll say train data. So I'm going to take this train data frame and fit this with a review column, so that, because that is the text column that we have, right? So I'm fitting on this review, so that means it's going to map the most repeated, or basically the most common 5000 words in this to those particular or specific integers. Now I'll say xtrain is equal to path sequence. So here we are going to do 2 steps. So we have this path sequences, or I think we can do this separately too. Let me do this in this way, or this can be written as path sequence. So this path sequences we have imported from here, from TensorFlow Keras preprocessing sequence. We have this path sequence. I'll explain you in a minute the purpose of this. So within this path sequence, we are going to say tokenizer dot text to sequences, and within this I'm going to pass my train data review, and max length is equal to 200, and I'll copy this same thing and say this, and let me call this as x test. So this should be test data. So let's understand what we are doing here. So here we are basically doing 2 things. One is tokenizing the data, and then applying the path sequence. So first let's understand this tokenizer thing. So now we have fitted this tokenizer, right? So think about solving a numerical dataset problem, so a diabetes dataset or something. So we use standard scalar. So we first fit it on training data, transform it on training data and then again transform it on test data, right? So we won't fit and transform on training data and we won't fit and transform on test data. So you should always fit and transform on training data. Test data should be transformed to make sure there is no leakage of data. So it's similar to that. So first we are fitting this tokenizer so that it gets all those vocabulary in this train data review, basically getting all those list of those 5,000 most repeated words. So once we get that right, so now we are passing this train data review and applying this tokenizer. So we are going to get a sequences, texts to sequences. So as I said, we are converting these 5,000 words into respective integers, and again think about it as each word is mapped to a particular integer. Now let's say your training data first data point has 10 words, so those 10 words has to be in a sequence of 10 integers now. So that is this step. So this is basically converting the words present in training data to those sequence of numbers, the integer values. So that is this step. So that's what happens in this tokenizer dot text to sequence of training data review. So we are not doing this on the sentiment column because we know that that's a label numerical value, so we shouldn't do that here, but we are just doing this on the review. And then the next step is path sequences. The purpose of path sequences is it makes sure that all the input data in this train data review thing, right? So they have the same length. So here we are giving this max length as 200. That means you have these words and you are mapping this to integers and so on. So this path sequence has to make sure that all those have the length of 200. This is because when you train a neural network or even any machine learning model, right, the input shape should remain constant. So one input data, one text data. So let's say that there is a review, so that review can't have, let's say, 10 words and other, I mean it can have words, but once you do this tokenization and other things, like it shouldn't kind of be in different shapes. So that's what I'm saying. So if you think about an image classification problem, you cannot pass a data set where some images are of 224 into 224 pixel, whereas some images are of 500 into 500 pixels. So there has to be an uniform input shape. So this path sequence makes sure that it has this uniform length of 200, and that's what we are doing here. And there is another way to do this path sequence. So instead of this length, it can also mark the end or the beginning of the input data with values like 0. So if it's 0, that means the model can understand that the input data has kind of stopped. So this is the purpose of path sequence, but for now we are going with the length thing. So first we are fitting it on the training data, the tokenizer, and then we are kind of converting this text to sequences here, training data, and in this test data we are also doing the same thing. So here pay attention that we are not fitting this fit on text to the test data again, similar to not applying standard scalar to a test data. So that is the step. So let's run this now. My xtrain and xtest will contain this tokenized reviews of training data and this test data thing. You can maybe also print and see this xtrain and xtest. Okay, so max length, oh, there shouldn't be an underscore. So let's run this. And let's print these things as well. So maybe in the meantime it runs, I can do this thing. Okay, so we got this. As you can see, previously this review was in text and now we have converted those things into numbers. So this is how you can kind of do this tokenization. So the next step is assigning the label. So we have this white train. So white train is equal to train data sentiment, and white test is equal to test data sentiment. Okay, so here we have these two columns, right? So we are applying this tokenization and path sequence for this review column and separating this sentiment column for white train and white test. So the review column goes to xtrain and xtest, and the sentiment column comes to white train and white test. So this is the next step. So again, you can print and see this white train and white test if you want. So this would have the values as 1 and 0s, which is the encoding that we did. Okay, so that's the next step. So now we have the data processed, ready to be fed to the model. So the next step is building the LSTM model. So I'll create this thing. So LSTM, and this LSTM stands for long short-term memory. So let's maybe understand this long short-term memory thing in a shorter way. Okay, so this LSTM models, right? So this is a type of recurrent neural networks, and we know this LSTM and recurrent neural networks. So these things are like, it's a kind of RNN. So this is useful for sequence data sets. So if you think about sequence data, it's like time series data set, or textual data set, where the input data is kind of linked to the previous data it's seeing. So let's say that you have this text where it says the movie is not good. So it should not look at all the words separately, but it should look this as a sequence, right? And it says like it's not good. So it should kind of maintain the sequence in the data, and it has to maintain or understand or have the memory of the input data in a sequence way, so that it kind of makes this decision on whether it's a positive review or a negative review based on the sequence of data. So if you think about a time series problem, right? So if you take the input data, so all these follow a sequence. So time series data is nothing but, let's say on January 1, 2024. So Jan 1, the temperature of a day is 25 degrees Celsius. On Jan 2, the temperature is like, let's say, 27 degrees Celsius. So this follows a particular trend or something, right? So this is seasonality thing. So when you use a sequential data, it should not look at those input data separately, but it should kind of have the memory of this other input sequences as well. So that's the advantage of LSTM. But if you kind of work with other general neural networks, right, so they don't have this memory. So this is like the difference between CNN or general artificial neural networks compared to a RNN, where it kind of tries to have this memory, where it has this kind of dependency of this memory attached to it. So that's the advantage of this LSTM. So in our deep learning course, we will discuss about this in detail, understand like the concepts of it, how the math works and all, when we come to that part of RNN and NLP. But for now, understand that LSTM is a type of recurrent neural network, and the advantage is that it kind of understand the sequence of data, and it doesn't looks at the input data as like one individual data point, but try to understand the sequence of it and the sequence of words present there. So that's about it. And now let's try to build this LSTM based neural network. So here I'll make a comment and call this build the model, and here let's create a variable called as model is equal to sequential, and let's do this model dot add. So sequential, as I said, it's used to stack your layers linearly. So I'll say model dot add, and first we are going to add a embedding layer. So embedding input dimension is equal to 5000, and output dimension is equal to 128, and input length is equal to 200. So I'll explain you about this embedding layers and other layers once I complete this architecture thing. So I just have to do like another 2 lines of code, so you can maybe wait until this point. So the next thing is model.add LSTM, and we have 128 units. Dropout. So dropout we can maybe put 0.2. Again, we can play around with some numbers, and then we have this recurrent dropout. With that also we can go with 0.2. And finally we have this dense layer of model dot add dense 1 comma activation as a sigmoid activation. Now let's try to understand this model. So here we have 3 layers. So first is embedding layer, and the next one is LSTM layer, and then we have dense layers. So we have imported all these layers from TensorFlow.keras layers, dense, embedding, and LSTM. So we have imported from here, and now let's try to understand the purpose of all these three layers. So we have the sequential, and we are adding these layers individually. So the embedding layer should always be the first layer in your network whenever you are kind of working with this NLP related problems. And we have mentioned this input dimension is equal to 5000. So this 5000 is basically coming from this tokenizer vocabulary that we have, which is this 5000. So that is what we are mentioning as input dimension, and the output dimension is equal to 128. So this 128 again is what happens here is each word in your data, the input data has to be represented in a 128 dimension vector space. So that's what this means. So again, embedding, it's nothing but we are representing this data as vector embeddings in this vector space, and the dimension should be 128 dimensional vector, which is like pretty large. And the input length of 200 is nothing but the path sequence that we had. So each input data would be having a length of 200, right? So that's what this input length means. So this is similar to mentioning your input size for CNN. If you are working with a CNN kind of a problem, so we would mention the shape of the image, right? So let's say 224 224 3. So it's similar to that. So here we mentioned the length, and the input dimension is coming from the tokenizers 5000 thing that we have mentioned. And again, as I said, output dimension is for the vector space that we are considering. So this this layer basically has to this is basically for representing the data in its vector form. So we are creating those vector embeddings in 128 dimensional vectors, and then we have this LSTM model. So this 128 is what we are representing here. So now we have this LSTM with 128 units, or again you can think about these as the neurons that we have in this LSTM. So we have this units as 128, and then we have this dropout of 0.2. So dropout, again we have two dropouts here. One is dropout and the other one is recurrent dropout. So dropout, it's basically in this case when you put 0.2, 20% of the input data, it's going to flow as 0. This is to make sure that your model is not overfitting, and this kind of turns off the output of some neurons. So that is the purpose of this dropout. And recurrent dropout is we have this memory, right? So as I said, a recurrent neural network has this ability to maintain this memory. So this kind of happens because this has a feedback loop that kind of flows to the previous neurons and the previous layers and so on. So we kind of add a dropout there. So that the purpose of adding all these dropout is just to generalize your model so that it doesn't overfit, or we call these as regularization parameters. So that's about it. And then we have this dense layer. So dense layers are the ones where when you say dense layer, that means the output from all these 128 units or 128 neurons are connected. All those 128 neurons outputs are connected to this one neuron or this one unit in this. So that's what it means. So if you want a definition, it's nothing but a dense layer basically all the networks, all the neurons in the previous layer are connected to all the neurons in this dense layer. So that's what a dense layer means. And the final out, this is the output layer. The output layer has one neuron and it receives the input from all the 128 neurons, and that's why it's called as a dense layer. And the activation is sigmoid. And we also have discussed this previously, that if we are going with a binary classification problem, it's better to go with a sigmoid activation function. And sigmoid, what it does is it gives out the probability, right? So between 0 probability, we know that the value should lie between 0 and 1. So now we can infer that if the probability is more than 0.5, then the class is going to be class 1, which is positive in this case. And if the probability is less than 0.5, then it's going to be a negative sentiment or negative review. So that's why we are using the sigmoid. So overall, we are basically using three layers. So embedding should always be the first layer, as I said. So we have this embedding layer, so that this kind of represents the words in a 128 dimensional vector space. And then we have the LSTM layer itself, which is very important, and we have added some regularization parameters to this. And then we have this dense layer of with one neuron and the activation of sigmoid. So we will also discuss later on, in the later videos, on how to choose these numbers in a better way, how you can fine tune this, all about those things. But for now, just try to understand like how this implementation works, so that you can implement this for other data sets too. So that's about it. So we have this LSTM based neural network ready. So let's run this. Recurrent dropouts. I think I made this should be, there is a typo. Recurrent dropout. Sigmoid cannot be deserialized. This should be lowercase s. Okay, so this is something regarding this GPU thing. So I mean, we can ignore this layer. LSTM will not use CUDN and kernel since it doesn't meet the criteria. So this is related to the GPU. So it says that our GPU, the one that we are connected here, the T4 GPU doesn't have this thing. So I mean, we can ignore this. That's okay. And the next step is we can kind of run this model.summary to look at the parameters and the different layers that we have. Okay, so first we have the layer, the type of the layer that we have, the output shape and the parameters. So first we have this embedding layer, LSTM layer, and the dense layer. So we have this embedding, LSTM, and dense, and we have this none basically represents your batch number. We have 200 as the shape. The 200 is this shape that we are mentioning, and then we have this output dimension of 128, 64,000 parameter. So how this parameter is calculated is it's basically the product of your input dimension and your output dimension. So here your input dimension is 5,000, right, and your output dimension is 128. So if you multiply that, you will get, so let's say 5,000 into 128. So that's going to be this number. So this is what we are seeing here, and then we have this 128. So here we have this 128. Again, in this case the input is going to be this number, and then we have this 128. So this is how you can kind of calculate this number. So it's input dimension into output dimension, and this 129 is nothing but in this case the input is 128, the output is 1, so it's 128 into 128, but we add a bias parameter to this, so that's why you have this 129 here. So this is how you can basically infer this. Okay, so that's about it. So that's how you can basically understand the summary of these models. So the next step is we can just add the optimizer loss to it and train the model. So the next steps are like pretty simple. So here I'll say compile the model. So here let's say model.compile. My optimizer is equal to Adam, and loss is equal to binary cross entropy. So binary cross entropy we can use for binary classification problem. So as this is like we are just predicting positive and negative, right, 1 or 0. So we can use the loss function as binary cross entropy, and then we have this matrix. So I hope everyone knows about this loss and optimizers. I mean, you don't have to exactly know what is meant by this Adam or what is meant by this binary cross entropy detailing, but just understand the purpose of this. So binary cross entropy, again we have this loss function, and when we train the model it tries to reduce or minimize this loss function, and we use this optimizers, Adam optimizers. So this optimizers tries to change the parameters in every iteration or every epochs and so on in the forward and backward propagation. So in your backward propagation your parameter changes, and that change is basically done by your optimizers, by just calculating these gradients. I've already made this videos on back propagation in my first module of my deep learning course. You can check that out if you have some doubts about it. So this is we are compiling it with optimizer, Adam optimizer, loss, binary cross entropy, and matrix as accuracy. So let's run this, and the next step is training the model. So I'll create a text and call this as training the model. So for this I'm going to say model.fit exchange. So we have to pass our X data, the reviews, and the labels, which is ytrain, and say epochs is equal to 5, and batch size. So batch size, again if you have a larger GPU you can use a large batch size. So here I'm going to use 64, and validation split, let's say 0.2. So what this does is it will reserve 20% of my training data for validation. So at the end of each epoch, so this would use this validation data as kind of like a test data, and it would give you the training accuracy and loss for both this training data and validation data. So once this training is done, we can kind of calculate this the accuracy on the final test data. So let's run this. So this model training is going to take some time. I think for me it took like 15-16 minutes or something. So I can pause this video for that to happen, or I can just try and continue with the other pieces of code, and maybe in the meantime the training will happen. So once the model has trained, right, so we have to do some evaluation. So here I'm going with 5 epochs. So you can also play around with this epochs and other hyperparameters maybe. So we have this learning rate and other things. You can play around with that to see if your performance is increasing. And here I'll call this as model evaluation. So we have to wait in order to run these cells. So we have to wait for the training to complete before we do this evaluation, but let's just write this code. So this is for evaluating the model. So I'm going to say loss comma accuracy. So this is equal to model.evaluate. So within this model.evaluate, I'll pass x test comma y test. Okay. So we are kind of creating this model within this variable called this model, and then we are training it. So once it's trained, we are going to use this evaluate function. So model.evaluate takes in 2 parameters, your x test and y test. So it takes this reviews data, which is tokenized. So it takes this data, finds the prediction, and once it finds it, it compares it with the test data, the actual test labels. Sorry, it compares the predicted labels with the actual labels, and it would give you the accuracy, and you would also get the loss function value too. But again, we can just print the accuracy to see like what's the test data accuracy. So I can just say print f of test loss and what's the test accuracy. So test loss is equal to, we can just say loss. So I hope you know this string thing. So f is, it's kind of like we substitute some parameters in this string. So when you say f and put parenthesis, so you have to put a variable that you have already declared. So when you do this, test loss is the string, and within this parenthesis we have this loss, right? So this will be replaced by the loss value. So similarly we can print the accuracy value. So I'll say test accuracy, like what is the percentage, and I'll call this accuracy. Let's run this. So this will execute once this step has completed, and then we have this saving the train model. So if you want, you can save the model, and you can also save this tokenizer, and you can maybe build a Streamlit user interface to this, and see you can just build a text input in your Streamlit app, and the user can type in some reviews, and once they click predict, it would show you whether that review is like positive or not. So that is like one thing, and the other thing that we can check is we can build a predictive system, so that when a user types in a review, right, so because this model now takes in numerical values as the input, the one that we have tokenized, but if they give a text input, so we have to know how we can convert this to a format that the model understand, and how we can give a prediction for it. So for this we can build a predictive system. So we used to build this predictive system when we are working with the ML use cases in my YouTube channel. So let's build a similar thing. So building a predictive system. So here we can create a function. So let's call this as predict sentiment. Here let's call this as a review. So here the input for this function is the review, the text input. So here the user can say the movie is good or the movie is not good, something. And then first step is we have to tokenize the data. Similarly, we have basically tokenized it before, tokenized and pad the review text. So this is user provided text, this review thing. So tokenize and pad the review. So we are just going to follow the steps that we did here. So we won't fit on text because we shouldn't do that, right? Because the fitting should only happen on training data. So we're just going to do the same thing, text to sequences and pad sequences. So that's what we are going to do. So here I'll say sequence is equal to tokenizer dot text to sequences review. So this would tokenize the data so that the it's basically compatible for the model to get it and make a prediction. And then we have to pad it. So I'll call this as padded sequence. This is just nothing but what we have done before. So this is pad sequence sequences of sequence comma max length is equal to 200. So this is basically what we did here, but we are just doing this in 2 steps. So even this you can do this in 2 steps. Tokenizer.text to sequence train data max length, and then you can do the pad sequence separately. But here we are doing this combinedly. So again, we can follow like any approach. So first we are applying the tokenizer to this data, to this text thing, and then we are padding it. So we are creating a sequence thing, applying the tokenizer to get the sequence of integers, and then padding it with pad sequences with max length of 200, and the input text is this sequence. And once you have that, you can make a prediction. So prediction is equal to model dot predict padded sequence and sentiment is equal to, so let's say positive, if prediction of 0 is greater than 0.5, else negative. Okay, so finally you can return your sentiment. Let's understand this code. So first we are tokenizing this text data. This review is basically a text data. So it's tokenized and then stored in this variable called a sequence. Then we are padding it to make sure that your input data has the same length, which is 200, the same length your training data has been trained on. And finally we are predicting this using model.predict. So we are passing this padded sequence to this model.predict, and this would give a probability. So here you would get like a probability value like this. So for each data point you would get something like, let's say 0.45 and 0. I don't know, it's like 55, I think this, yeah. So this kind of sums up to 1, right? So you would get a prediction probability like this. So we are kind of accessing the first element. So you when you pass this review and get a prediction, right? So this is how it's going to be. So there would be a list, and within that list you would have another list like this. Let me maybe put a comma here. So this is how you would get a output. So when I say prediction of 0, I am mentioning this part, this inner list, and within that I'm taking the first element. So this is the first element. So this is what I'm checking, and when you add both of these you would get 1. So you are checking this thing. If the first value, right, if it's greater than 0.5, then you are going to say it's positive. If it's less than 0.5, then you're going to say as negative. So this is just similar to predict probability of logistic regression or some other models. So you have 2 probability values. When you sum those things up, you would get a 1. So if this value is more than 0.5 or more than 0.5, it's going to be positive. If this value is more than 0.5, then it's going to be negative. So in this case, it would be negative. If this is 0.55 and this is 0.45, then it's going to be, positive, negative, and so on. So this is how this would work. So this prediction 0 of 0 and checking this 0.5 is nothing, but we are checking if this value is greater than 0.5. So if it's greater than 0.5, say it's positive, it is negative. So this case it would come as negative. So this is how we would give this prediction. So the final sentiment will be either positive or negative. So how you can call this function is, so it's in the third sequence. Okay, so here this is how we can, maybe I'll put this as example usage. So let's say this is like a new review, and in this new review the person says this movie was fantastic, and let's say I love it. So let's say I loved it. This is the review, and we say sentiment is equal to, now we call this function of predict sentiment, and within this we pass the new review thing. And finally this would give the sentiment. So this return this sentiment, and we can print this like print. Similarly we can use the substitution string, the sentiment of the review is this one. So this will replace the sentiment. Okay, so we are having like a raw text input. So we are passing this to the function predict sentiment that would tokenize this, pad the sequence, and then give a prediction and say if it's a positive review or a negative review. We can also have like other examples saying that something like this movie was not that good. Let me put it that way. So this movie was not that good. So here I'm using good, but there is a not, so it should understand that this sentiment is a negative sentiment. So let's see if it's able to kind of pick it up. So this is how we can build a predictive system and get an output. The other thing that you can do is, let me change this one. Okay, so here we have trained our model and we have got a prediction system. So let's say you want to, as I said earlier, if you want to build a Streamlit user interface, you can save this model as well as you can save the tokenizers properly. You can use maybe Pickle in order to save this as model.h5. I think, yeah, if you're using Pickle to save the tokenizer and other stuff, you can use PKL, or you can also save this TensorFlow models. Just use model.save.h5 format. You can do that. You export the models from Collaboratory. So when you save the tokenizers and the model, you would have those things here, and then you can download these models, put it in a in a local environment in PyCharm or Spider. Just build a script that has the Streamlit user interface, and once the user has typed in some text in the text box of Streamlit, you can call those models. Basically, you can have this function of predict sentiment and display whether that sentiment is like positive or not. Or other thing is like it's like it can crawl the IMDB site, and it can get all the reviews and map whether that review is positive or negative, so that a person who is going through the reviews would easily know whether, like, instead of going through the entire review, they can know whether it's a positive or negative review. So that's about it. Or you can also like take the 100 reviews, find the positive or negative, do average, and kind of say whether it's like positive or negative. So again, these are some of the examples, and this can be used for other sentiment analysis as well, but this is, we're just like getting started, and let's also do some more use cases for this. And currently it's in the 4th epoch, and we are seeing that the training accuracy first is 80 and the validation accuracy is 84. So this is coming from the 20% of validation split that we have here, and this is from the training data. So this goes on, and then we have this predictive system. So maybe we can wait until this 5 epochs is completed. I can kind of pause this video and I'll resume this once this training is done, and then we can look at the other code, and maybe once that's done, let's kind of do a recap for that too. So the training is completed, and overall it took 80 minutes. So we are seeing that the test accuracy is 0.883 and the test loss is 0.313, and the training accuracy is also 0.93. So there is not much difference. I would say the model is not overfitting, but again, we can improve this performance too by just doing better data pre-processing and trying to add more layers or kind of add more regularization to this. So we can do some research on this too. Later we will also be discussing this in the deep learning course on how we can do this training in a better way, do this hyperparameter tuning so that we get like a slightly better model. And now let's maybe run this predictive system code. So let's run this function code and see this. So here it should say the result is positive. So we are getting this accuracy as 0.88, right? So that means maybe approximately for 10 test data points, it should give the right answer for at least 8 data points. So let's run this and see 8 or 9 data points. So it says the sentiment of the review is positive, where it says the movie was fantastic, I loved it, and here it says the movie was not that good. So let's run this, and this would say that the sentiment is positive. Okay, so here it's not able to pick that up. Maybe let's run this again. So it says it's positive. Maybe I'll try some other things as well. So the movie was okay, but not that good. Okay, this says all those things are positive. Maybe we can check with some more data examples. Okay, so there is a slight issue in the predictive system code, so that's why we're not getting the proper labels. So here we are passing this tokenizer text to sequence and review, right? So what happens is it takes like each word separately. So rather we should put this review within this kind of square bracket. So this means like this is letting the tokenizer know that I'm getting the prediction for only one data point. So if you remember, in the predictive system for machine learning code we would do a reshape, so to let the model know that I'm getting the prediction for one data point. So it's kind of like similar to this. So that's why like we kind of didn't get like the proper response. So we have to make this slight change, and now we probably should get the right prediction for our code. So now let's run this again and check this. So make sure that you're putting this on a list. So now let's run this. So the first thing, so it's like a positive review, so we expect the positive as the sentiment. So it says the sentiment of the review is positive. So the next one is this movie was not that good, so this should give a negative sentiment. So it says it's a negative. And then we have this movie was okay but not that good. So let's see, this also should say negative, because we say that it's not that good. You can again try with different takes and see how it's working, but again the issue was caused because it's not it was not able to understand that it's for a single data point we are trying to do the prediction. So that's about this code. So I'll just give you a quick recap of what we have done, so that like you kind of get the overall picture of this. So first thing is kind of importing the dataset from Kaggle. So we have imported all the necessary libraries, and we have set up this Kaggle credentials in our environment by loading this kaggle.json file to this dictionary, and passing this values to the environment variables of Kaggle username and Kaggle key. And we have downloaded the dataset with this Kaggle API, and then we have extracted the file, read the CSV file to the variable called as data, just did some analysis of how the data is looking like, and we have encoded the labels to 1 and 0. And then we have the sentiments distribution, and see that it's like there is an even distribution, and we have did the train test bit. And the next part is the important step of tokenizing the data, applying patch sequence to ensure that the input data is of the same length. And then we have kind of set up the LSTM model with embedding LSTM and dense layers, and then we have compiled it with Adam, binary cross entropy, and metrics as accuracy. And then we have trained the model with 5 epochs. You can play around with the batch size and epochs and some other hyperparameters too. And then we have predicted and checked the accuracy on the test data, which is 0.88, almost 90%, which is good. And finally we build this predictive system where the user can pass a review and get a prediction out of this. So this is how you can work on this sentiment analysis using a recurrent neural network based or a LSTM model. So I hope this video is helpful to you. So please consider subscribing to my channel and stay tuned for more videos like this. So that's it from my side, and I'll see you in the next upload. Thanks for watching.